One, two, three. Welcome, everyone. I'm glad to see how numerous you are. And we will start without delay. Sorry for a few minutes delay, but a lot of things to settle. And I will start by a small introduction of this workshop, what it's all about. And here we go. So we have a long historical background of gathering the community around hydrology, the water cycle. Essentially, we started in 2003 with Annie Cazenave in Toulouse, and we've continued trying to gather the community in 2007 at WMO and so on, 2015. And the last one was a bit difficult to let's say, make extremely fruitful, because, you know, where you're not together, you don't think in synchronicity. And now we're together and we're really happy. And in parallel, we had the full water cycle activities, EO for water, one in 2015, then another one in 2020, which unfortunately was also not in physical presence. And so here we go. The objective of this meeting is reviewing the latest advances and results of the use of Earth observation. It's reviewing the progress in understanding the water cycle and all its details, variabilities, sensitivity to global warming or climate change, and so on. Reviewing the progress of novel Earth observation-based high-resolution data, how it's used, what methods we apply, how it is included in modeling, assimilated, and so on. At all scales, exploring the status of future EO missions, which stem from Hydrospace 2003, 2007, 2015, EO for water 2015, 20, and so on. And so we are going to think of what we need, and to paraphrase the United Nations Ocean Decade, you know, what the global cycle, what science do we need for the global cycle we want? And so exploring opportunities offered by the effective integration of the latest EO data. Of course, everybody says AI. AI, it means hurt in French, you know, aïe. So we have to make sure that we do it right. And advanced models and of all this computing technology that we have at our disposition now for developing, for instance, digital twins. We'd like to foster the networking and the collaboration among all the water science and stakeholders, and bring everybody together to make sure that the final result is bigger than the sum of the parts. Identifying the major scientific challenges, observation gaps. And this is where the agencies, of course, are really interested to hear from you. Do you need sub-daily water level, or is it okay to have a 25-day repeat, you know, 27-day repeat with Sentinel, or 10-day repeat with Sentinel-6, and other imaging instruments and optical radar and so on, and identifying the type of research that needs to be done. Okay, so basically, the space agency do not do what they want with their own ideas coming from nowhere. Basically, you tell us what we need to invest in. You tell us if you need more in situ data, more remote sensing data. You are the people who are driving the science of tomorrow. And you, meaning the stakeholders, the water managers and scientists. So we need to establish the state of the art. We need to identify the priorities for future science and applications. And importantly, applications, you know, like I think flood forecasting is a thing that we don't really know how to do at the local scale where it's needed. And you've got 11,000 people who died in Libya. You've got 6, 7, 8 people who died in Tuscany when we were doing the magic NGGM workshop, you know, variable gravity, which is probably the most important measurement humans can do on the planet. And characterize the capacity to address these priorities and these identified gaps, elaborate a roadmap for us to tell us what we need to do in the future. And so, you know, we define the actions that can be executed, but basically you recommend. And we use this workshop exactly for this, to shape the future, a roadmap for the future. And it comes from the discussion time slot. So basically, this workshop is your opportunity to shape the future. So we structured the workshop a little. Can you hear me? Oh, yeah. A little bit differently, we decided to work with themes and not topics or variables. And so some people are a bit puzzled. I don't see my favorite variable in this session block and so on. And the idea is to maybe think across the board a little bit, but it will boil down in the end when we put together the recommendations that we'll go back probably to topics and not to themes. Okay, we'll see. And so the discussion with the system blocks are very, very important for us. And I thank the co-chairs for organizing the discussion. And I thank everybody for feeding back to this. Yeah, so plenty of discussion time slot. We need to highlight the gaps in science and in observation. We need to look at requirements for gap filling and provide recommendation to agencies, different agencies, like for instance, all space agencies, but agencies that take care of in situ data, runoff data center and so on. And of course, the European Commission, which is a very important actor in Earth observation and elsewhere. Okay, so this is the pitch about what we want from this workshop. Now, a few logistic. This slide, I probably forgot to remove it. So logistics. So the Wi-Fi. If you have your cell phone, you scan, and you get in directly. You find this poster everywhere. The posters. The posters. I think I wrote something nice about the posters somewhere. I'm really fond of the fact that some people have posters, and they're the lucky people, because these people, they'll be able to show their work and discuss with people all week long. And I apologize for people who have an oral talk, because they're going to speak 20 minutes, maybe 10, 15, if you want questions. If you don't want questions, just speak 20 minutes. And then it's over. And then you have to pull out your laptop if you want to show your work to your colleagues. So congratulations to the people who got a poster. And you put it up now, and you take it down Friday at lunchtime. If you don't take it down, some people will do it for you and put it in the trash. And they are also, please come to the podium here and in Auditorium to upload your presentation. The lunch is off-site. We did not provide catering. It was a bit too complicated. So, but there's so many restaurants facing the river. So please enjoy a good meal. In Portugal, there's very good food. There's also restaurants in the mall and so on. And try to be here on time. Tell the waiter that you want the bill 15 minutes before 2 o'clock. All day long, but on Thursday we scoot a little bit, so it's 15. Be back by 15. We have an icebreaker today at 18:30. At 19:30 we'll turn off the lights, so find your way to the exit. It's a good time to look at posters. So visit them all week. Oh, there, lucky people who have posters. Visit them all week. And then the poster session takes place in Auditorium 3 and on the first floor. So we have two themes in Auditorium 3 and in the first floor. Social dinner. So on Wednesday, the buses will leave at 19:15, sharp, right in front. So you see, this is the picture of right in front where you have the flags. And there's going to be 4 buses that will leave. So let's get in the bus very quickly at 7:15 sharp. And then, and then you come back. There's a first bus that leaves for the people who are early sleepers at 10:30. And then the other buses will leave at 23 and 22. So try to catch the bus you want. So this is the place where you pick up. It's right in front. And okay, social dinner. If you're not registered for the dinner, you cannot board the bus. It's clear? Okay. I mean, I was told that I should not put yellow and red, and it's too much. Yes, but please, we have to get things organized, and we have the firemen on our back, breathing on our neck, that we cannot put one more person than we're allowed. If not, we all go to jail. If you're not registered, well, check with the registration desk if there are still some places left. I doubt it. And we'd like to thank the Operational Space Hydraulics Center, a French open initiative led by Magellan, CS, and Vortex, with a lot of partners that they offered. And I can tell you, thank you very much, because collecting cash, bringing it to the restaurant and so on, it's so painful and so difficult and so risky. So thanks to the Operational Space Hydraulics Center, they have a booth at the entrance. You saw opposite the registration desk if you want to know what they do. And okay, discussion time slot. The co-chair will simulate the discussion with seat questions. So co-chairs, I hope you have your seat questions. Maybe you can send them to me. I collected a few, but not enough to make a document. And just one thing, walk up to the microphone, make a line. I hope there's going to be a long line. And so we know in which order people can speak, and we don't run around with the microphone all over the place. And it's really nice to stand up a little bit. You know, the biggest criminal of humanity is the chair. Okay, and if you want a certificate, we'll make one for you. It's not printed yet, but ask for it, either to me or to Lorenza and the reception. Thank you very much for your attention. And so, Jean-François, my co-chair, he will announce the next speaker.
Yes, thank you very much, Jérôme, for the nice introduction. So we will have, first of all, a set of welcome presentation from the Space Agency and the organizer. And I just ask now Mr. Ricardo Conde from the Portuguese Space Agencies to make the first talk. Thank you very much, Ricardo.
Good morning, everyone. So in fact, I don't have the presentation. This is just welcome words. This is the easiest part of the day. I really want to welcome you all to Portugal, to this beautiful city of Lisbon. I really hope that you can enjoy some nice spots that you have here. And thank you, Jérôme, and thank you very much for to choose Portugal, particularly to this topic, space, Earth observations, new technologies to be developed. And this is something important for us, because particularly in Portugal, we are facing some serious problems in the climate as a consequence of climate change, but particularly the lack of water. You have been seeing probably in the news ourselves in the front line of things that are really complicated, like fires, big fires that we had in the last 5 years. Also, as a consequence of climate change, the lack of water. This is quite serious for our country in the last 4 or 5 days, or 4 or 5 years. And the reduction of the precipitation, almost 40% in the last decade. It's quite serious what we are facing here. So it's quite an opportunity to discuss how space agencies can really help, because we have been seeing that emerging new constellations, new sensors, development of new applications for Earth observation. This is the role of space agencies. So thank you to ESA, and thank you to all the organizers to bring this topic, so important for Portugal, into the countries of South of Europe. Let me just also tell you that particularly the Portuguese Space Agency is quite engaged with this topic. We are quite engaged to develop also a new set of sensors to tackle this problem, particularly to, in the next 2-3 years, to have 30 satellites also to address several sensors, not only the synthetic aperture radar, optical sensors, new way to observe, but particularly a new Earth observation data policy, which is one of the things most important. Particularly high resolution in time and space resolution is something that we have been observed for our community as a need. And this is something that we really need to do. In the next 2 to 3 years, we will address a new way to look to Earth observation policy. It's our commitment to bring to society open data coming from the high-resolution satellites that we are also preparing. I think this is an answer for the agencies. Also, new operators that they are looking particularly to Earth observation as a market, but here space agencies play a really important role. Normally I give the example of GNSS data. When you look particularly to GNSS data that all of us, we have in our mobile phones, we are not paying for that. This is an open policy. And look at what we have been achieved to develop new applications. Can you do it for the Earth observation data? I really believe that we can do it, and this is what so many countries that we are preparing, because it's mandatory, it's urgent to have a new policy for Earth observation. So this is the easiest part of the day, the welcome remarks. I really believe that space technologies, probably all the results of your discussion that we will have these 5 days will bring some new ideas, probably some new requirements, and also a challenge for national and international space agencies to be more present in this path to develop new technologies for our society. I really wish you fruitful discussions in these 5 days. I really hope that we can get some solutions. Probably we'll see some emerging new technologies coming from this discussion. And thank you again, Jerome. Thank you, the European Space Agency and all the sponsors, again, to bring this important topic, particularly for our country. Thank you very much, and welcome again to Lisbon and to Portugal.
Well, thank you very much for hosting us in Portugal. We really appreciate it. Part of this community was here some time ago for the Ocean Surface Topography Science team, and we're very glad to be back here.
So now we have the welcome presentation from Jérôme again, but on behalf of ESA.
Yes, on behalf of the European Space Agency, everybody is quite busy, and there's a certain number of apologies that there should have been a little bit more ESA people here for different reasons, including not being in good health and so on. So I will do the welcome from ESA, and it's very nice. So basically, welcome to Hydrospace. And in the interest of time, thank you very much. No, wait, I think I have another slide. Okay, so in the coming decades, increasing population will drastically rise the demand on fresh water, and global warming will intensify drought and floods. Nothing you don't know, but we need to get together and find the best collective response and the best science that we can do as a foundation for the right solution, just like Ricardo Conde mentioned just earlier. And so this unique set of grand challenges that humankind is facing requires more than ever that the scientists advance the understanding of the Earth system, especially the processes and the impacts of human activity. It seems that the human species has something to do with the evolution of the climate. So we need to translate that into a novel solution for society. So ESA is proud to be supporting studies in the water cycle since a long time, with observations on one side and also investing in research and development in coordination with the European Commission and international partners. We just held last week a very important coordination meeting between ESA and the European Commission. It was a workshop open to all the scientists that are involved with ESA activities. And the idea is to boost what we call the coordinated calls with the European Commission. And there will be a report of that, and we will have a way forward, a strategy to go forward with these coordinated calls. And so concerning observations, well, we have a lot of satellites that are operating, and we're developing many, many more, and we are even preparing some for going forward. So people at ESA are working over 77 satellites. When I got recruited, we had one, and now we have a lot more, and a lot of more variables which are measured. And we decompose that with explorers, the science part, the Copernicus part, which is the operational part, thanks to the European Commission, the Copernicus program, and of course we build satellites for meteorology operated by EUMETSAT, and they contribute also to the subjects we are interested in here. So we exploit a suite of satellite missions that are good for hydrology. I can name a few, and I'll forget a lot. Sentinel-1, Sentinel-2, Sentinel-3, Sentinel-6, Micah Freilich, all the Earth explorers that we have launched so far, and the one that we're going to be launched, and the meteorological satellite as well. So, and you know, the jewel in the sky is called SWOT now, especially for people like me that grew up with altimetry in the, what do you call it, the baby bottle, you know, biberon. And so we're very fond of exploiting SWOT data in synergy with all the other data that we have. We're working hard with the Sentinel-3 next generation. And for the first time, we put hydrology as a primary objective of a mission, you know, like SWOT. And then the follow-on of Cryosat is Crystal, and we think we can do nice things over inland water. And for me, the most beautiful measurement is variable gravity. And so we just came back from Assisi, where we had the magic workshop, and we're really looking forward to a follow-on to the Grace, the Champ and the Grace series, and so on. And so we also need in situ data. We need models, and I thank also the European Commission for supporting that part. Investing in research and development. So we are launching the water cycle cluster in the science hub at ESRIN in Frascati near Rome, where I work. And there's a special session tomorrow morning in the other auditorium about what is this water science cluster. You have different opportunities in the future, like visiting scientists, you want to spend some time in Rome. An example of the ongoing activity is the follow-on of Stream and StreamRide and the RightSat. And I see the people from Perugia just arrived. Here we have the queen of the river discharge running the RightSat program. And that led, looking at the roadmap, the near real-time river discharge and flood forecasting. We absolutely need flood forecasting 3 or 4 days. The people who are suffering from flood, they need to know with 2 days in advance how many bricks they have to put more on the levee. And we don't really know how to do that in local scale. We do global modeling, and it works well, but we have to do that. So we're launching a big activity to do that. And other activities like assessment of human impact on water cycle, the high resolution, high mountain hydrology, impact on climate, and so on. So this is just a few details about what is Stream Next, the first global space-based. I won't go through it because I don't have much time to do this. And the near real-time river discharge, I think it's a very important thing, and it should come out soon in 2024 as an invitation to tender. And the focus is near real-time, quasi-near real-time. Can we do it in 3 hours, or do we have to wait 3 days to do this? And then make it operational in the future. I mean, 11,000 deaths in Libya, 5 people died when we were just in Assisi because of flooding and so on. We have to stop that, and we can do that with the Earth observation and with the modeling. We're supporting a community with the altimetry community, which is essential for water surface elevation, river discharge, and so on. And we have this altimetry virtual lab. Just go there and see how you can customize the processing of the altimetry for your small target. The smaller the river, the more difficult, and the more useful maybe. And please see the poster by Marco Restano, our magician here, number 24 upstairs. We also developed the toolboxes for the community, the BRAT, the Broadview Radar Altimetry Toolbox, and the GUT, the Ghost User Toolbox. I'm the culprit for the name, so don't blame anybody else. And we do a lot of effort to gather the community. This is a proof here. And so I showed this slide in the other presentation. So there's a long history of sustaining the community and bringing people together. Also, near the coast, in the estuaries and so on, the coastal altimetry is also an important, and for 15 years, we've been supporting this community as well. And next, and also, you know, the 15 years of progress in altimetry, 20 years and 25 years. And so the next one, it's 30 years of progress in altimetry in Montpellier in September, 2 to 7 September 2012. Save the date and come to Montpellier. It will be a pleasure to meet you again there. So ESA is looking forward to the output of this workshop. Plenty of discussion time slot. It's the most important part. Highlighting the gaps in science and observation, providing gap-filling requirements, recommendation to agencies, to the European Commission, and to other funding agencies or other stakeholders who are interested in supporting things. And everything will be reported in a document, which is going to be called Summary and Recommendation of Hydrospace 2023. I would like to thank the European Commission to be with us in this adventure. Looking forward to the keynote that Panagiotis Baladonis will do on Friday. And a warm-hearted gratitude to our Portuguese colleague, Isabel Trigo from EPMA, which means the Portuguese Institute of Sea and Atmosphere, to have helped us make this happen. And credit to EPMA, it will rain tomorrow, and it will rain on Wednesday, maybe, and it will rain on Thursday, and so on Friday. So I hope there's going to be a lot of people here on Friday. Anyway, it's going to rain, so don't go anywhere. Come here, and so on. And I'd like to thank, of course, the sponsor of the dinner, and we really appreciate that. It simplifies a lot of things, and we appreciate the effort that they do. Please visit their stand. And on day one, Hydrospace 2023 is already a big success with 239 abstracts, which was more than anticipated. 269 people registered from 45 countries. Have a fruitful workshop. Thank you very much in the name of ESA.
Thanks a lot, Jerome, and thanks to ESA to organize all of these meetings and all of these activities. This is very, very impressive and very nice. So next, welcome speak is from Sophie Legac from CNES. So on behalf of CNES, Sophie, your time.
Good morning. Dear Ricardo, dear Jerome and co-organizers, dear colleagues, it is my great pleasure. Oops, something that's. Good morning again. So it is my great pleasure to be here in Lisbon today on behalf of Selma Cherchali, our Earth Observation Deputy Director at CNES, the French Space Agency in Toulouse. Unfortunately, she couldn't be here today, so I will try to be her messenger for some key messages. So I'm very sorry I lost my voice somewhere between Toulouse and Lisbon. So bear with me while I try to spare what's left of it, and I promise I will be brief. So first, let me say that CNES is a long-standing partner of ESA in the co-organization of this event since 2003, and that we are looking forward to this fruitful meeting. So as we all know, water is a crucial resource in the context of climate change, and in particular, fresh water. This is no less than our future that we are talking about. CNES program in Earth observation is centered around this idea to commit to a more sustainable world. So the need for hydrological data is quite obvious when we talk about sustainable development goals from the United Nations and adaptation to climate change, because you can't manage what you can't measure. So obviously, satellite data present many benefits with respect to in situ data, and we now need to merge and reconcile the both of them. Over the last decade or so, we have seen a true revolution in the satellite missions used for hydrology. Many improvements have been made in terms of accuracy, with more specific spectral bands, for example, an increase in the temporal resolution, going down to a few days with Sentinel-1 and 2, an increase in spatial resolution with SWOT, now measuring 100 meters wide rivers. It's quite incredible. And also a major progress in the accessibility of data, because they are freely available for the community. Finally, a long-term sustainability is achieved with the Copernicus program. So I just mentioned SWOT. This joint mission with NASA is already giving us impressive results and makes our water dream come true. So I could not resist to show you this first CARIN image that we got early in the mission in March 2023 over Toulouse in France. So the city is here. When we saw this first image, we were speechless, and I still am, obviously. And the quality of the CARIN instruments is such that it is possible to distinguish even the smallest rivers, like the Canal du Midi. It's this one. And it's quite incredible to be able to see that with SWOT. I know there is a keynote speech later, just before lunch today, from Cédric David, from our colleagues from JPL. So I'm sure they will show maybe some results, amazing first results. And also I know many French colleagues will present results from the lakes and the river products this week. So make sure you attend the SWOT session on Wednesday morning. And in the frame of the SWOT mission, CNES has also been very committed to develop a downstream program to manage the data. And the HydroWeb Next service is the name of our multi-sensor, multivariable integrated approach for hydrology, delivering many water-related variables and products. And I think there is a grand opening this week about HydroWeb Next, so please make sure to go see the people involved in this project. As Jérôme mentioned, we need to work together as a community towards an operational hydrology system. And to this end, CNES and its partners are supporting ESA's program, Digital Twin Earth for Hydrology. So this is the future. And in conclusion, CNES is already very much involved in all activities, innovative satellite missions with, for example, SWOT, SMOS, Trishna, and also AOS, it's an atmosphere observation system for the water cycle, and the Copernicus Sentinel missions. We are supporting continuous research activities. We are working together with partners and developing new data services. So I wish you a very fruitful meeting and enjoy the week in Lisbon. Thank you.
Thank you, Sophie. Our next speaker is from GWEX, is Peter van Ovelen. So, please.
Good morning, everyone. First of all, glad to see you here. I think quite a few people I haven't seen in a long time, so it's always nice to see some familiar faces again. Let me go. Let's see. There we go. Which one is it of all these? Oh, no. Okay. Yeah. No, it's not pressing hard enough. Great. Thanks. Well, that's exactly the most important slide, actually, from my presentation. I've got a couple of you. First, ESA and CNES, thank you for the great partnership in organizing this workshop. In particular, Jerome, thank you very much. You've done the bulk of the work. It's very much appreciated. You and your team did a great job. Thank you. You all, of course, thank you for coming. And my GUX colleagues, and as well as my office colleagues, I cannot appreciate them enough. So for those of you who are here and are not familiar with GUX, you should be, because it's been around for 35 years and is looking at the global energy and water exchanges, and it's part of the World Climate Research Program. And our goal is to facilitate international research collaboration to advance biogeophysical, climate and weather research. As I said, we've been around for more than 3 decades. We've done a lot of things. In the beginning, our focus was very much on initiating new observations from space to actually observe the water cycle. And our role has shifted a bit around many other organizations now, and the space agencies themselves have taken up that role as well. We're much more now into assessments. What does that do? Pushing the community to look at it, not variable-wise, but process-wise, and putting it also more into a larger, broader context. So that's are the things that we're working on. If you want to know more, I put a couple of slides in where you can just go back and see. But this page, this science plan is only 15 pages. So if you want to have a quick overview, you can do that. And I'll let it out for people who want to take a picture. And this, of course, is one of the key elements when we're talking about energy and water. Our food, our lives are depending upon it. And basically, the future of our food very much depends on the future of our water. And we've got, of course, other boundary conditions to deal with. Global population growth is one of them, but also things like waste and how do we deal with not just food waste, but also water waste. And one thing I want to really emphasize here is water is a renewable resource. Don't think of it as a static. When we talk about hydrology, a lot of people think in static terms. No. The biggest transporter of water is the atmosphere. So keep that sort of thing in mind when you're trying to solve problems, and don't look at it from a static point of view, because I think that's when we run into problems as a society. Really, there are a lot of ways to address the challenge. There are plenty of ways, and we have a long way to go. But really looking at it and using space observation is one way to do it. Understanding how water moves through our system and get a better handle and grip on what it does and how it's going to change with climate change. That's important. And Jerome pointed out flooding. But forecasting is important, certainly near real time. But how is it going to change in the future? When we're dealing with infrastructure and that sort of thing, we have to know how it's going to change in order to actually prepare ourselves for future floods. Because, 3 days in advance, we cannot do much about the structure. We can only get people out of the way. So there are many ways to challenge and look at the problem. This is a sort of short slide to keep you all a little bit titillated about trying to figure out how to solve our problems. So GUX itself, back to it. We organized around 4 panels. We're looking at global data products with GDAP, primarily looking at assessments. How good are the products? And not so much as a competition, but more for the purpose they are intended. We assess how they compare to each other within certain framework. We're really trying to also push the agencies to be consistent in their data products. Really look at all the angles on how to make sure that combining satellite observations with in situ observations, we get a consistent product. For climate variability, that's very important. Inconsistency in satellite data is not helpful. But that's just one small little aspect. There are many more. GAS are global atmospheric system studies. I'm not sure, I'm not a fan of the acronym, but somebody said leave out a G and you know what you're at. But anyway, it's really looking at processes in the atmosphere. And glass does similarly, but looking more at land-atmosphere interactions. And then we have our panel looking at hydroclimatology, more the regional focus, more the local aspects. And we're really, through this organizational means, try to rally the community and organize ourselves to support research collaboration. And again, we're not really doing the research, we're just enabling research collaboration. That's really our key thing. I'm going to skip this one. So, as I point out, processes and in particular land-atmosphere interactions are our core business, and they're complex. And I can quickly show you that. This is just one aspect on how many little things there are, you have to deal with. And they're all interdependent. So you get one wrong, you get a lot of other things usually wrong too. Let's see if I can. So for that, and this is not just for land-atmosphere interactions, but the more we're going to work together, we need to speak a common language. And this has been said many, many times, but we keep forgetting it. And we really need to know how we define things and really be respectful of that. In particular, for instance, when you're looking at soil moisture, soil water content, soil matrix potential, they're not the same things to the same community. I mean, there are some physical definitions, but the way they're used in the various communities is not similarly. So really look at also some of the key questions that are here as sort of a start for your thing. And then I'm going to go to the end. We have Earth observations, but we also have in situ observations, and we really are evolving there as well. This is an example of doing a sort of MRI of the land atmosphere processes, really looking at all the different things that are going on, turbulence in the atmosphere at a relatively large scale. This is the type of thing we need in combination with satellite observations. And why do we need that? Because our models are now at such resolution, both temporally and spatially, that they're outstripping our observations, meaning it becomes harder and harder actually to evaluate if we're doing the right thing. And hence, improvement of in situ observations needs to go hand in hand with the capabilities that our Earth observation is providing us. And one way in GUX is also to rally the community. As I said, we have regional hydroclimate projects around the world. The ones in blue, although not very obvious, two in North America, the Global Water Futures in the US Regional Hydroclimate Project, one in South America, Andex, one currently in Europe, Baltic Earth, a couple in Asia, the Third Pole Environment Water Systems in Asia PACs, and hopefully soon Central Asia. And we're working now on Africa as well as Australasian to get another one there. But this is our way to organize ourselves and be effective. And with that, I just want to promote another conference next year. We do that every 4 to 6 years, the GUX Open Science Conference in Sapporo. You're all welcome. It's a wonderful city. If you haven't been, highly recommend it. And look forward to seeing quite a few of you back. Unfortunately, I have to admit, it's in the same week as IGARS, darn. Anyway, thank you very much and look forward to talking to you.
Thank you, Peter. Thank you, Peter, and thank you for starting with the seed questions. I will pick them from your slide, and you can, of course, promote them in the different session. So the next speaker is unfortunately not here with today, but we hope to see him coming in the near future, meaning maybe by Wednesday. It's a great honor to have with us the European Commission represented by Panagiotis Baladanis. And he works in the research and development part of the European Commission, what we call DG RTD. And so, Panos, you have the floor. We see you, and we probably hear you as well.
Yes,
thank you very much.
Hello, good morning. I hope you can hear me.
Yes, very well.
Okay, thank you very much, Jerome. Good morning to everybody. Apologies for not being able to join in this first day personally, but as also Jerome mentioned, I will also attend in the last 2 days of the conference, and so I hope to have the opportunity also to meet in person, many of you. So let me say that it's also a big honor and also a pleasure also for me to address also this important audience, and also to convey the wishes of the European Commission, in particular also the Director General for Research and Innovation, DGRTD, also for the successful conduct of this important conference. I don't think that I have to say to you that it is very hard also to overestimate the importance of water. Every community across, the globe is relying on the availability of the clean water. Water is important, for our health, for food security, for sustainable development, but also what is also to stress that also water is also an important economic sector of growing also importance also for Europe. But as you know, we face a triple planetary crisis of climate change, biodiversity loss, and pollution. And you will agree with me that water is at the heart of all these challenges. And therefore, we cannot not longer ignore that the world's crisis of water. As it was also mentioned, water, land, biodiversity, food, energy, and climate are really interconnected, comprising a coherent system, what we call, this nexus. And this system is also dominated by complexity, and feedback. And so putting pressure in one part of the system can create pressure of the other. So this also shows the challenges that we and the hydrology also, who is at the heart of this system, also can play, and how is important also to measure and to address also these interlinkages. But the other thing is also that you all also know better than me that, the global hydrological cycle is changing. And precipitation is likely to become, less predictable over the time. And so the new normal might include also prolonged droughts followed by floods also in the same region. As it was also in a recent report, which published also this year in the context of the UN Water Conference by this Global Commission of the Economics of the Water. And what is important that I mentioned this report, because this report has been also produced by I would say, water specialists. So, but this is important. This is a report which is called Turning the Tide, a call to collective action. And this report, also stressed that we have also pushed the global water cycle out of balance for the first time in our human history. We have breached the planetary boundaries for water that keep the Earth system safe for humanity and of life. We face a systemic crisis of water, which is both local and global. And this also put it in risk our activities and also our sustainability objectives. And what is important is that this is not only a matter of climate. Of course, climate also is playing an important role, but this is also the impact of our, I would say, unsustainable management of water resources over the last also the decades. So we have, so nothing, let's say this is new, but what is new is that we have also to have a new approach also to address also this project. And in order also to reduce this vulnerability of water-related systems and society, we have also to improve also the knowledge of water resources availability and use. And this is also very important, and research and innovation plays also an important major role. And as also it was also mentioned, in particular because it is very difficult also to monitor, in systematically the whole hydrological cycle. Both, as I said, in global and local scales. Of course, there are many activities. There are the main international projects that are GWEX, and they are doing ESA also is doing also an important work. But this is the point: is that there is only a tiny fraction of water bodies which are monitored. So I think this is we need also to improve this, and Earth observation also can also help also to overcome also these limitations of the in-situ and traditional also water body monitoring. So Europe has also been at the core of supporting also research and innovation in water, trying to have, a more holistic approach. Just to give you an example, in the previous Horizon Europe, Horizon 2020 framework program 2020, 18 to 21, we spend more than 1.3 billion of funding, spend it, in water-related projects dealing, with water quantity availability, water quality, water resources management, ecosystem restoration and protection, and also within also the context. An important also component has been also to support also Earth observation, and as you mentioned, as Jerome also mentioned, I would also support this collaboration effort together that we are doing with ESA, also to support also this Earth initiative that ESA also undertaking, and water also fresh water is also one of the flagship initiatives, and also we're collaborating with that. But what I would like also to just to mention in just before closing is that also to that the also following also the UN Water Conference of this earlier this year in New York, and they created a kind of very important also political momentum. We see now that also water is rising high also on the EU political agenda, and this is also very important. We have, last July, the European Parliament had important discussion, on the water scarcity, water droughts, also in Europe. Most recently, also another consultative body of the Commission also proposed an initiative which is called, the Blue Deal, also for Europe. But most important, and this is I would like also to finish, is that the Commission also, our Commission President Ursula von der Leyen announced in her speech, for the State of the European Union last September, a new water resilience initiative for 2024. And I think this initiative opens, an important also opportunities also for research, because you would like also to use also this opportunity and to also have also strong research and innovation dimension in this initiative. So I hope that this conference will also provide us also some key elements about what are the research gaps, what we have also to do. And so we will be also happy also to look on the outcomes and take this properly into consideration. So once again, thank you also for this opportunity to address this opening, and I will be very glad also to meeting you towards the end of the conference. Thank you very much.
Thank you, Panagiotis. We really appreciate your message. And now we switch to the keynotes. And the first keynote is going to be given by Luca Broca from Peru. The people who arrived just this morning, just in time. Luckily, there was no delay. And so Luca is going to talk about the digital twin for water and the energy cycle. We have a problem with...
Yeah.
One computer. Les aléas du direct, like we say in French TV. WebEx works fine, except on that computer. So Marco, the magician, will relaunch everything very quickly. And Panos, if you're still online, we are looking forward to see you maybe Wednesday evening. Let us know. If not, Thursday morning.
Unfortunately, I will arrive late Wednesday evening, so I will not be able to join the dinner. I hope another opportunity.
Okay, well, we are looking forward to your keynote on Friday in all cases, and looking forward to see you on Thursday morning.
Thank you very much, and apologies, but I will have also to leave for another meeting.
Okay. Yeah.
Thank you.
All right, so Marco is restoring the WebEx session on that computer, which will allow us to record. I mean, the idea of having WebEx is that we have a very inexpensive way to record the meeting, and the idea is to put it on YouTube channel that we have for our workshops soon after the meeting, after I censor all the bad things you're going to say about the European Space Agency, of course, and edited in chunks which are findable and readable. And yeah, it would be nice to restart the WebEx session, because then Panos can follow the video, because we've separated the audio and the video. And so we have the audio on another WebEx account.
Work. Okay, I think, Jerome, we have to continue without WebEx. I tried again, but it doesn't work.
Uh-oh. Da, da, da. Bad luck. So all the signals are not green. We're not ready for launch. But we... So I have to take care of it. Again,
No, I can restart. It's just like S3, or let's say speaker as it was before.
Oh, everything works except for security reasons. We are not getting back in. But what login do you use for this?
Same they use this more. Just a fake, because we are guests. Yeah, so you
This
can
is the guest?
whatever, yeah. So you cannot proceed.
And can you just launch the browser instead of the application?
I go.
Yeah, go. No? Well, it's okay. It's not a problem. There you are.
Okay. On the web, it's okay. Share screen.
Share screen. Share screen is available or not? You're now the presenter. Yes. Okay. Share screen.
I don't have the
You have to authorize the camera.
Nice both.
Okay, forget it. Let's go. We're in?
Okay.
What is this image?
Share.
Yes? Share? We got this.
Let's see.
Yes. Well, a big applause for Marco.
Good morning, everybody. Thank you for inviting us for this talk. As you can see from the slide, it's not my work, it's the work of many people all together. And the topic is really to basically to make some steps towards the development of a digital twin for the water cycle. Let's start from the storm Daniel. Actually, also Jerome mentioned before. This is very important for two main reasons. First of all, it highlighted the fragility of the Mediterranean basin and actually of all southern Europe, but not only. And second, if you look at the precipitation, actually in Greece, it rains like the same amount of 1 year and a half, with more than 800 of square kilometers of flooded area. Basically, new lakes were developed after this event. And in Libya, it rains much less, but the number of casualties is really huge. Actually, the actual number is still not known. But if we believe that probably is one of the most impactful flood events for sure occurring in Europe and in Africa in recent years. So we need to make something for that. On the other hand, we have drought. This image is just northern Italy, April 2020 against April 2022. It's nice because it's high resolution, 1 kilometer resolution. This is soil moisture. Red means drought condition. And this image is quite nice because actually you can really see the variability of soil moisture over space at high resolution. And this happened in Italy, but for instance, I take up this image analysis from the Landsat, from EUMETSAT. This index is called the heat wave magnitude index. And basically in 2022, the index was nearly 70% higher than the maximum value recorded in the previous 20 years. And particularly the Mediterranean area is quite red. So drought last year was very, very important. Third example, not as much you think. This is also was mentioned by Jerome before. We have on track 2 projects for that. The maps shows the trend of runoff that we have obtained by using our approach that exploits satellite data and particularly gravimetry data. And the map is quite red. It's quite red also in Central and Northern Europe. And this is not as expected from climate projection that actually we expect red in the Southern Europe, but not in Germany, not in Poland. And basically this analysis is trend for the last 20 years and actually opens new activities for hydrological research in the future. What we have done? We have done what we call the Digital Twin Earth Hydrology Project. It was a project that lasted more or less 2 years and a half. The purpose is to basically put together high-resolution Earth observation and modeling to analyze and investigate the extremes and also for water resource management. There is a paper that is going to be published probably this week or next week. We are waiting for the edit of final acceptance, but that basically highlight most of the things that you can see in my presentation. But let's start from this very nice video that was developed by a US company. This is what we have done. For the Mediterranean basin, basically, we have developed whole the team. We have developed a high resolution observation for the main component of the water cycle, precipitation, evaporation, soil moisture, and snow, and also runoff and river discharge. And we move from what we had in the last, for instance, 5 to 10 years ago, 20 kilometer resolution. And now we move to 1 kilometer resolution and also to daily time scale. This actually happened thanks to capability of new observation from satellite, like for instance, Santiago constellations, but also new capability in terms of retrieval algorithm from the different partners. Then we put all together this data and we integrate with high resolution modeling. And for instance, here in the video now, we are going to Sicily for the flood occurred in 2021, October 2021. This was basically the MEDI came before the one that happened in Greece and Libya. And we were able to basically estimate flooded area and also flood velocity for these flood events. And we also made integration comparison with Sentinel-1 data to assess the quality of the simulation with respect to the quality of satellite data. And finally, we also do what we call what-if scenario. This is an example for what-if scenario for flood risk over the Po River. Basically, each graph here is a river discharge time series for different locations along the river. And basically, we built a what-if scenario that you can play around with different scenarios for initial storm muster and precipitation, and the system provide you the results in terms of river discharge at different locations. I will show you later that basically there is a platform online, you can go there and you can play around also with that. So digital twins bring together state-of-the-art technologies and also machine learning and also Earth observation and modeling to basically address. These are we just pick up some of the events occurred in the last years in Italy. And this is an effort from the Digital Twin Earth and also for the Med Hydrology project, and the video is from Planetary Vision. They are very nice. Another example, drought understanding. This is another project that we have with ESA. Typically, drought, we look at drought like with the standardized precipitation index, but precipitation, like evaporation, is a flux. It's not a storage. So probably it's much more useful to look at the drought or looking at the storage, like a snow, like a river, like soil. And now from satellites, we have this observation, and we have this observation also at high resolution. So for instance, this is an example of a small basin in northern Italy, over the Alps. And basically, we have different maps that show you different products for soil moisture, for evaporation. And basically, the different components provide you a different information. So for instance, if you have a deficit for snow, it means that you will have a deficit for the next 3 or 4 months. If you have a deficit for soil moisture, then the deficit is for the next month. So we need really to know where the deficit is to understand how to manage water. There is another platform also here that you can go there, and basically you can also visualize and intercompare different products and analyze them. But this is the good part of the story, but actually we have a lot of challenges to be addressed. One of them is these product resolution are available very recently, and so resolution versus sampling is one of the first challenge. A second challenge is related to the data, the consistency between the data with respect to the independency between the data. The complexity that also was underlined by Peter before about the physical and human processes, particularly if you want to model this at high resolution. How to model this, modular versus centralized approach. And finally, this is part of the discussion I had with many colleagues. We need to think really about how to make the data available, data infrastructure, and how to visualize and to show the data to the people. Because I remind you that actually digital twin and is under basically the destination Earth umbrella, and basically this digital twin was modeling. We are doing modeling for many years. The main point here is that actually we want that these models can be used by everybody. Everybody means politicians, scientists, but also citizens. And so to make them usable, we should also make these kind of efforts. I will go, yeah, we are working on these challenges in different projects with many of them with ESA, but also with EUMETSAT and also with the European Commission. Let's go step by step with the different challenges. High resolution is kind of trend. In the slide here, I've picked up just 3 papers, and one, the natural data sets that basically were developed this year. All of them, all of them basically are daily, 1 kilometer global gap-filled satellite and reanalysis soil moisture product. And it's not only for soil moisture, it's also for many other variables. So the point here is we have all these variables. Who is going to understand if these data are useful or not? Who is going to assess this data? Who is going to make this? I make just a first example for Italy. Of course, I came from Italy, probably you have already understood. These 4 maps should be all 1 kilometer. This is just monthly anomaly of soil moisture. And if you look at the data, you just look at the picture, you can really understand that one of the data is not 1 kilometer, or no, or probably one of the data is too noisy, or I don't know. You can pick up whatever you want. But if you look at the, for instance, the second with respect to the third or to the first one is quite different, the patterns, and also the fourth one. In principle, they should be all 1 kilometer, but probably they are not in reality. Another example, more easy to understand, if you have a precipitation events, then the footprint is really visible in overground. Again, 3 products. Red means positive variation. I should have changed the color, but I didn't. And basically, you can see that, for instance, on the top left, Sentinel-1 is really able to really track the footprint of precipitation overground. And this is not the case for other products. And for instance, if we compare with this on the bottom right, a 10-kilometer product is probably much closer to the one on the top with respect to Sentinel-1. So what is the actual resolution because of the data? And just the last example for looking at really, again, Sentinel-1. On the right, you have radar precipitation that is really 100 meter, 500 meter resolution. On the left, you can see the track of soil moisture. And you can really see that also, actually, by using radar, you can really see the patch, because, for instance, when you interpolate re-engage, this is not the case. So Sentinel-1 is really able to see this, and this is not the case for several other products. Consistency versus independency. This is an example that we have that I take up from these 2 projects, DT and 4D MED hydrology. We are developing an Earth observation product over the MED, because actually I've shown that we have already done, but we are continuing to work on it because we are improving. We are developing multiple products. We are trying to understand how the data are. These products are based basically on only one satellite, on only one single sensor. Actually, for IMERGE, it's not really the case because it's a constellation of satellites, but the other one is, for example, only from Sentinel-1, only from Sentinel-2, only from Muscat, so a single sensor. Then we have a number of models that we use for developing derived product. And this derived product, for instance, the most derived one is related to evaporation, but also snow melt, terrestrial water storage. And if you look at the link between the different products, you can really see that it's kind of, okay, you can't understand, me too. But basically the data, there is a strong dependency between the data. And so when we are going to use the data, we should know this dependency, because otherwise we can use the data with, I don't know, making a comparison, for instance, of gauge-corrected precipitation with gauge is typically one of the problems of several papers today also. Complexity of physical process. I take the example for soil moisture because I worked for soil moisture in the last 20 years. Here are 2 maps. One is the model, one is the satellite. And these 2 maps should be the same. This is the standard deviation, the temporal standard deviation of soil moisture, and you can really see that the map doesn't look similar. If you look at the mean, probably even worse. Then the question for you is, what is the model, what is the satellite? I will reply, for sake of time, on top you have model, on bottom you have satellite. And if you look at the spatial correlation between the data, that is this plot, this is for each time, for each day, I compute the spatial correlation of the data. Hardly it is higher than 0.2. So basically, if we want to model the soil moisture in space, we are really far from getting at least a good comparison between satellite and model. Then you can say, okay, the satellite are wrong or the model are wrong. ESA will say that model are wrong and the other blah. But actually, we need to actually address these problems. Human processes, I take this example for irrigation. Probably you know that we are working on irrigation in the last 4 or 5 years. It's really a hot topic. And basically, we are working, irrigation is the major water consumer of the earth, 70%, but in some areas it's 90%. And data are absent, well, basically. We don't have the data. Everybody wants the data, but of irrigation, we don't have. And so probably this is one of the major impact on the water cycle. And we are working towards getting irrigation water use estimation from ESA. This is work done from one of my colleagues. Actually, this is, you can see the animation of irrigation water used at high resolution that now we have for the Po River, for Spain, but also northern Africa and France, but actually we are developing the products more or less everywhere. And again, we have projects with ESA and for going ahead in this direction. Finally, modular versus centralized approach. And this is an example for basically, we have one of the application of DTE was the flood risk assessment. For doing this, we start from here. Each box is a product. It means that for each box, one partner, so I don't know how many people, but 1, 2, 3 guys are developing the products. And so this is valid for each box when you see the satellites. If you want to make flood risk, that is quite easy with respect, for instance, to water resource management, then you need a model for snow, and then you get stone melt. Then you need a model for soil water balance, you get percolation, model for groundwater, surface and subsurface runoff, and then routing for river discharge. Flooding, hydraulic model, you can compare with flooded area from satellites. At the end, you get flood risk. Each module basically can be modeled in different ways. And the point here is we should make the different parts of the system available to everybody in order to make all the communities interacting with this system. Because otherwise, if you make a centralized modeling approach in which, I don't know, one important or very fantastic center do all the job, basically we are going to lose all the activity that we as community are doing. And this is for flood risk, and for water resource management is even worse, because actually there are also the human impact that is really, really very important. I will not go to explain these plots. Finally, data infrastructure. I'm not expert and I don't know anything about that, but people started to tell me, okay, Luca, you are going to provide 1 kilometer data for continental scale. Nobody is able to actually get the data, even scientists. I get a lot of email. Oh, I need the data for here and for there. I am a scientist, but they are not able to. We want to make this data available again, I tell you again, to the citizens. So we need to really work on data infrastructure. This data infrastructure is very nice. It's developed by a team in Germany. And actually, the data here are open. You can go there. There is what we call the hydrology data cube for the Mediterranean scale. You can extract data. You can work with Jupyter notebooks. I was also able to basically work with the Jupyter notebook and extract the data I never basically programmed in Python. And for instance, yeah, I did this monthly map and also did the comparison between sun moisture and precipitation myself. And actually, so it's very easy. And but we should work on this. And finally, I will not probably go because probably I don't know how much time I spent, 60 minutes probably. So I have time. So this is the digital twin earth hydrology platform, but we will show also tomorrow. Actually, Jerome already mentioned that tomorrow morning we will have the launch of the hydrology cluster or water cycle cluster. I don't know what should be the name. Probably water cycle cluster, water cycle. And this is the front end, one of the front end that we have developed for basically put all the stuff that I have shown you before, the data, the modeling, people put together, and to make the results available to the people. We have 4 case studies. You have seen the first one for the drought. The second one here is for the flooding. And this is basically the same example that I've shown you before for the sea city, but we have also another example in northern Italy. And probably the 2 more interesting things are the 2 what-if scenario. The first one for flood risk assessment that you have seen also in the video. And basically this, you can go in the platform, you can see different dots. You have 2 boxes, initial sun moisture and precipitation. You can play around with the boxes. You can change the numbers, and changing these numbers, basically you get different, of course, outcomes in terms of river discharge for the different location. So the dots become red if you overcome some threshold, and basically everybody is able to understand. I show this plot also to non-experts, and actually they are happy to understand what they are seeing. And finally, what is a scenario for water resource management? Again, northern Italy, actually we are here, it's more complex because it's not only initial condition, but also seasonal forecast for precipitation and evaporation. But basically the most important plot is on the bottom, the graph, the bar, in which you can have an assessment of the future water uses, in particular if you can have some deficit of water uses for some of the different uses. And just to give you an idea, for the Po River Basin, basically we are using 20 cubic kilometers of water. In the whole Italy is 27. So basically in the Po River, actually we are using most of the water. And so basically this is really an important problem. Last slides. Thank you very much for attending. The challenges, everybody who wants to contribute to solve these challenges is welcome, because actually there is a lot of things to be done.
And if you ask me, if we are ready to build a digital twin for the water cycle, I will tell you, I will reply no. And because actually all these challenges will be carefully addressed. Thank you very much.
Thank you very much, Luca Broca. We are a little bit late, but we have time to one question. If someone wants to speak, you go to the microphone, or if we have an online question also, we can take it. So there is one question, I guess.
I thought you are leaving.
Not yet. Yes. Thank you, Luca, for a very interesting presentation. One thing, I mean, you really already said we're not ready yet for a digital twin. I think that's a nice way to say we have a lot of work to do. My question is, when you're opening up data and information to the general public, people who, have limited experience in dealing with this data, there are certain issues I think we have to take into account. So one of them is epistemic risk. It's like there's things that we do not know, and as scientists, we deal in uncertainty a lot. My question to you is, how do you see this digital twin for hydrology dealing with the aspect of making sure that the data is used appropriately or the information is used appropriately?
Well, this is actually my experience in making our job available to the people, to stakeholders, to people, for instance, people working in the flood risk. We work with civil protection a lot. We have a project with them. But actually, for instance, providing a flood forecasting system for my region, it took like 5 years or even 7 years. Once people started to use the data or the model or whatever every day, then probably they trust on the data more of you, because I use the data only, I don't know, one day per month. And but this is it's really a long story. And actually, every people using the data has his own way of looking at the data, understanding what the data are, and understanding how to use the data. It's really a complex system. And actually, the point here, I am afraid from those saying we are going to develop something on a global scale for everybody. It's kind of, I don't know, probably it will happen, I don't know, but it looks to me quite, I don't know, not a dream, but I don't know what it should be there. So a nightmare, probably, yeah, but no, I don't know. We have all different way of understanding things.
Thank you very much, Luca. So now we have to go a little bit, and so to move on to the next speaker, who is Beatriz Revilla Romero from Spain, from GMV, sorry. And the presentation is about climate resilient food management in South Sudan using Earth observation.
Yeah, thank you very much. Thank you for the organizing committee and colleagues. It's a great pleasure to be here today, actually, to have the keynote talk to present the work that we have been doing at GMB in collaboration with the World Bank and under the ESA project. So GMB, for those that don't know, is a technological group that with headquarters in Madrid. Actually started from the space, so we work at the remote sensing and geospatial analytics division. And I might confess that I'm not an Earth observation engineer. Actually comes from more than the flood forecasting, and I did my PhD at the Jersey on the global flood forecasting. But obviously there are many challenges that started when I did 11 years ago and still very relevant on how Earth observation can contribute to improve hydrological models, especially in the regions that they don't have barely any in situ data. So yeah, today work we will present, we have done under the Global Development Assistance Program from ESA. Actually, it's quite a large program, sorry. And it's a global partnership that the goal is actually to mainstream the use of Earth observation in many different topics into development operations from international institutions, international funding institutions, such as the World Bank and the Asian Development Bank and others. So within this GDA program, there are actually many thematic areas that are obviously interrelated as well. They were presented today under the climate resilience program, but at DMV we are very lucky that we actually are participating in many other clusters, such as, for example, the water resources that started this year as well. And yeah, there are many topics within that as well. So how we work? Typically at the end of these projects, there's like an engagement phase because it's quite challenging how to understand how Earth observation in different topics actually can actually support like on the other side at the banks that you may have an economist and how to explain what services and can support them into the operations in different countries. It usually takes actually more than 3 months. But once you have some basic requirements, we start working into agile way with different cycles around 6 months in order to get a prototype working and later on improve based on the feedback on the needs. So on the South Sudan use case or a small project, we're actually going to the coming now to the end of the third development cycle, so I will show some examples. But before that, obviously, South Sudan is actually the youngest country in the world. It just got the independence from Sudan in 2011, so it's a very young country. There's around 2 million population, but actually around 10 million of them, they are like so most of them, they are in need of humanitarian assistance, and around 8 million actually facing acute food insecurity. And this doesn't, I think, doesn't usually make the highlights of the news, but it's quite a dramatic situation. Obviously now with the conflict in Sudan, there's a lot of returnees and people coming back and internal displaced person that's actually there. And on top of that, then suddenly you have 4 consecutive years of devastating floods that really affected over 1 million people. And probably the actual impact is even larger. However, so this is just an example from Doctors Without Frontiers, where you have the scale of last year floods. Obviously, in the center part is like a big swamp area, but still, like the area covered, and not even that, is also the frequency and the persistence of the flood is really, really of another level. I know in Europe we have many floods, but this is just another part. And the flood here in South Sudan is not mainly driven because of the rain that actually falls in the country. It's from the rain from upstream in the Nile, for example, from the Lake Victoria and other countries. And they were like talking with the staff at the ministries there, say we have floods, we don't know where the water is coming from. We actually have no data, so we got hold of, I think, 4 very intermittent river stations that they are not even operational, and you have this level of waters, like how they can, the government, how they can take actions without not having data. So with Earth observation, I think they suddenly saw that actually you can see a lot. It might not be perfect, and still many things, you know, under development, but actually you can provide data across the country, which it was very, very welcome. Basically, when we started working with the World Bank and the Ministry of Water Resources and Irrigation, we will ask whether we could assess the extent and the occurrence of flooding. In this case, obviously funded by ESA, so using Earth observation to support some of the design and preparation of another project that the World Bank is currently doing in South Sudan. So apart of from that, we technically at GMB we started looking at using Sentinel-1 and method. We started with a basic method that is from the UN Spider on the change detection, where basically compare like 1 pixel to another before and after the flood. We use every single image that was available from Sentinel-1 from the 2015 to 2022 period. We counted the number of flooded pixels, but also as it's a very large area, there are many paths from the satellite, some with more observations than others, so we need to normalize just not to create bias where we have more observation doesn't mean that you have more floods. That was kind of like a map, a preliminary map. We did several runs of improvements of the algorithms. Then we were also asked to make like a basic flat hazard index looking at the flat area, but also the flat frequency based on the Sentinel-1 images, and make basically a category by the admin level just for the World Bank to see how which areas could be more prioritized over others. And then also we did for specific river basins, we look at the percentage of the flooded images and the consecutive months flooded based on this Sentinel-1 imagery. And that was kind of part of the first few months where we work. Then on the third development cycle, from June this year until early next year, we have been asked to focus on target areas on 5 different basins in the country, and we were asked to look at more on the seasonal behavior based on Sentinel-1. We also did some flood exposure assessment, and currently we are working on improving both the Sentinel-1 algorithms, but also using other sensors to try to improve the flood hazard assessment based on Earth observation. So this is a map for just one of the basins, the Bahr el Jebel, in central South Sudan, where you can see the 3 basically per season, so from December to February, March, April, and so on. And what you can see is changing basically year by year. So as you can see, on the March to May period, there are many areas that actually just get flooded very persistently. And we were like, yeah, the word basically tell us, basically we didn't get rid of the water that was there from the previous season, and when new water arrived and just swamp basically very large areas for a very long period, obviously affecting the population there. Then we look at the flood exposure. So we use global data set because we didn't have any national data. So we look at the built-up surface population from the World Pop and the global human settlement, and then looking at the agriculture on the crops and pastures, and also we look at the roads. So we did that for the 5 different basins as well. We compare the data set across different basins in order to give them a bit more information to prioritize, both in the, for example, for the population. Obviously, here the challenge when assessing flood exposure on the population is that actually in South Sudan, the population moved a lot due to conflict, but also due to these big floods that are happening in the last few years. So the assessment are not as the reality, but it's just a first step. We also look at the potential roads exposure on the main cities and those basins, the built-up, which is very much interrelated, and also on the crops and the grazing areas. So on the next steps, we know that obviously, like based on Earth observation, you might always have the chance that to miss the flood peak if the satellite just doesn't pass at that time. But in this case, they're really recurrent. So in the lucky, very unlucky, but that is on the lucky that you have more chances in South Sudan to actually pick the flood extent. But we know with the algorithm that we were using initially, we don't detect all the inundation, which is under or with vegetation, and also in the cases that the reference imagery used as the dry, sometimes were not dry, as we were doing like obviously like a countrywide analysis. So we decided to incorporate also beers, the 5-day product, into this, doing a bit of downscaling to kind of go a bit, because otherwise the pixel is quite large. We also been working to improve some of the Sentinel-1 pre-processing to reduce some of the noise that we could detect, and also different methodologies such as using a geomedian in order to reduce the dependency on a single reference images. Then also doing a classification based flood frequency, which we could see that it really improved the areas where it was like in the wetlands or with vegetation. And finally, we are looking into do like a combined flood hazard map. So this is just some of the examples for the same basin, the Barrel Jebel, where we're looking at the different products and see how at the end we can get, based on Earth observation, a more like informative product for the World Bank and the national counterparts. So this is a part of the GDA. This being quite a successful project. Not always is the case, because sometimes the expectations on Earth observation or how this can kind of get into the World Bank project is not always successful. But in this case, the engagement has been in both sides very rich. We got quite a lot of positive feedback, and basically you just ask for feedback just for this presentation today. And yeah, they have emphasized the value of Earth observation, especially in countries where they're very fragile, conflict and violence affected. But at the same time, they have basically no ground measurements, are very limited, high vulnerable to floods and population, and they have very limited national capacity. So I think there is a lot of Earth observation only for floods, but for other topics they can also bring to them. And yeah, looking at the outlooks, so yeah, we work, thanks to Earth observation, we could support the World Bank in some of the preparation of the development and operations. We have been using Sentinel-1, but I'm sure there will be a lot of different sensors that will be very much of use, in this case for flood hazard. The approach of Earth observation was very new for the country ministry officials, but actually it was also very much welcome. And yeah, improving ground-based observations in South Sudan or any other country is really much needed and is essential in order to improve also the Earth observation validation. Thank you very much.
Thank you very much, Beatrice. A very nice presentation. And we have time for 1 or 2 questions, if you want, please.
Yeah. So what is your prospect for doing the forecast of the flooding in a sufficient resolution so it could have an impact on the population? Like, you know, like around Bentiu, there's this refugee camp, which needs to know if the water is going down or going up in next week.
Yeah, I mean, when I was my time at the GRC, like obviously there are these big models are very imperfect. You know, they have many mistakes, but they just say, like, if you can say just few lives, even few, like still will have a value. So obviously are very complex systems, and in order to have accurate flood forecasts, it can be very challenging when you don't have observations that tell you to calibrate. But I think having at least different type of options, you know, you have Earth observation, hopefully you have some ground data and you have models. I think the ideal world, you have different type of data that complement each other. And hopefully at the end it can result into like the population get it, some news or alerts on that. Also, like previously, I work also the collaboration with the Red Cross, but they have this very interesting program just a few years ago now called forecast-based financing, and obviously Red Cross and the World Food Program and others. They're very much aware that these global models are, or data, they are very imperfect. But still, if they allow them to do some actions before, you know, an event, a drought, a flood happens, it's still very much of value. So I think it's lots coming on these topics.
Thank you. Every time I see we cannot see under the canopy, or there's a canopy and we cannot see, I remind that in 2012 in Venice, in the keynote, I finished with a slide showing the flooding in the Amazon, which was extended much beyond the Amazon, under the trees that nobody could see. Optical didn't work, star slanted was bouncing off, but with the altimeter, because it looks at nadir, we see that there's a very strong reflection, so there's water. So when you cannot see, use the altimeter. It's not a swath, it's not there all the time. But it's a good indication that there's water under the trees. Yes, please go to the microphone.
Hi, thank you. Really interesting presentation. I wonder if you've considered the potential of the much higher resolution data that can come from the commercial sector for improving your understanding of what's going on.
Within this, we usually, because it's like an ESA project, we try to use obviously like the Sentinel or other data set, but yeah, I mean, commercial with higher resolution, it will be very much of a value. Perhaps when you do like a very detailed analysis over a specific area or short-term period, obviously it has clear value. In this case, because we were coming from, we had nothing on the last year, just we know that we have or they have a lot of floods, so we went from the larger scale approach. But then I think having like a refined approach and using commercial data, yeah, will be much of a value.
Quick plug for ESA,
Yeah.
ESA's EarthNet program, because it's given me access to some high-res data, and it's a great program.
Yeah. Thank you.
Very good. Thank you very much.
Sorry, Guy. Yeah.
We have time for another question.
Next speaker is, so please, thank you very much. There is a question. No, go on. You can go.
Jérôme's point was very valid because the altimeter and the forecasting, because there are examples in the world where more regional-based forecast models are running with a simple 1D model like HACRAS and altimeter-based ingestions of water level, improving boundary conditions. So maybe we should just have a talk at coffee break, because I think that's a very valid point. And you were mentioning forecasting models. And Jérôme, the altimeter, it does work in forecasting models to update parameter sets. And
Thank you, Guy.
Yeah, no, thank you, Guy. Yeah, in fact, I think what is very interesting from the GDA program from ESA is actually is getting Earth observation, another type of data, into like operations from the World Bank. They run projects all over the, many other countries, which typically they have lack of data to support the operations. So having a different type of approaches, I think, is very much welcome. And yeah, we are actually starting probably next week another project in South Sudan with the World Bank. But we hope like over the future, like more will come where they use different type of data, which typically they don't have to support the operation. And obviously not just Earth observation, but to complement with models on other type of data. So yeah, thank you.
Let me just thank Guy. He mentioned we talked about it over coffee. I think we'll talk about it over lunch and over dinner and over coffee again. Thank you very much.
Thank you.
Thank you very much. So next talk is going to be presented to us by Benjamin Kitembo from Lagos, who is going to talk about the water storage change anomalies from satellite remote sensing. Benjamin.
So good morning, everyone. Thank you to the organizing committee for the opportunity given for a keynote presentation. So on behalf of all the cohort, I will present the work titled Towards a Global Long-Term Spatial Temporal Variation of Surface Water Storage, Anomaly from Space from 1992 to 2015. So to begin, I will talk about the rationale for surface water storage. Surface water storage is a precious resource in terms of biodiversity, ecology, water management, and economics, and is a key player in the climate system and water resource variability, as well as a key component of total water storage variability in the tropics. So therefore, these hydrological variables, the surface water storage, is an indicator of the current climate change. Additionally, this hydrological variable is needed for groundwater estimation through the decomposition of the total water storage. However, the global land surface model output doesn't yet well estimate surface water storage. An example of this is highlighted in the publication of Papa et al. That underline the underestimation of the surface water storage from model in blue as compared to the surface water storage based observation in gray. In the Amazon, in the Congo, as well as in the Grand Brahmaputra and in Mekong. So moreover, the current knowledge about the surface water storage spatial-temporal variability, it's still poor regionally and globally. So here we are presenting the ongoing effort to estimate surface water storage at the global scale from observation. These ongoing efforts led us to a scientific question. What is the spatial temporal variability of surface water storage at the global scale from space and its link to climate variability? So here we will talk more about water in floodplain and wetlands, and water in lakes is the storage in lakes is quite well known, and will not talk about it. To answer to this scientific question, a trove of observation have been used that include a global inundation extent from multi-satellite dataset called GIMS dataset. We had digital elevation model data and radar altimetry datasets. In terms of the methodology used to estimate surface water storage, we applied the hypsometric curves approach. That methodology relies on these two publications of Papa et al. In 2013 and Kitambo et al. In 2023. So the methodology consists in this. For each pixel of surface water storage, we compute the hypsometric curves from the corresponding depth value. That gives a relationship between the elevation with the surface water extent that allow us to estimate surface water storage. So for comparison purpose, in one of our publication that is here, so we used FODEM, ALOS, ASTER, FABDEM, and MERIT in ADA to see the impact of different DEM on the storage. In these slides, we show the conversion between an area elevation relationship into an area surface water storage by estimating the surface water storage using the formula below. So for the first time, we will start talking of the Congo River Basin. For the first time, we were able to estimate the temporal variability, the monthly temporal variability over 24 years. As you can see here on the map, on the figure A, that provides the row series, and the figure B provides the deseasonalized anomaly with good signal related to climate variability. On the other ends, we also provide the spatial variability of the average month of the surface water storage maximum. And from this figure, we can observe that there is an hydrological pattern in terms of time of the maximum of surface water storage, where we can observe within the cuvette centrale that the maximum of surface water storage in the northern parts occurred in September, October, while in the southern parts, it's happened in November, December. On these slides, we point out the big floods that occurred in 1988 that's actually related to the El Nino event. And this map actually illustrates this situation, the flooded situation in one of the locations in the Congo basin. And on this slide, we also show the major droughts that occur in the end of 2005 and the beginning of 2006. And this map actually illustrates the severity of the droughts on the vegetation in the Congo River Basin. So this data set actually provides us also a possibility of characterizing the spatial distribution of the highlighted droughts. So this map actually presents the spatial signature of these droughts, and we can observe that the severity of the drought is not homogeneous all over the basin. So after the satisfactory results of the estimation of surface water storage in the Congo Basin, a question raised in our minds. And the question was, what if we upscale the hypsometric curves approach to global scale? Since all the data sets used to estimate the storage in the Congo River Basin is global, then we end up by saying, let us try. So looking at the African continent, here I'm presenting you the mean surface water storage over the African continent, and we can observe that spatially this data set depicts the major wetland and floodplain that are particular ecosystem in the major African river basin. And on this side, I'm presenting the long-term monthly surface water storage over the entire continent. On figure A, it's the row series, and on figure B, it's the seasonalized anomaly of the row series. And actually, I've also plotted the ENSO index that actually shows the El Nino and the Nina events. And we can observe on this figure that our surface water storage is modulated by local and regional variability actually related to climate variability. Looking at the South American continent, we also display the spatial variability of the mean surface water storage over the South American continent, and we can observe that, again, the data sets depict very well the large floodplain and wetlands on this continent. And also for to be confident with our estimates, we realized that our estimates were in the same order of magnitude with the previous value obtained in the Amazon River Basin. And these figures, the figure A presents the temporal variation over 24 years at a monthly time scale. And the figure B is the seasonalized anomaly. As for the African continent, we present on figure B the seasonalized anomaly, where we also observed the modulation of surface water storage by local and regional variability. And the next continent where we try to estimate our surface water storage is the North America. So same, we are presenting here the the spatial variability of the mean surface water storage. On these figures, we are presenting the temporal variation over 24 years, and the figure B, same as for the two precedent figures, it's the decisionalized anomaly showing the El Nino and the Nina index. So this slide actually is talk by itself. I've presented the work actually completed like on the African, South and North American, and we are still working. There's still some work in progress. So as you can see by this signal, so very soon we'll be providing the surface water storage at the global scale for the scientific community. So in conclusion, I will say that Earth observation have allowed us to estimate surface water storage first, as I presented, in the Congo River Basin, and the data set actually is accessible freely on this repository. And as shown here, we also compute the storage in different continents. And we observe that the surface water storage is modulated either by local or regional variability, also highlighting some hydrological pattern. In perspective, we can say that this important data set will really help to deepen our understanding of the extreme events on surface water storage in conjunction with climate variability in major river basin at the global scale. As a recommendation is that this data set also can be assimilated in global or regional surface model to improve the surface water storage dynamics. There is some work going on the Congo River Basin, and we observe that we make a comparison between the storage from observation and the surface storage from model, and we see that the surface water storage from observation depict actually very well the bimodal peak, while the surface storage from the model doesn't. And also, as a recommendation is to say that, as I highlighted before, is that the surface storage is important in a sense that it can allow to derive the groundwater variation, and also it's a kind of work that is conducted in the Congo River Basin. And finally, I will say that our product that is being developing will be a benchmark product for such mission in many parts of the globe. So I end up my presentation by saying thank you to remote sensing, and thank you to you all for your attention.
Thanks a lot, Benjamin. If there are questions, of course, we have some time. I have just one. When do you plan to finish all the continents for the next release of your database?
Yeah, it's quite a tough question, Jeff. But
Sorry, Benjamin.
Okay, I think by the first semester of next year, the dataset could be available to the scientific community. At least knowing that when it will go into the process of publication, it's depend with the reviewers and the journal that will submit it.
Okay, questions? Luca?
Actually, I have 3 questions. One is spatial resolution of the data.
Okay. Sorry, I didn't mention that. Is like almost 27 kilometers. Is the resolution rated from Jim's dataset?
And the more difficult question are, first, the maps looks quite red. Let's see. The storage looks high. Did you make kind of comparison with the other data sets or with groundwater storage?
Okay.
And the test question, so I can sit down, it's if you ever make, because actually you make an assessment of the Congo against modeling, is there a way of assessing the product, of understanding what is the accuracy of the product on a global scale?
Yeah, I will start first with the first question about the redness of the maps. It's just the scale things, you know. So I can again set and the red will disappear. So they looks.
You have to speak in the mic so we can hear you.
Values. So it's not red or blue. It's simply because actually it looks like at that resolution, kilometer cube at 0.2 cubic kilometer looks very high. I don't know. It's a high value. So that's why I was wondering if you make comparison with groundwater storage data with some to understand, have a feeling on what we are looking at.
Yes, actually, so there is some graph here. There is a graph that I show here at the beginning. So like we really did, it's an ongoing work that we are doing. We are doing for the Congo River Basin. So we compared our storage to the storage from model, and what we observe is that when it comes to storage from model, it's really underestimates. And there is actually previous work that use also other sensors that compute the storage, and our results was in the same order of what has been found. So same like as I presented when I showed the results on the South American. So I didn't show it actually. I'm doing a comparison with the previous estimates from also other studies that has been done. And actually, I'm a little bit satisfactory. It's not really the same, but when we include the standard deviation, it fails into the same order of magnitude. So there is a comparison that have been done. Thank you.
Okay, thank you very much, Benjamin Kitambo, for this keynote. I think it's time for a coffee break. Hopefully we can get the 200 coffee made in less than half an hour. And so let's try to be back here in 25 minutes if it's possible. If not, we'll be 5 minutes late restarting. Enjoy the coffee break and talk to Guy about flood. Ouais, j'ai avalé des poudres de palmier. Tu as pris un café? Tu as eu un petit déjeuner?
J'ai eu un petit gâteau et un petit café.
Karim, bonjour. Hein?
L'Espagne?
Non, pas de nouvelles.
Je ne l'ai pas vu aujourd'hui.
Non, il y avait 42 fièvre, là, tu as vu les mails. Hein?
Ouais.
39 au moins. Et je n'ai pas consulté mes mails ce matin, mais...
Non, mais je vais regarder, je vais lui envoyer un mail.
Tant pis pour lui, on va faire... je vais faire le sharing de la session avec toi.
Ok, bah oui.
Tu vas faire...
On avait prévu de faire, mais normalement, c'est lui qui a prévu des slides d'introduction.
Ouais, ce serait bien qu'il nous les envoie.
Ce serait bien qu'il nous les envoie.
Que tu les présentes.
Aussi, oui.
Bah ouais, c'est toi, le futur est dans tes mains.
Ouais.
Non, moi,
Ça va pas l'air brillant.
moi, je Je prépare mes vacances, là, donc
Ok.
dernier
Sur les
act
slides
of God, là, ce workshop.
Non, non, mais je vais lui envoyer un mail là.
J'essaie de récupérer les slides pour demain matin. Et bon, il avait envie de présenter 2-3 trucs, sinon l'introduction est vite faite. Hein. C'est des contrats de l'État et on les montre. Et puis, insistons sur les futurs contrats, les appels d'offres, ça intéresse tout le monde. Et puis, l'idée, c'est de faire l'agence matrimoniale, faciliter la création de consortiums.
Oui, oui, ça, on avait prévu 2-3 slides à la fin pour engager les conversations et notamment avec elle.
OK. Espen number 2.
Voilà.
C'est toi. Okay, everybody's back in. So the next speaker is Fernando Jaramillo with a few co-authors that I will start reading now. When maybe not. Very impressive list of co-author. It must be interesting to herd all these people. You know, it's like herding cats. So we're really looking forward to your presentation on the potential of hydrogeodesy. Hydrogeodesy, it's a new word in fashion, so you have to put in your brain to address the key hydrological questions, water resources sustainability. Fernando.
Okay, thanks, Jerome. Okay, so my name is Fernando Jaramillo. I come from Stockholm University. I'm a hydrologist, but basically my focus nowadays is INSAR. So here in this image, you see an interferogram, which is the result of combining two SAR images together, and it's useful to understand how water is moving, especially in floodplains and wetlands. But actually, this is the only image from space that you will see in this presentation. So sorry about that. So basically, hydrogeodesy, it's a combination not only of INSAR, but there are also several technologies that are hydrogeodesy. So altimetry is a technology of hydrogeodesy. Gravimetry, well known for the GRACE satellites and GRACE FO. We also have all the applications of GNSS. So we were thinking, we've been thinking, and this is not the first time that the term hydrogeodesy has been used, but we thought that actually it's the science of measuring Earth's solid and aquatic surfaces from space to understand water availability and its changes. Most of us, we focus in one of these technologies or two, but sometimes we don't know what the other people are doing with the other technology. So maybe this was the idea of this study, which it started everything in 2017 in a workshop organized by EarthScope, exactly on hydrogeodesy that we had in 2017 in San Diego. And we came up, we noticed that several of us, we were working with different technologies, but we didn't know anything about what the other people were doing. And it comes out that it's basically because we ignore what the other technologies are being capable of, and also what can they be used for. So the idea of trying to gather a hydrogeodetic community and writing something together started in 2017. And in this workshop and through since 2017, we realized that there are several questions that, as a community, we basically ignore from a global perspective. And it's, I mean, how is hydrogeodesy developing in the last decades? Of course, we've seen the missions that are on space, but as a whole, we really don't know where we are pointing at with our research. Also, how often are these technologies combined? So how often is GRACE combined with altimetry or altimetry with INSAR? How is GNSS used as a support now, for instance, for the SWOT mission or for other technologies? And question number 3, what water resources are we focusing on as a community? Question number 4, and what are we doing our studies for? What is our main objective? Is it making a database, intercomparing our results, supporting modeling? So this was question number 4. And then question number 5, looking a little bit beyond what we usually do is, can we actually, like doing the same study, in the same scope of research, can we use hydrogeodesy, all these techniques, a little bit more into hydrology and water resource sustainability? So these are the questions that this study aims to answer with these authors, and I'll later say that, I mean, it's not closed. Like the other people, if other people are interested in joining in, you can just contact me. But this is based basically in a meta-analysis, which now stands more or less at 3,600 articles. And the way of trying to frame what was hydrogeodesy is like we simply, after a lot of struggles during these last months on how to structure the term, we said, okay, when an article has on its title a word of a water resource, and then when the technology of hydrogeodesy, such as GRACE or altimetry or INSAR or GNSS, stands in the title or in the abstract. So this came up to 3,600 articles. We also did an expert elicitation from the group of co-authors that each one of us know somehow one of these techniques. And then we also discussed with hydrologists and also with researchers on sustainability science on what could be the potential of hydrogeodesy. So now I'll go briefly into the results. So this is more or less like the development of hydrogeodesy. So we have that, for instance, from the early 90s, mostly with the first missions of altimetry and also with GNSS. The field has been developing quite extensively, but we see actually an exponential boom of publications. From my case, I was only interested in INSAR, but then I see that INSAR is actually the one that has the least number of studies. So then that interests me, for instance, to see what other people are doing. And also something very interesting here is actually the number of publications that are combining these technologies. So we see that down there in green. So there is an exponential increase of these studies, and actually now with the upcoming missions, SWOT that was launched recently, NISAR that will be launched soon, I'm sure this exponential increase of articles will increase in the near future. So this is a diagram showing how these technologies have been combined throughout these 300 and 600 studies. So we see, so each of these ovals represents one of these technologies, and simply where these ovals intersect, this is the number of studies that are using this technology. So we see that actually there are interesting combinations of, for instance, of GRACE and altimetry, or even we also have altimetry with GNSS, or we also have several studies that are combining INSAR with GNSS. So there is potential for collaboration and also combination of these technologies to exploit their full potential. And I must say that this is not, remember that we're just limiting ourselves to the title. So because when we use the abstract, it was just became exponential. There's many studies that use these missions for other purposes, right? And then when we see where are all our studies ending up? So we just basically divided the journal that is targeted in 4 categories: glaciology, multidisciplinary journals, remote sensing journals, and water resources journals. And this is very interesting because we find that actually gravimetry or GRACE is a technology that has permeated hydrology the most, I would say, from the number of articles that are published in water resource journals. But on the other hand, we have, for instance, altimetry or GNSS, they're still mainly published in remote sensing journals. So there's many potential reasons for that, but actually it might be like the expertise that is needed, or also the nature of the missions itself. For instance, GRACE or gravimetry is based on the core to understand changes in water resources. So, but there is definitely a large bias towards remote sensing, and even though these tools are used for water resources, they haven't still permeated completely water-related journals. And here now we see we took keywords in all these articles related to specific words of water resources, and we see the massive use of hydrogeodesy for glacier or ice surfaces. For instance, we see that glaciers, and ice are mostly used or studied by altimetry. As a surprise, at least from my perspective, GNSS studies has quite some background in soil moisture and snow, which actually I want to study, but I was trying to do that with INSAR and it was quite difficult. But I would maybe point out the circles on the right. So these are the water resources that are the least studied are actually wetlands, permafrost, and a little bit soil moisture. So there is a potential to study these resources with hydrogeodetic studies. And if we compare it with the other resources, there's really like a lag in studies. Yeah. So now, this was basically the main, okay, why are we publishing our articles? So we try to extract from the abstract the main objective of these studies. So for instance, we have several studies, as one of the presenters showed, they're used to measure flood and droughts, so hydrological extremes. But most of the studies are focused in assessing the main variable that this technology can assess. So for instance, water level, or change in water level, or the height of the ice. And that's what we call hydrovariable. Other studies are intercomparing data sets or the results from missions. Then we also have some studies that are using these technologies for management. So this is mostly INSAR, which is used to, for instance, to understand groundwater depletion by the deformation of the ground. Then we also have a general interest of trying to understand hydrological processes and geomorphological processes. And then finally, there's articles that are just interested in developing the technologies further by improving algorithms, by improving the codes that these technologies are based on, or different methods. Yeah. So we see here that it definitely depends the application of each technology really points to a different objective. But we didn't see much happening regarding sustainability or actually core hydrological questions. So this is when we decided that maybe we could do an elicitation based on the list of authors and also some people that we also asked. So we based ourselves in this study that's called the 23 Unresolved Problems in Hydrology, which was published some years ago involving many researchers. And this study came up with 23 unresolved problems of hydrology. So we asked each of the persons that were interviewed in this elicitation process, like, how would you grade from 1 to 5 the application of these technologies to answer specifically these questions? So these are just the subtitles of these questions, but you can see that obviously we use, most of hydrogeologists are interested in using these techniques for measurements, and again, the explicit definition of the hydrological variables that they can measure. But we see very interesting that the last two, there's a high increase of interest in trying to combine this with modeling and also try to do interfaces with society. So there is an interest of us as a community to try to use these techniques to understand key sustainability questions. The problem is how? Can we do this in the same study where we're using these technologies, or is it just too much to go a little bit beyond? So for instance, this is a sustainability framework that it's getting very well known maybe in the last 8 years, which is called the Planetary Boundary Framework. And this framework tries to define the limits that the Earth has based on our impact on Earth. So it actually tries to measure the threshold that define the safe operating space of humanity. And one of these are the planetary boundaries, the circle that you see there on the left. And it tells you how close are we to reaching that maximum or not. So, well, there's a lot of questions about the framework in itself, but actually one of the boundaries is the water boundary. And lately we've tried to define this boundary actually is when you try to understand how can we affect water as a system and how can that really affect our survival on Earth, well, you have to divide water in 5 components. So surface water, groundwater, frozen water, soil, moisture, and then you also have the atmospheric component of water. And hydrogeology has actually a very good potential to try to target these five of these 6 compartments with the measurements, especially now with the scales and the resolutions that we're getting with our tools. So this is just like a message to show that there is a lot of potential to go a little bit into the field of sustainability too. So in conclusions, there is a need to increase research on unexplored resources such as wetlands, permafrost, also unexplored, even though other resources are highly explored such as lakes. I mean, well, obviously, like some of these lakes are always the ones that are studied, but now with the potential of SWOT to go over into all these many other lakes, it's important. And then we also, to move a little bit into other disciplines, try to not stay so much in remote sensing, but maybe venture a little bit into sustainability science and also hydrology, and also increase our collaborations between us, between hydrogeodesists, but also with hydrologists and sustainable scientists. So just to end, so we have a special issue in water resources research that actually it's open, I think, until March next year. So if you have any studies that you still don't know where you want to aim for, so you can submit it to this special issue. And also, if you have some ideas or thoughts about this study, hey, these people forgot about this technology, or maybe I didn't see this focus, you can also send me an email. I mean, the list of authors has been growing exponentially and also embarrassingly. So we need to close the article soon, but send me an email, and of course I can send you the surveys and for your perspective. Yeah. Okay. Thank you very much.
Thank you, Fernando. You're the perfect example of the person who don't want question and uses up all the 20 minutes. So we go to the next talk.
Sorry. So next talk is going to be presented to us by Kanishka Matlik about conjugate biophysical regulation of stomata. Oh, it's complicated title, sorry. And aerodynamic conductance determine terrestrial evaporation response to land surface temperature variability. So you have 20 minutes.
Thank you, everyone, and good morning to all. Thanks to ESA for selecting this as a keynote talk. So this is all about understanding the biophysical controls of terrestrial evaporation and how such controls eventually regulate the ET responses to land surface temperature variability. So basically, it has a long legacy, which started back in 1981 with the seminal work of John Monteith, who first postulated the theory between evaporation and surface temperature. And this particular graph, it is taken from Monteith's paper. So this shows 2 very contrasting response of latent heat flux or evaporation when it's plotted against temperature. So one line shows an exponential increase in evaporation with increasing temperature and vapor pressure gradient. And this is a condition which is very ideal for the plants, because this is the condition which we call as the energy limited condition, but there is unlimited water supply. So as a result, the plants can transpire happily. And at the same time, the conductances, which are the main regulator of transpiration, they also increase proportionally with increasing temperature and vapor pressure gradient. On the other side, the solid line that shows that evaporation decreases with increasing surface temperature. And this is the line which is the condition of water limited ecosystem and when the surface is having maximum biophysical regulation. And this kind of condition we normally see under either bare soil or during sparse vegetation. And what happens is during this time, the entire net available energy that is available to us, and that plants, they convert that net available energy into sensible heating. So it leaves very little amount of energy to go into the latent heating or for the transpiration by the plants. But these are the two extreme cases, as you can see from the picture. In the real world, the plants are operating in between two extreme limits, and therefore all the interactions are happening from this crossover point. Now, what do we need for any ecosystems to evaporate? So if you see this is a very simplified diagram. So the two most important things that we need, or that the plants need to evaporate, one is the supply of energy, which is the engine. So think about a car, if it like an engine, but the most important part is in order to drive that engine, that is we need the fuel, and that fuel is the water stress or the water availability. So here land surface temperature is a signature of the variability of the water. So depending on the net available energy and the availability of water, the energy that is receiving on the surface, that is partitioned into sensible and latent fixed. So from this particular equation of energy balance, you can see that there is a physical connection between latent heat and land surface temperature. However, the connection is not linear because each and every variable is changing, and as a result, there is a co-evolution pattern. For example, if the surface is wet, there is evaporative cooling, and then latent heating is happening, and at the same time, the upwelling long wave radiation is also changing. So there is also a kind of co-evolution. And on the other side, depending on this co-evolution and depending on the water stress of the surface, there is a biophysical regulation. So as a result, there is always a kind of, this is not one-way problem, it's a kind of feedback and interaction approach. And so for rest part of the talk, I'm going to say that how do we see the interaction between LST and evaporation in energy and water limited condition from the observational perspective? Then how do the surface energy balance is coming, and how the equations of conductances are regulating in thermal remote sensing of ET, and what are the perplexities? And then how can we understand from the first principle and then include them to model evaporation at the spatial scale? So this is an observational evidence of LST and evaporation interaction. So this is a alfalfa in the Mediterranean ecosystems of California, which receives 400 to 500 millimeters of annual precipitation. So as we all know from thermal remote sensing community, that Mediterranean ecosystems are the most complex ecosystems where the dynamical changes in hydrological regime, it makes evaporation extremely difficult for the plants to maintain their metabolism and evaporation. So this plot clearly shows that evaporation increases with increasing LST under non-restricted water condition, but at certain point, it becomes asymptotic. And there are conditions which are the restricted conditions where latent heat flux reduces with increasing both LST and net available energy. So the figure in the inset, to have a better handle on this situation and understand, the figures in the inset, we plotted LST and the same plot, but for different times of the day. And if you see this, it is very much clear that evaporation increases with LST until 12 o'clock afternoon hours, and then there is a very strong stomatal control, and then even if LST is increasing and net available energy is increasing, still the evapotranspiration is decreasing with increasing these variables. To get another overview, what we plotted is, we plotted this evaporation with long wave radiation, because that is also an indicator of surface drying. It is more pure observation that we can observe from the piezometer. And we plotted it as a third vector. We plotted it against the vapor pressure deficit, because we all know that the atmospheric aridity or atmospheric drying, it's a signature which is carrying by the vapor pressure deficit. And this gave us the confidence that evaporation increases with increasing surface drying under the humidity control situation, whereas evaporation decreases with increasing surface drying under the aridity controlled environment. And then when we plotted exactly the similar plot for another oak savanna, which is Tonzi Ranch, and which is enormously dry, which is having tremendous control of vapor pressure deficit and soil moisture stress, it is clear that firstly, one of the first impressive features is, despite being situated in the similar climate, its latent heat is 1/4 of what we saw in alfalfa. And here, there are only limited time of the day in the morning. We can see that ET is increasing with increasing LST, maybe during in the morning around 8 o'clock or 9 o'clock. But from the figure in the inset, we could clearly observe that after 10 o'clock or 11 o'clock, the stomata is almost shutting down or in a very restricted manner. As a result, there is no increase in latent heat flux, and it is decreasing with increasing LST and net available energy. And the other figure with the long wave radiation and vapor pressure deficit, it also shows that there is a humidity control line and there is an aridity control line. So in the humidity control environment, evaporation increases with increasing long wave radiation or LST, but it decreases the moment the control shifts over to high aridity. Now the question is how the role of conductances we see. This is a very simple cartoon diagram. In the right side, we can measure all these components in a compound form through eddy covariance observation. But when it comes to predicting or mapping evaporation from satellite measurements, so we need to use the theory of energy balance. And the energy balance works like the analogy of Ohm's law, that the final the current that flows, it depends on the potential gradient and the resistance. And here the conductance is the reciprocal of the resistances. So here we can see that there are many different conductance or resistance components, but we can lump them into a unified one, which is we called aerodynamic conductance, and another we called canopies, soil substrate conductance. But the most important part is there are many biotic and abiotic processes that is interacting in this interface, and there are many scaling effects. And we do not know what these conductances are. So if we use simple empirical parameterization, we might have to be very careful. But by using all these equations and putting them in algebraic form, we can see that this GA, GS, and T0, we call it trinity in ET modeling. And from here, the famous Penman-Monteith equation has been originated. And we can clearly see that all these three variables, they cannot operate independently. There is always a feedback. So only one thing that is independent in the land atmosphere system, that is net available energy. So what Monteith did is, Monteith was very clever. He eliminated the need of surface temperature, but he gave us clear indication that if we have the surface temperature, and if we are able to express these conductances in terms of surface temperature, we should be able to solve them nicely. So this is in the right side, this is the form of Penman-Monteith equation. And here, these two conductance ratios are playing the main role in ET behavior across different ecosystems. For example, what happens in water stress condition? When there is extremely soil water stress, of course, plants cannot transpire, and since not enough water can go into the atmospheric boundary layer, it increases the vapor pressure deficit of the air. And that apparently reduces the conductance ratio, and since the conductance ratio decreases, it reduces the total latent heat flux, it increases the sensible heat flux, it increases the land surface temperature, which apparently again feeding back into increasing the vapor pressure deficit and reducing the stomatal and aerodynamic conductance ratio. So that means under the water stress condition, this ratio is very much approaching zero. On the other side, when the plants are happily transpiring, when there is no water stress, so then during that time, this ratio is approaching 1. So therefore, we can anticipate that if we have these conductance ratios from eddy covariance tower, and if we have evaporation from eddy covariance tower, we should be able to see how this interaction and feedback mechanism is working. So here is the graph again for the alfalfa. It's a biophysical interaction. Again, this is the observational evidence. And when we plotted evaporation in y-axis and vapor pressure deficit in the x-axis for a range of this ratio, which shows like when very strong biophysical control, when this ratio is 0, to very weak biophysical control, that means wet condition, when it is approaching 1. So here also we have seen that under the humidity control environment, evaporation increases with increasing vapor pressure deficit. But after a certain point, it reaches to an asymptotic limit. And these are the points where there is a very strong control by the plants, because they do not want to lose water, because there is not enough water available for them to transpire. And there are some cases where these red dots, there is the rate of change of evaporation is very little depending on the water stress condition and depending on the vapor pressure deficit condition. So it increases, and after a certain point, then it starts reducing. Now the question is, where is the role of land surface temperature here? So when we plotted the same ratio for the entire range of land surface temperature and vapor pressure deficit, we could clearly see that there is a very strong connection between vapor pressure deficit and land surface temperature, that this conductance ratio increases with surface temperature under the humidity control condition, but afterwards it decreases with increasing surface temperature, because then the gear of the plant, it shifts to more towards aridity. And the figures in the inset, it shows that during which hour of the day it's happening. This is mainly happening, this increase is happening in the morning between 8 o'clock until 11 or 12 o'clock, depending on the type of ecosystems, and after which plants are losing water in a very conservative manner. And exactly the similar thing we found when we plotted this result with over Tonzi Ranch. And very interestingly, the total evaporation is 1/4 of what we found in alfalfa. And another striking feature is here, this conductance ratio is 10 times less, or the biophysical control is 10 times stronger than what we found in agricultural crops. But here, exactly the same behavior. The only thing is stomata starts shutting down even after 10 o'clock, or plants start losing water more conservatively after 10 o'clock, because these ecosystems are kind of perpetually water stressed. So now the question is, how can we transfer this, what I have shown now, how can we transfer this theory for estimating satellite ET? The most important part is, if you see this particular diagram, this diagram is from a famous paper of Shuttleworth and Wallace in 1985. I have just redrawn it. But the most important part, what we can observe from satellite, these are given under the green light. So these are the variables we can observe: land surface temperature, we have emissivity, we have albedo, we have vegetation index, and from geostationary satellite, we can have shortwave radiation. And then we can, it's a very common practice, we take air temperature and humidity from the ECMWF variables. But there are some state variables, and these are the trinity, which we cannot measure. So either we assume that we use the right parameterization, or we try to retrieve them from the observed variables. So here what we did is, we have formulated some state equations, and the state equations are formulated with respect to those variables which we can observe. And then we tried to find an analytical solution of these state equations. So when we find analytical solution of these state equations, we still have some more unknowns, and to use those unknowns, we have used numerical iteration. The characteristic feature of such kind of approach, this is called surface temperature initiated closure. The characteristic feature of such modeling approach is, we do not need to parameterize any roughness length, any aerodynamic conductance, and any stomatal conductance, but using the satellite observations of surface temperature, vegetation variables, and environmental variables, we can physically retrieve them and putting them back into Penman-Monty to get evaporation. So the most important thing is, how can we evaluate? So one of the best test bed was, again, I found out that in this Californian ecosystem, they are Mediterranean. There is a strong coalition happening, because high radiative load in conjunction with high soil water stress and atmospheric vapor pressure deficit, it throws the right challenges of the plant to impose the biophysical control. So it can give a good test bed for the models, or throw the right challenge to the models to check whether it is capturing that kind of biophysical signature appropriately or not. So here I have used Landsat 8 and 9 LST along with the vegetation variables from Sentinel-2, and plus the meteorological variables I have taken from the flux tower data. The main reason first is to check how is the stability of the models. Normally, I do not like to show immediately one-to-one validation. So I would explain the figures in the left-hand side. This is the temporal diagram or the temporal dynamics of tower-based evaporation, and the black dots are the retrievals from the Landsat. What is the most interesting feature that we found out, that the model is capable of capturing the dry down and green up phase, because in this Californian ecosystem, this is for the agriculture, and alfalfa, it is having multiple growing cycles. So it is cut in every 3 months, and again, it regrows. So one of the challenge for these models is whether it is able to capture this very short growing cycle or not. So this could capture the green up and the dry down phase, and on the other side, corn, which is a very unique growth cycle, it is also able to capture the dry down and the green up phase. And next is, again, the hardest challenge was to get them understand how the model is behaving in woody savanna and grassland, because this is where the power of thermal remote sensing is coming. And here also we have found out in both the dry down and green up phase, the model is behaving pretty well, but still we can see there are some more scatters, because the magnitude of latent heat flux is so low that it's very difficult for the models to capture, even if we are using the 100% theoretical approaches. The next question is that it's not only how good or how bad the model is, the most important thing is what controls the structure of the model. So in micrometeorology, we know that there is a long-standing challenge of surface energy balance closure, and this is because we measure ground heat flux at a very small footprint. On the other side, we have sensible latent heat and net radiation at a larger footprint. So as a result, the surface energy balance is never closed, or it's very difficult to close. So I am not a micrometeorologist. I'm working with with micrometeorologists who are working. So here we used, and we have seen that in the y-axis we plotted the model versus observation, and we plotted against energy balance closure, and we have seen there is a strong significant relationship with energy balance closure, specifically when there is a overestimation tendency by the model when the energy imbalance in the flux tower is very high, and that tendency is diminishing. More and more we are going towards closed energy balance, and these are the situations when latent heat flux is high. That means there is a full fractional vegetation cover and the bare soil proportion is relatively low. And to understand this more, what is the effect of fractional vegetation cover, the same plot again shows that when the fractional vegetation cover is low, so that means there is the proportion of energy unclosure is very high. There is a strong overestimation tendency, but on the other side, more and more we are going to the homogeneous vegetation condition with high fractional vegetation cover. That overestimation tendency is reducing. But by correcting for the surface energy balance, we can fix this error, and this is what we are working on that. The next part is what are the effects of soil and atmospheric water stress and how the fractional vegetation cover is playing a role in that. So here we plotted our error with LST in the x-axis, and in the y-axis we have plotted against the color coding is done according to the vapor pressure deficit. And what we found is the errors are very random, so there is no systematic error. So this is a good news for this kind of model, that if we are able to, so that means nearly all the errors are happening because we are using the unclosed surface energy balance, but there is no systematic error we are seeing for the whole range of soil and atmospheric water deficit. And further, when we plotted against the vegetation fraction, the error versus land surface temperature, and with vegetation fraction, we have also seen that it doesn't matter what is the vegetation fraction, that the errors are uniformly distributed between -150 to +150 watts per meter square. So this is the good news for this kind of modeling exercise. So this is my last result slide. The last thing is, when I started, I had shown some of the interaction. The question is the model capable of predicting this kind of theoretical interaction? So first I tested for these, for the Landsat data that I used during the evaluation. Again, I took them and plotted evaporation versus long wave radiation as I had shown in the beginning with the observational data. And in the inset, for the same data points, evaporation versus long wave radiation for the observation for the entire range of atmospheric aridity. So what we can see is this kind of modeling exercise is capable of capturing this kind of interaction. Still, there are some discrepancies, and we anticipate that this kind of discrepancy, what we see in the data points within the black circle, this could be due to the unclosed energy balance. And the second, the right-hand side, the similar kind of plot, but for the conductance ratio and LST. So it is also following exactly the same pattern as we saw for evapotranspiration. So here, where I started, we could clearly see that the regulation of biophysical conductance, this determines the terrestrial evaporation responses to surface temperature variability, because we wanted to validate also aerodynamic conductance and stomatal conductance. And what we have seen that aerodynamic conductance, it is very difficult to validate, because from the tower we use friction velocity, wind velocity, leaf area index, and plus on the other side what we could see is somehow it got some compensation that our stomatal conductance or the canopy conductance validation, it was kind of more or less, it performed more or less well. So here I would like to finish off that the outlook and recommendation. First of all, it's better to compete with science instead of competing between the models. And the most important part is we should verify the theoretical interaction and feedback in LSTT science. After that, we can go for model validation. And one of the missing link is emphasis on stomatal conductance. And we have seen that the stomatal sensitivity is very strong, especially we go into the water stressed ecosystem, and this can be taken care for the future thermal remote sensing mission. However, this kind of concept we have introduced in our European Eco-Stress Hub, which we are running phase 2. And if you are interested to understand what are the sensitivity and how this kind of model perform with eco-stress, I would like to request you to attend the speech of my colleague Tian Hu on 30th November in Auditorium 1. So this is what I would like to thank everyone, and we have 18 months of postdoc opportunity that will be opened up in Luxembourg Institute of Science and Technology in 2 or 3 months. So please spread this information to anyone who is interested to work in this kind of approach. Thank you. Thank you.
Thank you very much. So I think you are the second one who decided to take his 20 minutes talk. So we are moving to the next one, which is who is it's you okay, Cédric David, who is going from GPL, who is going to talk to us about the SWOT mission. Cédric. So please, Cédric, 20 minutes, 15 if you can, plus 5-minute question.
Yeah, and thanks for standing in at the last minute for Parag Vazit, who unfortunately could not make it today. So thanks, David. Thanks, Cédric.
That's right. Thank you, Jerome. So yes, Parag sends his regrets. He's not able to join today, and instead he sends me, which means I'm Parag's regrets. So I'm Cédric David. I'm going to be talking to you about an update on the surface water and ocean topography mission. Of course, I'd like to acknowledge Parag, and who's the project manager on the US side for the SWOT mission, and Temlin Pavelski, who's the hydrology lead for the mission on the US side as well. So listen, I'm standing here, but all of the good slides are theirs and the bad slides are mine. There are also tons of really excellent experts on the SWOT mission who would be at least equally suited to give this presentation today. And there is a whole session on Wednesday morning focusing on the SWOT mission. So if you'll get a lot more quality information then. So this is the outline for the presentation today. I'd like to start with a brief timeline for the SWOT mission, then show you some early science images, some of which we've never shown publicly. So consider yourself lucky. And I'll talk about implications for hydrology and for water intelligence before moving on to the mandatory outlook and recommendations slide. So as we celebrate the ongoing success of the mission, we have to acknowledge the 30-year legacy of altimetry on a series of native altimetry missions, which were collaborations primarily between the French Space Agency and the American Space Agency, going back all the way to Topex Poseidon in 1992. But we also have to acknowledge the legacy of the shuttle radar topography mission, which made a measurement of land topography using a technology that is similar to what's being used for SWOT today for water topography. And in addition to the 30-year legacy of altimetry, there's about 20 years of development that went into the SWOT mission. So the mission launched in 2022, but the first concept for SWOT was called the Wide Swath Altimeter, and it was presented in 2003, at a time that I didn't speak English. It's been a while. And the concept is similar to what's being used today for SWOT, although the design has evolved a little bit. So many of you will already be aware of some of the priorities for the SWOT mission. There are primarily two stories, an ocean story and a hydrology story. There is, of course, a story at the coast as well. For the oceans, it's about characterizing the sub-mesoscale circulation of the ocean. And for hydrology, it's about measuring stores and fluxes. And there are changes through time at scales ranging from sub-monthly to seasonal to annual timescales. I wanted to show you a few pictures before and during launch. So we launched on December 16th of 2022. On the left, I don't know if I can use that. Yeah. So on the left here is the satellite folded up origami style. In the fairing, we had a brand new fairing from SpaceX for the launch, although the rocket had actually been used already 5 or 6 times before, but the fairing was brand new. So you see the launch here in the middle, and then the deployment of the solar arrays on the top right, and of the carrying antenna in the bottom. The next slide, I have a little bit of an animation of what I meant by the origami of the satellite. So of course you need to fold it to make it fit in the fairing. And then when you get into space, you have to unfold that whole thing. What's pretty impressive with the way that's being done is that they use space pyrotechnics. So it's outer Earth fireworks here to trigger the springs that actually open up the big antennas before they can be deployed in a super stable way. So a lot of engineering advancements allowed the deployment of of the satellite here. So some summary on the current state of the mission planning. So we launched on the 16th of December, and after 7 days of a successful yet stressful launch and early orbit phase, there was about 90 days of checkout and commissioning, followed by another 90 days of calibration validation with an orbit that is slightly different from the science orbit, with less spatial coverage, but a daily revisit. And so that started on April 5th, all the way up to July 21st, when the science orbit really started. So that's the official start of the science mission, which is planned for 3 years and hopefully many more. So bottom line is SWOT is functioning well. It's meeting, if not exceeding, its requirements, and it has some exciting initial results, some of which I'll show today. Of course, many of you will be excited about the public release of data. So am I. We're hoping for a public release end of December or early January for some of the data sets reprocessed all the way until the beginning of the calibration validation phase, and of course, all of the science mission. Those will be pre-validation, and you should expect better products in the spring of 2024. Of course, we have to acknowledge that it takes a village to make a satellite, so a handful of pictures over here, but really hundreds of scientists and engineers who have worked on the development of the mission over the past 20 years. All right, you guys want to see some images? Okay. And I know this is perhaps less of an oceanography crowd, but I'll start with a couple of images of the ocean because SWOT is also a revolution for the ocean. So what we're looking at here is the first global map of sea surface height anomaly. So this is the difference from the mean. And what you're seeing is little mountains in red and valleys in blue, about plus or minus 35 centimeters over the world, and places where you have high gradients in topography is where you would have high currents. So when you take the first derivative of the elevation, you get the currents. And so if we zoom in now on the eastern part of northern North America, so we're now looking at the first spatial gradients of elevation that gives us ocean currents. And so what you're looking at here is about 21 days worth of jet stream. Yes. Yes, absolutely. These have been reviewed and approved for public release. Have fun. Yeah. And so what's really incredible is that the oceanography community was already hoping to take the first derivative, the spatial gradients, and that's pretty great for currents. But it turns out the instrument is good enough that you can start taking second derivatives, and that gives you vorticity, which is the vertical mixing of the ocean. And that's a very important part of understanding how the oceans have been eating up the increased heat from rising temperature on our planet. Okay, so now I have about 6 or 7 slides on hydrology observations of SWOT, and we're going to start at the smallest scales possible with what we call the pixel cloud. So this is a map of a handful of pixels, and if there's a pixel, that means water was detected, and the color of the pixel varies as a function of the intensity of the return signal. And what we're looking at here is the United States' biggest swimming pool on the bottom left, which holds about 3,000 people. It's the 7th biggest swimming pool in the world, and next to a couple of man-made reservoirs. So what this suggests is that although we do have a couple of pixels that are outside of the water body, the geolocation errors here are on the order of 100 meters, which is really not bad at all. So we're able to capture swimming pool size water bodies, which is nuts. Still staying with the pixel cloud, we're now looking at the confluence between the Ganges, Brahmaputra, and Meghna rivers in South Asia. So we're still looking at the pixel cloud. The color map is the intensity of the return signal. And so if it's bluer, it's brighter. And if it's whiter, it's less so. So now the objective of the mission is that the signal was to bounce on water and less so on land. Turns out that water detection is hard, and that's partly why it takes a little bit of time to release the data products. But so we get some bright signals at the center of the two swath at nadir, and but you can also detect water in some of the confluences of these rivers. And of course, this is a major river in South Asia, which is guaranteed to flood every year. The question is when and how much. This is the first picture of river topography that I saw. What we're looking at here is the Yukon Delta in Alaska, water flowing from the right of the picture to the top left, and you're seeing a gradient in elevation, which seems to confirm that water is flowing from upstream to downstream. So it took us a satellite to demonstrate that. Another topography, river topography map, but here looking at the rasters, 100-meter rasters, focusing on the outlet of the Nile River flowing through Cairo, and again, flowing from upstream to downstream, which is reassuring, but we're starting to be able to observe spatial gradients in a way that we've never seen before for water elevation. We're now looking at Lake Mead, which is just above the Hoover Dam. This is the largest reservoir in the United States. You're able to start capturing some gradients in surface water through the 100-meter raster here, but there are places in which upstream is lower than downstream, and that's because there are still ongoing corrections of what we call crossover calibration, but what you'll hear about on Wednesday suggests that we're doing a lot better now. And then the last image I wanted to show is here, the Grand Ethiopian Renaissance Dam. This is about to be the biggest hydropower reservoir in Africa. It's been under construction since 2011, but they've only been filling it up for the past 4 years, since 2020. And of course, they fill it up over time, because if they were to fill it up at once, it would basically kill the Nile River. So they do it every summer, and this year, over 3 weeks, that you're seeing going from August 1st, 3 weeks later to August 22nd, and then 3 weeks later to September 18th, what you're seeing is the growth of the reservoir, which went up about 30 meters this year, and it's currently about 150 meters higher than the river level when the dam was built. All right, so let's talk about implications for hydrology. The first thing that I'm particularly excited about, that's what will allow us to revisit, is some of the most fundamental aspects of water storage and fluxes around the planet. The picture on the top left is extracted from one of my favorite papers. It was published in Science in 2006, and the story that it tells us is that surface water is cool, but it has tiny storage and mighty flow, and both of which are cause for concern. Tiny storage is because we need water for sustainability, and mighty flow is a concern for flooding, of course. Now, it turns out that the big numbers for how much water flows from land to the ocean, how much water is stored on land, those numbers haven't really evolved since the late 70s as part of the United Nations International Hydrological Decade, which is at the bottom. And basically the numbers we've been using for the past 4 decades have been the same. And they're based on literature that goes back to the 1870s. So there's a lot that we can learn on the global water cycle, particularly the surface water component with SWAT. I'll show you a couple of examples. One of them is to some extent related to the presentation that you saw earlier today, thinking about the, so we're looking at here the variability in surface area of natural lakes and man-made reservoirs around the world. Those in blue are lakes, those in red are reservoirs, and the variability, although on a global aggregate, which is the time series on the top right, there's not a whole lot of variability on a global aggregate. But when you look at the bar charts on the bottom right, which shows a % variability as a function of growing area, nominal area, what you're seeing is that the variability of the smallest water bodies is much greater than the variability of the largest water bodies. So being able to observe at fine spatial resolution will allow us to get a glimpse of that spatial variability, particularly for the smaller water bodies. Turns out that SWAT will also tell us, despite having a 21-day repeat, we may very well learn a whole lot about the speed of propagation of flood waves. And that's really important for emergency management and for flood forecasting. And the reason why we think that that is the case is that the storage variability in Earth's rivers, which you can see some time series over 30 years of global river storage variability. here on the image. So the mean and the variability of global river storage is directly related to not only how much water comes from precip, but also how fast water moves. So it turns out that when you have shorter propagation time, you have a smaller amplitude and smaller storage in Earth's rivers. And at this point, we really don't know if a flood wave travels 30 kilometers in a day or 120 kilometers in a day. And if you see something and you want to let people downstream know that it's coming, knowing that velocity of the flow wave is absolutely critical to give a heads up to people and hopefully more time for evacuation as well. Now, we expect SWOT to be a revolution for global surface water modeling as well. On the top left is in situ observations, which of course are absolutely critical. And they're great because they're continuous in time when you have access to them. But they're very sparse in space. And what satellite observations, SWOT included, but also many other missions, really what satellite observations give us is the continuous in space, but sparse in time. So it's a completely different perspective, trading space for time in the observations. And we're guaranteed to learn a whole lot about some of the weaknesses of our computer models when we look at both perspectives at once. All right, so before moving on to the outlook and recommendations, I want to acknowledge a couple of things. First of all, it's more and more of us on this planet. It's now 8 billion people. That's 8 times more than 200 years ago. And the United Nations tells us that access to to water, safe access to fresh water for drinking and sanitation is a human right. And so if we want to guarantee that for everybody, acknowledging that water crosses borders. Also, if you're upstream, you get first dibs. If you're downstream, you get what's left over. There's a lot of work to be done to help with global sustainability. And so here we are. I mean, we're seeing throughout the variety of spacecrafts we have out there that there is depletion of many of the world's water resources throughout the water cycle. That leaves us with a very tiny component that happens to be the most renewable, which may perhaps help a little bit with sustainability. And in order to do that, we have to continue advancing remote sensing capabilities, both for spatial sampling. We talked about the variability of reservoirs and lakes in space, but also advancing capabilities in time, because a lot of these water bodies vary really quickly, much finer than on a 10 or 5 or 21 day basis. And then foster the use of remote sensing and in situ observations, very important, together with models. And I'll stop here. Thanks.
Yeah. Any questions? Burning questions, because you'll have the opportunity to ask many questions in the SWOT session on Wednesday morning. A burning question from Guy. Come to the microphone.
Very provocative one, since we have JPL, NASA, and ESA here. You said it took 20 years for the mission planning. So what about after SWOT? So let's say SWOT is really, I think it's fantastic. Let's say it meets expectations. It keeps on doing that and keeps on going like 5 years, 7 years, hopefully, fingers crossed. What will be the non-experimental mission? What will be a follow-on? Will there be ever something like an operational SWOT? If successful, what will happen?
And the European Commission is concerned by your question.
Yes, please.
Listen, Guy, this is such an excellent question. I think to some extent it's for all of us to answer that question. Perhaps we can take a moment this week. Did you want to make a comment?
I can partly answer that question. I'm Remco Schoro from EUMETSAT, and I'm one of the 2 MAG chairs, the Mission Advisory Group for Sentinel-3 Next Generation. Sentinel-3 Next Generation is very, very likely, although that still needs to be discussed in April, going to have a SWOT altimeter on board.
Perfect.
And that means that by around 2033 and 2035, so keep your hopes down a little bit, We will have 2 Sentinel-3 satellites with this capability. It will be different, but it will be a source altimeter.
This is really nice, much more than I was hoping for. So,
And of course, it's going to be a joint EUMETSAT, ESA, and probably some other partners mission.
thank you.
Yeah, that's great to know. And let me add a little something. So, as we're thinking about the future, we have to think about both space and time. And I think there's a lot of effort to be put into defining measurement requirements for specific science and societal benefits that we have to work on together to be able to leverage not only what we have, but think about what we should have in the future. Thanks, Guy.
I may add that, since, well, first I want to add that between 2003 and 2010 something, we had a proposal as an explorer to the European Space Agency called WATER, WA, then capital T, the ER. And it was supposed to be an explorer like GOES, a big explorer. We have small explorers and big explorers, 400 million euros. And it was SWOT, basically. It was WSOA. And I think another one was called Hydrosphere Mapper in between. And so it's a long story, A lot of people with gray hair have been involved since the beginning. And water was studied by ESA very quickly. We had done a study before that to do an interferometer, just a study. And in fact, 400 million. But we did back of the envelope calculation, and it was probably twice or 2.5 that much that we had to invest. And we didn't know how to do this boom that SRTM did and so on. Then to answer your question, I think SWOT is the TOPEX Poseidon of altimetry. I mean, after TOPEX, you could not do any other type of altimetry than high precision altimetry. In the future, I don't think we can do any other altimetry than interferometric altimetry. We demonstrated with cryosat. Then, so it has an antenna with just 1 meter separation, 2 antennas, and it's not an array antenna. It doesn't make an image, but you can do swath if there's a slope. And then we're going Sentinel-3 next generation. We have also Crystal, which has 2 antennas. Anything that has 2 antennas, you can play with in terms of interferometry one way or another. And so the future, Guy, is that I don't think any space agency could think of doing an altimetry mission without being an interferometry mission in the future. I mean, SWOT demonstrated, and the picture we just saw, and we had some released earlier, shown by Sophie Le Gag from CNES. You can not even think of a future without interferometry altimetry. And then, so many, one more question, burning, that cannot wait until Wednesday. Go ahead.
Thanks for the presentation. The images and all look impressive, but as part of the release, will also validation data be provided where you look at the confusion matrix in terms of surface maps, where you have misdetections and false alarms, as well as altimeter-based surface height compared with actual observations that be valuable.
You're saying there would be value in having maps of surface elevation and water extent at the same time?
No, I mean validated maps by having a confusion matrix which shows misdetections and false alarms as compared to observations that you have with the SWOT retrievals. Images look impressive, but real value is in the validation.
Listen, absolutely. So this is a first taste, and I encourage you to get excited about what you'll see on Wednesday, because a lot of the validation efforts will be presented then.
That's a very good transition to lunch.
Yeah.
Wednesday is SWOT mission. And Jean-François would like to say a few things. I just would like to say.
Okay. So just first of all, thanks to all the speakers that has presented to us this morning. And now I will ask all of you to stay in the room because we have a last presentation which was not planned and not written in the program. And I ask also Jérôme to sit down here, please. So, Jérôme, it's of course impossible to display in a couple of minutes a whole career and a professional life devoted to the Earth observation, but we will try to show you our gratitude and how much we owe you. So your heritage is enormous. It is, you are a very enthusiastic colleague, always pushing us, always pushing the students, the young researchers, and you are an inspiring person. I think everyone can testify that. Your role is to encourage and to support the science community. You have done that so well. And to, in order to handle the remote sensing technique in oceanography and hydrology. And it was very tremendous work, and we also can all testify that. Jérôme helped us, all of us, to navigate within the very complicated arcane of the space agencies, especially ESA. And doing so, it contributes to build a community of users, a community of scientists involved in that. But not only space agency, also we need to build bridges with the space industry, with the international organizations, with the research sectors, with the users. And you contribute and did not count your effort to achieve this very, very important challenge. And also I can say, and I think everyone can say also, that you succeed to do it. We can again say that we are all grateful to you, Jérôme, for that. And in French, we have a word, which, or not a word, an expression, which is passeur de savoir. I tried to translate in English. I don't know how to translate in English, so I found that on Google Translate, which is a knowledge broker. So now we have some slides just to summarize your career. So Jérôme has done his PhD degrees in oceanography from space from the University of Toulouse. At that time, the laboratory was called the GRGS, if I remember well, where you started. After a postdoc in space data assimilation in ocean model at MIT, quite great, Jérôme moved to the European Space Agency, quite great too. He has been the ESA, so maybe, I don't know if there is on that, if we can have, no, we don't have the sound, sorry. So he has been the ESA Earth Observing Data Center, so he came to the ESA Earth Observing Data Center near Rome in Frascati since 1992, where he was in charge of all the altimetry constellation that we all know from ESA, the ERS-1, ERS-2, Envisat, Cryosat, 1, 2, Sentinel-3, A, B, C, Sentinel-6, radar altimetry. So we recognize, you recognize all of you as a senior advisor at ESA. So we were recognized, but we also recognize you as a senior advisor in our discipline. So also, Jérôme has launched and monitored a very important climate change initiative for sea level, for coastal, for so many things. And it is a very, very excellent program that gathers all European teams in the survey of the climate through the essential climate variable. You were also editor of many books. Some are shown here. You developed the coastal altimetry group. You set up the coastal altimetry group in hydrology, the mean sea level, etc., etc. It's really tremendous. So before that, which will be presented by Marco, I also invite Angelica to say some words to you.
We met in 2012 because he was my poster neighbor, and he introduced me in the altimetry world. From there, I found him again and again at many conferences, and because I was often alone, I spent many time with him, listening and learning. I learned a lot from him, not only work stuff, but the approach to life, the way of dealing with other scientists, the generosity, the importance of sharing, and most of all, the importance to help and support young scientists. He was always so interested in the students, in the young colleagues, in the small more than the big. And if I can learn anything from anyone, it is definitely from him. So I think I can speak for many other colleagues here when I say that I don't know a younger mind than this one, than your active, proactive, hungry of knowledge, logical and rational. For us, you have been a mentor, a source of knowledge, always willing to help everyone. And the ultimate problem solver and sometimes also a psychologist, at least for me. So I thank you very, very much for all you have done for me, and I'm sure for many other young scientists. And it will be a big loss for ESA, but we know you will be around. So I hope to see you again, continue to be for us what you always were, a big source of inspiration and a very, very special person.
So I totally agree with Angelica. And before continuing commenting the slides, let me say something to you, Jerome, because we have been working together for 8 years. And since the very first time, the interview I had with you, I felt honored to have the chance there. And then in all these years, it was truly an honor to work with you on so many activities. I was working in a pretty different field, ending a PhD on Mars exploration. So you brought me literally to a different planet. We had a lot of water on the surface, and I was started becoming involved in all these activities, oceanography, coastal altimetry, inland water altimetry, hydrology, and also this AVL, this cloud computing facility. So I can say I saw with you altimetry from 360 degrees, no? From the very beginning up to the exploitation of data in CCI projects. I totally agree with Angelica when she says that you have been for us a mentor, not only a boss, a chief, a manager, okay? But the way you allowed us to shape contracts, to give us our suggestions, and you were always open. We never felt the difference, no, in experience and in the role, because Jerome treats us as, at the same level, and this is rare, honestly rare. And so for me, it was a pleasure. And when we were organizing this conference, of course, as this is the last act, I think, at least within ESA of your career, to dedicate, to tribute you with this very small speech. And I mean, you marked a very important period of my life, so 8 years, a very long time, and you impacted truly the course of a lifetime. After my family, I think you are the most important person I met in the way you truly changed my life, allowing me to become an expert in many fields. And so I wish to thank you, warmly for this. I never forget the time we worked side by side in these 8 years. And just to conclude, we are awarding you now with these two little things. The first is in the frame of the Hydrospace conference, this Jérôme Benveniste Forest, Inspiring Research in Hydrology Science, which is a forest composed of 150 trees. Essentially, it's a tribute in the sense that, as you can read, it's a tribute of the European Space Agency and the Hydrospace 2023 community to one of their most distinguished members. It honors Jérôme's precious contribution, his 32 years of service to the scientific community. And the forest is meant to inspire scientists to advance our knowledge of water cycle and combat climate change by growing taller and taller trees in the Jérôme Benveniste forest. So by the end of the event, you will receive a QR code, but I think it's available also to you at the registration desk. You can select one of the trees which compose the forest, or real trees in various nations. And so this is the first tribute to Jérôme. The second one, Jérôme, if you can please come on stage, is a plaque for you, which is in recognition of all the years you supported ESA and the altimetry, oceanography, and hydrology communities, which will be forever grateful for your commitment, dedication, and guidance. So thank you, Jerome.
Speechless. I have no idea. I had no idea this was going to happen. The big drawback is that you guys are going to have a short lunch. I would like to, I mean, there's only one way for me to thank everyone and thank the culprits of this little moment, which I appreciate very much. Oh, yeah. Last time I cried is when I lost my parents. I can only find one way to thank the culprits of this moment. Yeah, so basically, I reached the best before date, and so I'm going to be unusable. But that doesn't mean that I won't see you. I really hope to see you at the 30 years of progress in radial altimetry, which is also a nice series of events where people get gathered in September in Montpellier. Montpellier is a very nice city, and you won't regret coming. And then, you know, I'm involved, I'm the vice president of the remote sensing of COSPAR, Commission A, and I intend to apply for president. You know, it's like Obama, you cannot reapply to the same post, so I have to apply to the post above. And so I invite you to look at COSPAR. It's something that was created after the flight to Sputnik for very good reasons, especially these days. We have these reasons flying in the atmosphere around the world. And so, you know, COSPAR was essential during the Cold War. Capacity building, also I'm involved in capacity building in COSPAR. So maybe I'll see you in Busan, in South Korea in July, in Montpellier. And someone has to think about the coastal altimetry workshop and the next Hydrospace. So I'd like to thank everyone who did this very, very nice, very nice moment. Thank you very much.
want to do the first one? I can introduce the session.
You introduce the session and I go with
The first talk, yeah. Yeah, should we do that? Advantage in remote sensing method techniques. But then, how do you turn down the... Oh. How does it do?
Marco. Technician is doing something.
Okay.
Yes, you are really thirsty.
I have mine.
Techniques.
It doesn't. It doesn't. It does, but it doesn't. Okay.
Okay, can you hear us? Okay, good afternoon, everybody. We hope that you had a very nice lunch and you're ready now to hear some interesting presentations. So welcome to this first sections of several with the name Advances in Remote Sensing, Method, Techniques and Products.
So the first speech is from Omid Elmi, and the title is Extending River Discharge Time Series of the Global Runoff Data Center, GRDC, using satellite data, a product with uncertainty estimate. Please.
Hello. Good afternoon, everybody. I'm very appreciative for this opportunity to present our recent development in Stuttgart. Today, I will present our new developed database, the remote sensing-based extension of GRDC dataset. We know gauge observation are backbone of many studies. We saw even the new satellite technologies for estimating discharge still dependent on the gauge observation. And for many hydrological models, still gauge observation, in situ observation are backbone of calibrating them as an input data. But when we look at the number of active gauge stations in the GRDC network, for example, we see after a peak in 1980, every year, year by year, we lost more active gauges. And we see, for example, now in 2023, there's a huge drop back because also the latency. So we have inactive stations and also stations that we have latency in data provision. And when we look at the map, the spatial distribution of the active gauges, we see that the majority of active gauges are accumulated in North America and West Europe. And here the pie plot shows the monthly average discharge of the whole stations versus the active station. We see, for example, in Asia, in Africa, we hardly measure less than 10% of discharge on that region. And we can see it even more when here I plot the number of active stations during the time in different river basins. For example, in somewhere like Mississippi, we only lost 20 stations out of 300 during from 1970 till 2020. But in somewhere like Ob, in river basin Ob, we lost something around 300 stations. We basically don't have any more measurement in Congo, in this very important river basin. Without any outlook to improve the gauging network, remote sensing data can be an alternative. We can estimate discharge from remote sensing data and developing a rating curve between gauge and space-borne river width or river height is the most straightforward one. Here is a very simple example. For example, in this case, in Niger River, we had a station. It was active from before 1970 till 2010. Luckily, we have time series river widths from MODIS from 2000 till now. We have 10 years simultaneous measurements. We can do the modeling. And then after 2010, when the station stopped providing measurements, we can continue it by having the river widths. But parametric rating curve does not always lead to promising results, because when we say we have a limited number of model parameters, we basically pre-assume that the river section always have the same relationship between different percentile of discharge and height and width, which is not always true. Therefore, if we do this assumption, we need to deal with a huge modeling error. And in this study, we address this question, and instead of finding a model parametric model with a limited number of model parameters, we use a non-parametric approach, and basically we let the data speak by themselves and define a non-parametric mapping function. So we propose a non-parametric approach based on the Monte Carlo simulation for developing a mapping function for transformed remote sensing data into the discharge. Our method is independent of simultaneous gauge and space-borne measurements, because we are not in a time domain anymore and we are on a percentile domain. We do not assume any specific mathematical model for river widths and discharge. And these give us a freedom to have a greater flexibility for accuracy in the modeling in the relationship between widths and discharge. Basically, if we assume a parametric model, whatever we have as an uncertainty at the end is a mixture between the uncertainty of discharge and the modeling error. And by applying this technique, we try to reduce the modeling error as much as possible. I don't want to go to the detail of the algorithm, but basically we do a Monte Carlo simulation and then a quantile matching procedure, and then after an iteration, when the algorithm is stable, we have a mapping function together with the uncertainty. Okay, now we have the model, and we want to see for how many of the GRDC stations we can run our model, for how many of GRDC stations we have enough remote sensing data. The input data for us is monthly time series of GRDC, because for some stations we don't have daily data, we only have monthly data, so we prefer to stay in a level of monthly. We have river width time series from a JRC Global Surface Water data set. We applied a technique to enhance the quality of that and obtain high quality river width time series for a Landsat period, and also water level time series from altimetry we generated in Stuttgart, and we use also the Dahiti database. Here, we exclude the stations with the monthly discharge less than 10 cubic meter per second, because they are mostly seasonal rivers and very narrow rivers that we could hardly get any reasonable, any high quality remote sensing data, so we exclude this group. In terms of number, they are about 4,000, but when we look at their contribution, their total contribution in the global monthly discharge, we see they are something around 35 cubic kilometer per month. But luckily for station with a large contribution, station with more than 10,000 cubic kilometer per month, we mostly have remote sensing observation for the majority of them, and for a station in the mid-size, with a moderate discharge, we have more than 50% remote sensing data for them. So we had three criteria. We exclude those with mean discharge smaller than 10 cubic meter per second, a station with less than 3 years of record after 1970, and a station that we don't have satellite data. We don't have satellite altimetry data because there's no track, or we don't have any river widths because of the cloud and this kind of stuff. After developing the model, also we had a quality assessment procedure. We start with comparing the remote sensing based discharge estimate with the gauge that we have on that station. If we have simultaneous data, we compare them through the kg value. We take the mean discharge as a reference, so minus 0.4 is a reference for us. If it's higher than that, we keep it. If our estimation has less quality, we just drop it from our database. If we don't have any simultaneous data, we compare their monthly mean. If we have a positive correlation, again, we keep it. Then we run a KS test to check the statistical distribution of data. Finally, we check almost all the time series one by one visually. If there is any unusual long-term pattern or any notable anomalies or anything which is not usual to us, we also exclude them from database. Basically, our time series are like this. For example, this is a typical example. In this station, this station was active until 2000. Then we continue it using width-based discharge. This green color means that this discharge estimate comes from river width. We have it until here, and then after that we had discharge from satellite altimetry, and it's active until end of 2022. So basically, in cases we have both estimation from width and height, we prefer to use satellite altimetry because it's more accurate than estimation from width. In some examples, we only have, for example, river width. In this station, it was active up to here, and then after launching Landsat 7, we could get some river width time series, and we can continue this station. This is another example. We only have river stage from satellite altimetry. We also have some interesting cases. For example, this one, we had some gap in the gauge, and we see, if you see here, these tiny green dots, we can fill the gaps by using remote sensing based estimation. And also here, this station was active from 2000 till 2010. And since we have river width estimation during the Landsat period, starting from 1984, we can go backward also to estimate discharge from the time previous the activation of this station. In the paper, we have a discussion about the performance of the algorithm in different climate regions, but I don't want to open it here. So regarding the color of this scatter plot, here we want to show that by increasing the monthly discharge, our performance of model is also goes increased. It means that when we have remote sensing data with higher quality, we can also provide discharge estimation with higher quality. We also see this here in the CDF of the statistics. For example, for more than 80% of the estimation, we have RMSE less than 30%. And for more than 80% again of the estimation, we have a KG value, a positive KG value. In this table also, we see the statistics for a station, larger stations, we can the performance of our algorithm is about 0.64, and by reducing the size of the river, the performance is also reduced. Another important aspect of our product is we promise to deliver also reliable uncertainty. Here, first of all, we want to see whether we have a consistent uncertainty through the whole database. Here in the X direction, I have estimated discharge in percentile for all the whole data set, the whole 3,500. And here I divided the uncertainty, the estimated uncertainty by the discharge, and it's on percentile. So we see a consistent performance. At the beginning, we have an interception point. It's never start from 0. And then after a few percentile, then in the mean percentile, in the average percentile, since we have a lot of measurement, basically most of our measurements are in the middle percentile, we can estimate discharge with the high quality, so the uncertainty dropped to the level of 4 or 5%. And then at the end, it goes up because we hardly have, we don't have enough measurements to can model the high percentile in the discharge. In the second plot, we want to show that whether our estimated uncertainty are meaningful. To do so, in the X direction, I plot the error, the logarithm of error. It's observation minus estimation. So it's a residual, it's error. And in Y direction, again, we have uncertainty, the logarithmic of uncertainty. We expect to have a linear relationship between these two. If the error is small, we expect to have small uncertainty, and vice versa. And here we got these point cloud. We see that if we run a simple 3 sigma test, we see that more than 85% of our data set accept in the 3 sigma test lies in this side. And also if we take the 1/3 of sigma as a line for that our uncertainty estimation are not too pessimistic, so to say. So more than 75% of our data lies between the line of the 1/3 of sigma and 3 sigma. And that's a measure for us to say that the uncertainty of our discharge are something reliable. For some cases, for example, we provide a very large error, but since also the uncertainty provided is also very large, if it's used in the model, this large uncertainty can compensate the large error that we have. Okay. And finally, this is the final statistics of our data set. Here, the gray line is the number of stations in GRDC data set. The number are in the white here, and here we have the accumulated monthly discharge. And the blue bars are the stations available in a GRDC data set. You see for most of the group, we can reach to the blue bar, reach to the gray line. We also have a lot of stations that either they are rejected through the procedure or we don't have any remote sensing data, but overall in each category, we try to reach to the amount of discharge that we have in GRDC data. And I want to back to this map again. I want to start from here. You remember this one after the peak in 1980, then we had a drop. And with the help of remote sensing data, we can keep this line nearly up to the 5,000 again. And here you can see the rise of the remote sensing based discharge estimation plotted on top of the GRDC data. In the map, you see, for example, in Asia, the improvement is significant. We hardly have, just the chart still in gray is very small. And also in the other continent, the improvement is huge. And when we back to the histogram of the river basin, we can see, for example, in Mekong, the improvement is from 0 to something around 96. And in Congo Basin, now we have something around 42 active stations. The good thing is that when the model is there, so the latency in the provision of data is not the problem anymore because remote sensing data is available sooner than the gauge data. So since the model is there, so updating this data set is not so a big challenge for us. This data set is available on University of Stuttgart Darus server, and you can download it and use it. And the outlook of this work, we are working on, we call it RSEC Plus, Remote Sensing Based Estimation of GRDC. And we want to extend this work not only on the GRDC, but the gauge of the other data center like USGS and the others. So that's the next step of our work. And on the technical side, for the river viz, we just rely on the optical. And now we have 10 years of Sentinel-1 data. And to the best of my knowledge, we don't have any river viz data set from Sentinel-1 until now. That could be a huge development if we can add Sentinel-1 river viz time series to this data set. Because for some region, we just rely on the river viz. And since in the winter it's all contaminated by cloud, we basically have observation of summer. And that could be a huge improvement if we can add SAR images in general. And that's it. Thanks a lot. Thanks for your attention.
Thank you. One quick question, if any. Oh, okay, one, yeah.
Yeah, okay, thank you for the presentation, quite interesting. I have a question. Have you done a calibration of your model afterwards? Let's say you have a station which is available for the GRDC data set, and you apply your model and compare it with a gauging station data?
You mean the validation part? We put a set of GRDC data outside of modeling at the beginning, but at the end, since everything was stable, the result I showed here is for both that the data, the validation set data set, I would say, and also the one inside the modeling. So the data showed out here is the combination of both. But we had also a validation data set which was outside the modeling, and we test through all that also.
Okay, thank you very much.
Thank you.
So we should better move to the next speaker. So our next speaker is Sophie Legac from CNES with the title, What Can We Learn from Numerical Simulation of Satellite Altimetry Signal over Rivers, Detailed Studies and Comparison to a Dataset of Sentinel-6 Individual Echoes. So.
Thank you, Karina and Angelica. It's me again, sorry, same voice, it's getting better. So this time I'm presenting the works of my intern student, Elliot Bourget, who worked with us at CNES 6 months this year. And he just graduated from the engineering school, ESA-ESRIN, and he was also in a master's study at the Royal Institute of Technology in Stockholm. So, of course, we already said it this morning, water is a key resource that needs global monitoring for better monitoring and risk, global monitoring and risk mitigation. And my talk will be about altimetry data. Altimeters, they provide global measurements of surface water levels. Although they were primarily designed for ocean, they also deliver quality data over inland waters. But these scenes over land are very heterogeneous in the antenna footprint, which poses some problems. So our question during this internship was, what can we learn from numerical simulation over rivers and how to do that? So there were many objectives. The first one was to characterize the nature and the variability of the altimetry signals over rivers. Then to improve a simulation tool for realistic rivers, but because usually we simulate very simple rivers that do not look like real rivers. Then we wanted to evaluate the impact of using the simulation inside the processing algorithms of real measurements. And the ultimate goal, of course, is to improve the water surface elevation values. So there are several nadir altimeters currently flying, but our study was mainly interested in Sentinel-6 data. Just a short background on altimetry data. So over the past years, the altimeter's tracking capability has been very much improved due to the tracking function on board. But the retracking algorithm that we do on the ground still suffer from several approximations because we don't use a model that is really adapted to the nature of the hydrology signal in the altimetry signal. And sometimes we can encounter errors in the estimation of the water surface elevation that can reach tens of centimeters or more. And some echoes are really complex to deal with. So we have still a lot of progress to make. We need to understand the specifics of the signal of the rivers in particular. And to our understanding, we separate the processing for lakes and for rivers, as lakes are sometimes more close to the ocean waveforms, but over rivers, it's not the same story. Abilea in 2017 and then 2021 referred to the specular flash observed over rivers, and they define a model. So in this end, simulations are very useful to understand what can be done over rivers. So Sentinel-6 data was launched in November 2020. It's part of the Copernicus program. It's the operational oceanography mission, but it's also a very powerful tool for hydrology. It's a Ku-band nadir altimeter, but it delivers individual echoes at 9 kilohertz sampling over some areas of the globe. And we have interleaved chronogram, and not going into the details, but it's very useful and facilitates the ground processing and innovative processing. So we built a database of individual echoes from Sentinel-6 over 100 rivers over the globe of various widths and properties. We try to be representative of the world's rivers. Almost 2 years of data. And we extracted the satellite position, the real position, and not the theoretical ground track. We used the real one. We used complex individual echoes, so INQ samples. We selected roughly 3 seconds of observation over each river. And we also have a water mask of the river that we use. The plots here, we looked at, it was a first assessment of our database. We looked at the peakiness parameter, which is an indicator of how peaky the signal is in the waveform, both for echoes that are measured over the river and outside of the river. As you can see, echoes inside the river are mostly very peaky. The highest value, the peakiest is the echo. But you can also find peaky echoes outside the river. So that was quite interesting. And another parameter is the sigma naught, is a backscattering coefficient. For all rivers, you can see that as in the theory is found, sigma naught values are higher over the rivers than outside. So in this database shows that Sentinel-6 are very peaky, mostly similar to a square cardinal sign. And we find high sigma naught values over the rivers, but also outside of it. This is a very interesting example of Rio Madeira in Brazil, where we have a single overflight of the river. And I show you here two examples of individual echoes. So the middle panel here shows you the overflight and three different parameters. Here you have an indicator of the sinc square shape. But look at the sigma naught, which is very variable over the river. The blue envelope here is when we are above the river. And this is the water surface height that we retrieved using a sinc square model. And you can see that on some parts of the river, it's really a flat water surface elevation, meaning that the signal is really peaky, corresponding to a sinc square model. But in some other areas, our retrieval is really noisy, and we can make a lot of error when we use a sinc square model, because the signal is not a sinc square. So what is it? And we looked at the individual echo. So this is the illustration here. Here it's in this part. So it's a very a sinc square echo, perfect. The red curve is the model. And on this one, you are in the middle of the river and you don't see a specular echo anymore. So this example is just illustrative of the fact that over rivers, it's very complicated. And most of the time we have a sinc square like echo, but sometimes it's very noisy and maybe multiple peaks, and it's complicated to process with a single model. So our simulation framework takes a water mask as input. It allows multiple water bodies in the scene. We also have a roughness value for each water body. We can put relative heights for different water bodies, and we use the real satellite ground track. So basically we take all this, we do the simulation, and here you can see a bank of simulation. The three curves correspond to either a very specular surface, it's the blue one, a very rough surface in orange, and a mix of specular and rough in green. Here is a different type of visualization. It's the evolution of the power, the altimetry power, in function of the distance along the track. So when you are before the river, over the river, and after the river, you can see the classical evolution of the signal over the river. We validated our approach against a theoretical study by Abelia, retrieving this V-shape function. Here it's the size of the 10 dB lobe width in this kind of in this evolution. When you take the max minus 10 dB lobe width, you plot it against the river width or transect length, and you obtain this kind of V-shape curve. And the light orange arrows are our results. Here is an example of the Garonne River in France, near La Réole. So Sentinel-6 is flying here. It's the theoretical ground track. The river Garonne is in blue, and you have to know that there are other water bodies around. This is like a sandstone quarry, and this is our simulated scene. So we take into account the river and other water bodies. There are three steps. The first step is an initial simulation, so blind simulation. We simulate the altimetry signal, and we obtain this kind of echo. And the black one is the real one from Sentinel-6. So you can see it's not that quite the same. And then when we separate the various water bodies in the simulation, and we affect a priori heights for each of them, we obtain this one. So it's closer. You can see that the river signal is in blue, the quarry signal is in orange, and the green one is another water body here. So what we could have misinterpreted at the beginning for the river, for example, if we thought it was this peak, we would be false, because actually it more looks like the quarry, the signal coming from the quarry, and the river peak is the second one. And when we adjust the simulation with the fitted heights, we have a minimization of cost function. We obtain this final result, which shows that our simulation best fits when we take the relative heights and roughness of different water bodies. Elliot performed a statistical analysis of all the rivers in the database. So he prepared the datasets, he launched a simulation of all the rivers, and then he output some diagnosis here. So some kinds of diagnosis he showed was a comparison of the echoes. So for example, for a river, you have this kind of fitting. You can see it's slightly shifted in the x-axis. So this is what is represented here. And so he computes the shift between the real one and the simulated one, and then he fits both of them. And then he computes here the overall statistics in terms of error. So the color is the heat map of the number of samples, and what you can see in the red curve is the absolute error in function of the peakiness here. So you get a trend that you get less error when it's peakier. And here, in function of the transect length, you get more error when the transect length is longer. So our conclusion is that the simulation works best for peaky echoes and narrow rivers. He also performed a quick analysis in function of the river surroundings, because obviously it's very heterogeneous. Some rivers are surrounded by only forest, for example, or are found in urban environments, or surrounded by crops, fields, etc., which can be very wet as well. So he found that the simulation works best for homogeneous environments, which is not surprising. And to conclude, our simulation includes the parameterization of various parameters, such as the surface roughness, detailed water mask. I did not go into detail about that, but we use several of them. And we can consider multiple water bodies with various elevations. So this study has confirmed our initial hypothesis on the altimetry signal simulation of rivers. It confirmed that it's very complex and variable over hydrological scenes, which makes the processing very challenging. And we also investigated other parameters, such as the river slope, but it had no significant impact. So the next steps, and I will advertise some other presentations from this week. So over lakes, this time you have we work with CLS to develop a lake processing prototype, and you can go see my colleague Carlos Yanes at his poster number 18. He's got a great example of a reservoir in Spain. And over rivers, we're working a lot on this topic. And François Boy will give a very interesting talk in this session. And also Jean-Alexis Daguzé on Wednesday. Thank you. I think I have no voice anymore. Thank you.
Okay. Thank you, Sophie. So are there any questions? We have time for questions.
No voice, so maybe
okay,
during
so
a coffee break or
yeah. So maybe I have a question also. So have you thought about maybe also adding a DEM into your simulations when you simulate the waveform?
Yeah, we did that. We have two separate tools. A simplified one, which is not so simple, it's this one, and another one who takes into account high resolution DEM in input as input, but it's very time consuming. Not so much, but it's higher time consuming than this one. So baby steps now.
Thank you.
Okay, let's move to the third speaker. From Christian Schwack from DGFI TUM with a presentation on generation of high-resolution water surface slopes from multi-mission satellite altimetry. You have 15 minutes for the question, if you want question.
Thank you very much for the introduction. So the next talk is about the generation of water surface slope from classical multi-mission satellite altimetry. First, I would like to introduce my co-authors, Michał Halicki from the University of Wrocław and my colleague Daniel Scherer from the Technical University of Munich. So why are we want to estimate water surface slopes for rivers? So the river discharge, as you know, is an essential climate variable, which has been defined by the Global Climate Observing System. And here you can see, in order to estimate the river discharge, we need also water levels, and both data sets, the river discharge and the water levels, have certain accuracies, so goals, which have been defined. In order to achieve such goals, both products, so the river's discharge and the water level, have to be improved further. And one point is the water surface slope, which is very important for both parameters. So what we did so far was we published one paper last year where we derived water surface slopes globally from ESA-2. This is available also on a poster here, 74, tomorrow. And on the other hand side, we also derived in another approach water surface slopes between virtual station, between sentinel tracks. And now we would like to combine classical altimetry, all data we have, into one approach in order to estimate a high-resolution slope along a river. So our study area were some Polish rivers, so 11, which you can see here on the map at the right. And the characteristics of these rivers is different. So in the north of Poland, we have wide rivers with small slopes, and in the south of Poland, in the mountainous region, we have smaller rivers with higher slopes. And why we used this study area was that the Polish Institute of Meteorology and Water Management provides 600 water level stations we could use for the validation. And in our approach, we were able to use 81 of them, which were located along the rivers of interest. And as input data for our approach, we used calibrated water levels from multi-mission satellite altimetry. And in this approach, we would like to use so our focus was on using not the classical missions which were flying on a short repeat cycle, but using missions which were flying on geodetic orbits or drifting orbits, such as, let's say, the ERA-S1 at the beginning, which was flying on a geodetic orbit, but also the JSON-2 mission, and of course, the Sentinel drifting phase now. And additionally, we added the cryosat mission, which has a repeat cycle of about 1 year, and also the 2 ISAT missions. So we have a coverage of different missions which we're measuring at different locations and not always at the same position. And this leads us to our new approach. So here's a small flow chart of this approach at the right, and I will show now how this approach is working for our river section in Poland. And so the goal here is, on the one hand side, to use all the water levels by an least squares adjustment. And based on them, we extended the classical least squares adjustment with an additional Laplace condition. and an a priori gradient condition. But I will show now the approach step by step. Here, for example, you can see an example of the data coverage. So the first step is that we extracted the center lines from the SWOT datasets, which was produced for the SWOT mission, and it's a high-resolution dataset which describes the center line of the river. So you can see here the black line in the middle, and based on them, we defined our own center lines, which has a resolution of 1 kilometer. And based on this 1 kilometer points, we estimate the water levels and finally the water surface slopes. And here you can see the advantage of using altimeter missions which have a drifting or geodetic orbit, that we have a good coverage along the river. So you can nicely see here in red or here in green, the classical short repeat time missions such as Sentinel or JSON. But then in between, you can see the data from Cryosat or ISAT 1 and 2, or also the ERS data. So this is a river section along the Whistler River, which has a length of about 25 kilometers. And you can see here the good coverage of altimeter data if we use all the data we have. This is then used in a least squares adjustment to estimate a water level at each 1 kilometer location along the river. The altimeter missions are weighted by a mission-dependent weighting derived on their uncertainties. And then we added, of course, a Laplace condition, because it can happen if we have smaller rivers that we don't have an altimeter mission, altimeter measurement within each bin we would like to estimate a water level. And this allows us to estimate a gap interpolation and also a kind of smoothing, because we don't want to estimate a time variable water surface slope, but because therefore the altimeter measurements are not enough. So our objective is to estimate a static mean water surface slope along the river. And finally, we apply a third condition, an a priori gradient condition, which is used to stabilize our least squares adjustment to the boundaries, because we can only estimate this approach along the river in sections which has no discontinuities because of dams or reservoirs. And the weighting of these parameters is, as I said, the mission-dependent weighting for the altimeter measurement and a relative weighting with respect to them by the factor of 50 or 100 for the Laplace condition and the a priori gradient condition. Here you can see now how this looks like. Here's a 211 kilometer section along the Whistler River, where you can see in the upper part all the water levels we have along the rivers. Here are also some data gaps. And based on our approach, we can then estimate an average water level along the river. So you can nicely see here also when we have JSON data, where you can see the variations of the rivers of several meters. But that's not the intention of our approach. We would like to estimate, water surface slope. And this is then derived from the water levels. We can achieve then the water surface slopes here between all the 1 kilometer points we have. And this varies between 0 and 250 millimeter per kilometer. Here are two examples of the Oder River, the full river, or the Whistler River, where you can see here over 500, almost 500 kilometer, the water level, water surface slopes in red along the river. And also here at the Whistler River, you can see that we can estimate water surface slopes along almost the whole river. Here are a few points where we don't want to estimate them, because here are reservoirs and all the gray lines are dams along the river, and there the river sections are too short to estimate the water surface slopes in between. But in general, I would say, as on longer river changes, river section, we can estimate a water surface slope. And of course, the validation is quite challenging, because you don't have in situ water surface slopes, and therefore we compared our results with different other data sets. On the one hand, we used water levels from in situ stations. So we have 2 in situ stations along the river, and then we can estimate a mean water surface slope between them. And then we also average our water surface slope and compare them with the average water surface slope from the in situ data. So, but I will show it later in the validation part. And then we compared our results also to water surface slopes, which have been derived from DEM models or from LIDAR. And one data set is from ISAT, and also the water surface slopes from the SOAR data sets. But therefore, this is what I'll show later. Here's the final results of our approach. We estimated the water surface slopes for all of the 11 rivers. Here you can nicely see the slower water surface slopes in the north, and in the mountainous region, you can nicely see also the high water surface slopes. And in the middle, you can sometimes see, for example, that here are no water surface slopes are available because this is related to reservoirs and dams. And what also can happen that we are not able to estimate the full river here, for example, is that the SOAR datasets does not provide center lines for the whole river at the end. And now I'm come to the quality assessment, the validation we performed. So here you can see now the 8 rivers where we had in situ data for a station. And then we made estimated RMSE values between all the combination of in situ stations we have. So if we have one river, we estimated all the combinations between the different stations, and we are able to estimate mean values between the different sections. So then we have more data sets we can compare. And based on this, we estimated also a mean water surface slope based on our data and estimated RMSE values. And this has been done for all the 6 data sets. As I said, the first data set is first column is our result. Then we have the 2 RMSE values for Butenick and Cohen, which has been derived from DEM models. Then we have the LIDAR data set. Then also the data set from Scherer et al., which has been derived from ISA2 only. And then we have here at the end the data sets, the water surface slopes, which have been derived from hydrosheds, and they are provided in the SOAR data sets. And you can see here that in 6 of 8 data set, our new approach performs quite well. Only in 2 cases, the ISAT approach only is slightly better. And also in 1 case, in a steeper region, we can also see that here the DEM approach is a bit better. And overall, when you estimate the mean RMSE values, we can see a strong improvement compared to the other data sets. Another possibility how we can show that our data sets are reliable is that we would like to improve our water level time series from satellite altimetry. So for example, classical altimeter missions have an orbit shift about 1 kilometer. You can see it on the map in the top right. The yellow point is the reference point of the virtual station. And now we would like to correct this water surface slope error in order to improve the water level time series. And now you can see here the time series from Tahiti in red is the original one, which is not corrected for water surface slope. And the green one is the corrected one. The blue bars show the distance between the reference location and the altimeter crossing. And at the bottom, you can see the improvement. So the difference between the in situ station before and after correcting the water surface slope. And in this case, this was for the Sun River. We applied a water surface slope correction about 500 millimeter per kilometer. And we could here improve the RMSE from 36 millimeter before correcting the water surface slope down to 21 kilometer, which was a strong improvement. Also, if we look at another target in the mountainous region, so here the river is quite small, about 100, 200 meters. And there is also a strong water surface slope of about 1000 millimeter per kilometer. And also here you can see the improvements if we apply the water surface slope correction. And here we could decrease the RMSE from 49 centimeter down to 29 centimeter, which is a strong improvement by only applying this water surface correction. So let's come to the conclusion. So this study showed a new approach to derive water surface slope from multi-mission satellite altimetry, which is an excellent data source, I would say, to derive such slopes if you combine the different mission phases observed by multi-mission satellite altimetry. And also, this study showed strong improvements compared to other data sets approaches to derive the water surface slope. So we could derive very high accuracies, especially for the large rivers, such as Oder and Vistula, which had only 6 or 12 millimeter per kilometer RMSE, but overall we could achieve 3 millimeter to 18 millimeters, depending on the river section. But if we look forward with SWOT, for example, there the accuracy requirement was about 70 millimeter per kilometer, and we would say we are also in a good area with our classical altimeter data. So the next step will now also to derive water surface slopes from SWOT directly and also compare it with our approach. And what we also showed very nicely that if we apply the water surface slope corrections to our water level time series from satellite altimetry, we can strongly improve the results of them. And this whole approach is now also, there's also a manuscript currently in review by the Journal of Water Resources and Research. Thank you very much. That's it.
Thank you very much. Do you have any questions? Yes, please.
Thank you for your presentation. If I understood correctly, you suppose the slope is independent on the flow condition, it's a static variable?
So in our case, we try to estimate a static water surface slope because we don't have enough water levels from satellite altimetry in order to estimate also the time variability. That's the reason why we have here, for example, you can see it looks like noise, but that's are the seasonal variations you can see. And so by applying our approach, we get then an average water level along the river so that we can then also estimate only an average water surface slope, a static one. Because at the moment, with classical altimetry, there's not enough data to estimate time variability along the whole river, especially if we look at smaller rivers where we don't have so much data.
I have a suggestion
Yeah.
for the validation, because in our project Street Art, we have this problem of validation of Sentinel-3 because the in-situ station is far from the virtual station, so we need the slope of the river, and the slope change with the high flow, low flow. So what we have done with Jean-Christophe, Nicolas Picot, and many other, Hervé Jesus, Nicolas New, we use the drone flight. So if you have some campaign and you can fly over the river in different regime, you can obtain some at least.
So this is what we did in the first column. So we used LIDAR data already. But this was also quite noisy because we had also the problem that the center lines from SWOT are not often really located over the rivers. And so it was a bit hard to derive valid heights from the LIDAR measurement itself. So we had some problems in the processing, I would say.
So because we need to do some recommendation to the agency, what do you need for improve this method? A new center line?
So in this case, I would say we processed the LIDAR data by ourselves because this was not measured by us. So it was by the public agency. So maybe also a data set which has been derived in pre-processed by people who know how to work with LIDAR data would be good for validation. So using the data, maybe to have data which is ready to use, I would say, for the validation. Because now we did it on our own and we are not experts in LIDAR data processing, I would say, because we used almost raw data to handle them. It's what's not so easy, I would say.
Okay, thank you. Any other question? No? Oh, yes.
Okay, so I can introduce the next speaker, which is Francois Boy, also from CNES. He will be presenting measuring a longitudinal river profile from Sentinel-6, fully focused SAR.
Good afternoon, everyone. So first of all, I would like to acknowledge my co-authors, so Nicolas Picot from CNES and Sophie Legac, and also people from the Vortex IO company. They provided fixed stations and also LiDARs on board UAVs to validate this work. So let's start. So can we measure longitudinal river profile using Nadir SAR altimeter? So it is the impression I had when I looked at the 40-focus SAR measurements on the Sentinel-6 mission for the first time. This is an example here. For those who are not familiar with 40-focus SAR, it is a SAR processing technique that can provide half-meter resolution in the on-track direction. So here it is the configuration with a 10-meter posting rate and resolution. It is a good compromise between resolution and precision. And this is an example over the Garonne River. You will listen a lot about Garonne River. We use a lot of this location close to Marmande for all of our work in inland waters measurements. So this is an example over the Garonne River close to Marmande. And our eyes, we can clearly see the river profile in the radiogram of the altimeter. These are waveforms. It looks like a SAR image. It is not a SAR image because it is an IDR altimeter, but we can clearly see the profile of the river in this radiogram. So if our eyes can see the river profile, why not trying to measure high resolution river profile using this measurement? And here we can see also some locks. This is the canal latéral de la Garonne, and we can even see the locks of the canal. And so as I mentioned, the signals are very powerful. They are sharp and powerful, even at off-nadir location. This is distance to the river, so we have powerful echoes at nadir. It is normal because it is nadir altimeter, but we also have up to 10 dB of signals up to 5 kilometers away from the nadir location. So I think, yes, we can measure longitudinal river profile using SAR nadir altimeter, but we have to take cautions because it requires to process both nadir and off-nadir signals. And the system has not been designed to process off-nadir signals. So we have to take cautions to not be trapped by ambiguous return. The SAR processing technique removes the back and forth radar ambiguities, but the right and left ambiguities remain in the nadir SAR altimeter. So we have to take cautions when we process off-nadir signals. However, in some limited cases, in given configuration, we can remove those remaining ambiguities, and so we will be able to process off-nadir signals safely. I give here an example. If the river is flowing down along the satellite track and provide a single crossing with the radar footprint, we can easily remove the right and left radar ambiguities. Even if there are also water bodies, if the shape of the river is really different from the other water bodies, we'll be able to remove these kind of radar ambiguities. And so it is maybe the first message of my talk. You will see a very accurate river profile using this processing technique, but keep in mind that it will only work in some limited cases, unfortunately. But when all the cases are met, you will see that the precision is really excellent. So we will focus on this kind of rivers flowing down along the stellar track and providing us a single crossing with the radar footprint. Then we have to revise the classical nadir altimeter equations to compute the water surface elevation, because we will process of Nadir's signals. And so there is a slant range view of the river. So we have to consider what we call the slant range correction, that is an extension of the range to compensate for the slant range view. It is really easy to compute. If we have a pre-knowledge of the radar center line, so I will be using a river center line, with a simple calculation, we can compute the slant range correction to be applied to the entire equations to provide a water surface elevation. But again, there is another limitation. We understand that if the river bed is moving in time, this processing will be not any more accurate because we need the river to be steady in time because we use a static river center line here. Then, as we introduce a new correction, we want to control the error, the uncertainty of this new correction. So here we will compute the uncertainty of the slant range correction. And we easily understand that here I'm making the assumption that the signal is coming from the center of the river, but it is an assumption. The signal can be basketed by one side or the other side of the center line. So the uncertainty of this correction will be directly correlated with the river width and the distance to the river. It's only geometry. And so here I wanted to control this new uncertainty of the Nadir altimeter performances. And so I just put a threshold to not overpass of 15 centimeter. And so it gives me another limitation. So I will focus on the river that have a width below 200 meters and a distance to the Nadir below 2 kilometers cross-track. Just a short comment on Sentinel-3. We also have the fully focused SAR on Sentinel-3 mission. But here you can see that the uncertainty is higher. It is mechanically higher on Sentinel-3 because the satellite is flying lower, at a lower altitude, and how the altitude of the satellite play a role in the uncertainty of the slant range correction. It is more difficult to apply this kind of processing on Sentinel-3. That's why I'm focusing here on Sentinel-6. Then we have to decide how to process those nadir and off-nadir signals. And Sophie Legac earlier presented some tools we developed at CNES to perform simulations over rivers. And so I played a lot with this simulator to identify which model I have to apply to have the best accuracy and precision in that conditions. So I won't go in detail, but just tell you that I play with river widths, river direction, river slopes, the distance to the nadir. I played also with the basketting regime. I put some specular regimes, some diffuse regimes. But whatever was the simulations, the results were the same. The sin square model is the best one in that conditions. And it is quite obvious since if you remind all the conditions, we will process rivers flowing down in the along track direction with a processing that provides a 10-meter resolution. So the spot that is lightened by the radar is only 10 meters in the along track direction and the width of the river in the cross track direction. So it is a small spot. And in that conditions, the signal is very close to the point target response of the radar. So it is a sin square, and the best way to process a sin square is to use simply the peak position. So I will search for the peak position to obtain the range measurement from the radar altimeter. But the next question is which peak to select. But this is just an example of the waveforms we can have in such configuration, which is a waveform over the Garonne. And there are 6 peaks, and which one to pick. And it is a general comment. Today, in operational processor, we process waveforms the same way we process waveforms over ocean. We process waveforms separately, individually. But over rivers, it does not make sense. I think it's really important to consider the entire acquisitions over a given water body because it gives us a lot of information to drive the processing. So if I ask you which peak corresponds to the Garonne River, maybe most of you will tell me the most powerful one. But now if I show you the radiogram, everybody will tell me, well, the river is here. And so this is the peak of the Garonne River. So considering the entire radiogram, it is easier to focus on the right peak to have the best estimate of the water surface elevation. So now it is step-by-step definition of this processing. So this is the output of the fully focused art processor. We oversample a lot this output, have a fine resolution. Then we compensate for the slant range correction. And here we can already see the profile of the river. We see the river that is flowing down in that direction. Then I have to start to initialize the processing. And so I will simply search for a linear shape in the radiogram because it is a river, it is flowing down. So I will search for a linear shape to initialize this processing. And then to process the other waveforms, I will not consider the entire waveforms. Again, here, now I have initialized the processing. I'm on the river. It is a 30 centimeter per kilometer slope river. So the next measurement that is in front of the first measurement has an elevation that is only different by few millimeters. So you don't need to search for the peak position in the entire waveforms. I will search for the peak position plus or minus half a gate around the previous estimation. And I will propagate this first estimate back and forth to measure the longitudinal river profile of the Garonne River. And here we are. So this is the longitudinal river profile of the Garonne River. So it is an 18-kilometer river profile with a 10-meter posting rate. So this is a high-resolution river profile. And I'm not an hydrologist, I'm a radar processing expert, but I'm sure that all hydrologists in the room will recognize the typical behavior of such a river between high water situation and low water situation. When water is low, the profile is not a nation of pools, it is flat regions with calm water, and rivers that look like this with quick elevation change of the river elevation. And then when the water level increases, the pools are filled with water and the profile is becoming more homogeneous. So I was really happy with these first results, and then looked at how the profile evolved in time. So this is here the elevation of the Garonne at the beginning of the profile, and this is for each date along 1 year, how the profile changed in time. And so you will see that when we have this flooding event, the profile is becoming more homogeneous, but then when the water surface elevation decrease, we see more rivers appearing in the river profiles. So I think that for hydrologists, it's a very interesting measurement to understand how rivers are behaving in time with respect to the river elevation. So then we wanted to validate accurately the performances of this processing technique. So first, we have compared the river elevation with a static station. So we take the measurement that is the closest to the station, and we compare both data sets. So in gray, this is the elevation provided by the station. In blue, the measurement from Sentinel-6 microflash mission. And the agreement between both is about 3.7 centimeter RMS. It is really excellent. Before Sentinel-6, it is rare to see performances below 10 centimeter RMS. But how we are measuring river longitudinal profile, we wanted to compare directly the profile that had been computed with an in situ measurement of the profile. And so here, Vortex.io deployed 2 drones with their LiDAR technique on board, and they deployed both UAVs at the same time. Then Sentinel-6 overflew the Garonne River. And in black, this is the profile provided by Sentinel-6 mission, and in blue, the profile from Vortex.io. And the agreement is, again, quite excellent, except that here, for the highest refill of the river, we can see exactly the same rivers in both data sets locating at the same location. So I was really happy with these results. More recently, we compared Sentinel-6 with the SWAT mission, And again, the agreement is really good. I applied no bias in any data set. It is the two data sets plot in the same figures without any corrections. The SWOT measurements are slightly more noisier, but keep in mind that Sentinel-6 processing, this processing is limited to some conditions, whereas SWOT will provide globally this kind of river profile. I have other examples, but I think I will go quicker to not overpass my time. This is another example. It is the same processing technique, but applied to the canal latéral de la Garonne. And it is, again, very impressive how we can measure the profile of the canal. We can even see the locks of the canal. And here we are able to measure something that is close to 1 or 2 centimeters per kilometer slope of the canal. So really high precision. So my conclusion is that using this processing technique, we can provide very accurate longitudinal river profile using the Sentinel-6 microfoliage mission. Unfortunately, over limited cases, but when it works really good. And I think that this data set can be very useful for hydrologists to help them in understanding river evolution. So this data set will be used to contribute to the validation of the SWOT mission. I already show you one example over the Garonne River, but we will do this over more rivers. We are already collaborating with the Fairfax Institute to improve river modeling and flooding event prediction using those profiles over the Garonne River. And I invite you to have a look on the poster from Tanui, from the Fairfax. We are also working with CLS, because I was a little bit frustrated about all those limitations. So Jean-Alexis Daguz will make a presentation next Wednesday. And so he tried to overpass some of those limitations to have a more global approach to densify the virtual station that Sentinel-6 can provide over rivers in the corridor of plus or minus 4 kilometers. And we are also collaborating with other groups dealing with similar challenges. Fritjof Ehrers from TU Delft, Jean-Damien de Joncker from JPL. Beyond this work, my main message is that Sentinel-6 microfoliage mission is the best nadir altimeter in town for the observation of rivers and lakes. And I really invite all radar processing experts to have a look at this mission, because clearly the precision is tremendous. For the first time, I really think that we can achieve 10 centimeter total uncertainty over rivers and lakes with an nadir altimeter. So I really invite you to have a lot of interest in that missions. And I have two last results. Just a quick wink to Cedric from JPL. This morning, you show us SWOT results over swimming pool. And when I performed this work, I was interested by those small dots in the radiogram. So this is the canal latéral de la Garonne, the lock. And here you can see 2 dots. And these are actually swimming pools. So this is a 4 by 8 meter swimming pool, and this one is a 10 by 5 meter swimming pool. So again, I don't see any scientific interest in measuring swimming pools with Sentinel-6, except for taxes authorities, maybe. But it doesn't work everywhere, so don't panic. And this is for fun. I just measured the, let's call the swimming pool surface elevation with respect to geoid, and I think it is quite relevant. It is only plus or minus 6 variation along the year, a full year, and I think maybe the owner filled up the swimming pool at the end of the summer. So thank you very much.
Okay, I think Remco has a question.
Yeah, thank you for the shout out to Sentinel-6. Is there anything that we can do on the upstream side at EUMETSAT, for example, to make this even better?
I think the room for improvement is huge. And I really invite all the experts, all agencies, institutes to have a look on Sentinel-6, because the potential is just huge. I'm sure you will have plenty of ideas, Remco.
So what's the limit? The potential is huge, and the limit?
The limit is that it is an ideal altimeter. I think that we will be able to retrieve water surface elevation with good accuracy, but only in a corridor of plus or minus 4 kilometers around the track. So it is a small corridor if you compare to SWOT with the two big swaths. So it will be better than what we can achieve today, only looking at nadir crossing with the river. So I think that we can densify a lot the virtual station that we can provide with Sentinel-6 mission.
But can you apply this kind of approach globally?
Yes, we can apply globally, but you will find maybe 100 cases or 200 cases, 200 rivers that comply with all the limitations I just mentioned. But Jean-Alexis is working hard to try to overpass some of those limitations I just mentioned. But I don't want to create too much hope in that work, honestly. I know that the profile is really impressive, the profile and the precision, but honestly, I spent hours trying to find rivers that comply with all the limitations, and today I found 20 cases, so it's not a lot.
More questions? Yeah.
Cedric.
Also, that was a really great story. I think you demonstrated that nadir is not dead.
Exactly.
Yeah, it's really impressive work and nice job with the swimming pool. Hey, do you have a perspective on SWOT nadir versus Sentinel-6 Mike Freilich? When you say best in town, are you including SWOT?
I have more expectation with Sentinel-3 NG because on the SWOT, the nadir is a old-fashioned altimeter. It's great, we have it, we're not complaining, but it is a conventional altimeter, and this technique is not possible on conventional altimetry. But on Sentinel-3 NG, it was mentioned by Remco Charu, that is currently developed by ESA and EUMETSAT. You have both. You will have a super nadir altimeter, POS5, it is even better than this one. And we have SAO, it is a swath altimeter with an heritage from Carin instruments. So you have both at the same time. So we can imagine to have profile provided by the swath altimeter plus the nadir complementing this use set of measurements.
Yeah, well, I had a similar question. Thinking of crystal, so you have two antennas and you have the fully focused SAR processing capability and so on. Can you project what you could do with crystal over inland water and make sure that crystal is a hydrology mission and not a cryosphere mission?
I think that crystal could have been the best altimeter in town after Sentinel-6 if we have afforded for the SAR interferometer mode over hydrology. Unfortunately, for system capability, I think it was decided to just use the SAR mode of crystal over hydrology. And so the interferometer will be not used over hydrology. I hope I don't say a mistake, but I think it was a choice made by the agency to limit the telemetry measurement. But if you decide to use the interferometer of hydrology, it will be clearly another tremendous data set for hydrology.
Glad to hear that. Maybe we could have a few seconds of data to play with. And I don't want to hijack crystal at all. I was already a very bad culprit of cryosat. I wanted to make an oceanographic mission, but the technology that you develop is really promising. It's very, very impressive. And I think we should think of over-exploiting, pressing the juice as much as possible. And if there is some resources to do some acquisition in the estuaries or in the Arctic rivers where there's CI and so on, maybe we could benefit from that. Excellent work.
Thank you.
Thank you. We move to the next speaker, Elena Zakharova from EOLA. And the presentation is on the altimetry for the hydrology of Arctic rivers.
My presentation is dedicated to the altimetry and its application to the Arctic rivers. And I'd like to thank all my co-authors listed here and even not listed here. And I'd like to share my ideas and some of my recent results that I achieved during my almost 20 years work in this environment. And last year, I'm concentrated on the Arctic rivers itself, but also my interest covered wetlands, permafrost, and lakes. Now, I divided my presentation in several parts. First of all, I would like to highlight several specifics of Arctic river hydrology, which are important for remote sensing and specifically for altimetry. Then I would like to demonstrate the impact on water level measurements by altimetry, of course, and on the methodology to retrieve the discharge from the altimetric measurements. And finally, I will present several recent discharge and some retrospective, several two slides dedicated to recent achievement on discharge estimation in Arctic environment. Only several specifics that I would like to mention today. First of all, of course, the snow which covers the watersheds and rivers for 6 and up to 8 months each year. And then the massive snow relief as a meltwaters during just several weeks or maximum 1 month in spring, which could be in April or in June, depending on the latitude. Then I'd like to demonstrate just impact of large amount of wetlands and lakes that we found on the high latitudes almost everywhere in Arctic, on the measurements and also on discharge retrievals. And of course, the ice. Ice is an important agent in the water regime, on local and regional water regime. And I would like just to highlight one important thing that when we calculate the discharge, we assume that our approaches are developed and valid for open channel. So we apply open channel equations in some assumptions. But during the winter, of course, the Arctic rivers are ice covered, and we need to add more assumption to our existing assumptions to derive the discharge in the Arctic during the winter. So the snow accumulation for 6 and 8 months and massive release during the spring just for several weeks or up to 1 month. From 66 degrees to north, there is this very, very nice seasonal variability of the water level and, of course, water flow. You have low flow period in the winter, very, very long, with decreasing discharge and decreasing the water level. Because there is of course, all snow is accumulated on the watershed, and all the groundwater and depleting lakes are fed the rivers, actually. And then during the melt, you have very nice decrease in water level, and then decreasing depending on the continentality of the river. You may have the second flood during the summer, or you will have, like for Kolyma River in extreme continental Arctic, you have only the snow which can contribute up to 70% of the flow at annual scale. And this seasonality is very important to take into account, because in the Arctic reaches the seasonal variability magnitude of water level can reach about 25 meters. This is records, in situ records. So I will explain you why. I have one case very strange on the Lena River. Yeah. And you see here, I searched for other locations, and I found for big rivers in tropical areas 12, 15 meters of seasonal variability for several big rivers. Of course, 25 is not everywhere, but it exists. So for my knowledge, this is a high magnitude, seasonal magnitude that I found. Probably you know other places, but me not. Large amount of wetlands and lakes on the floodland, you see, and on floodplains, sorry, and watersheds. You see here in the Arctic, due to its glacial history and due to the permafrost existing now, and due to the water thermal low thermal resources, lakes and wetlands are widely spread. These figures show you. You see? No, you don't see. Yeah. Oops. Yeah. You see here the distribution of the lakes number and the area by latitude, and here we have some presentation of the special distribution of the lakes according to the famous global wetlands and lake database. And what is the impact? Impact actually very, very clear. For rivers with a large amount of lakes and wetlands, the spring peak is lower comparing to the rivers, for example, with lower amount of the wetlands. So the rivers with large amount of lakes on the watershed and on the floodplain are regulated by these objects, these water bodies actually. The peaks are attenuated, but the length of the flood is extended up to several months, like on the Ob River, where I put here in average more than 35% of wetlands and lakes, but actually at some places it reached 70% of wetlands and lakes on the watershed. So, and you see the river here has very long flood actually. Why I mentioned this here, because actually starting from 66 degrees of north, we have only polar orbiting satellite, which provide us with the water level measurements with a periodicity of 35 days for old missions and now 27 days for Sentinel-3 missions. Actually, we are able to monitor the water level variability and discharge, retrieve the good annual variability of the discharge using polar orbiting satellites for rivers having this type of flood, this type of seasonality. But of course, with this temporal coverage, we miss a lot of peaks during many years if the river has very peaky flood. Ice also impacts the water level variability. Here I said on local scale, but also on regional scale. You see, for example, the scheme, how it impacts during the freezing. During the freezing, when the freezing front propagates from the north to the south, so the freezing, if the river has meridional extension, like most of them, except probably several like big, like Yukon, the freezing starts from the north and propagates to the south, and flow is in opposite direction. And when the flow meets the ice edge, so we can observe the backwater effect, which is actually is not supported by the variability by the increase in flow. So we should to take this also into account when analyzing the variability, the relationship between discharge and water level. And you see also in many places now, the agencies doesn't provide measurements during the winter. So I thought this is a problem of the Siberian Arctic, but not yet. It's also a problem of Alaska in many sites in Alaska and Canada. As I told you, we need to take, during the winter, we need to take into account the presence of the ice because the presence of the ice modifies the vertical distribution of the water velocity field, and some line of maximum flow is could be found somewhere in the middle of the water column. And here I present the famous Manning equation, which is in some assumption that now is widely applied to open channel flow with altimetry, and in the future, probably now by specific teams with SWOT measurements. But actually here we should, having another border on the fork, we need to add another frequency term related to the ice, and also the presence of the ice modifies the geometry of the wall section. Actually, we need to know that here the wetted perimeter, not only the bed perimeter, but also we need to add one more parameters on the top. It may modify our discharge and water stage relations, of course. During the winter, it has an impact. And you see, for example, the increase of the water level, which is not related to the increase of the discharge, but it is related only to the installation of the ice that I demonstrated on the previous slide, can be observed not only in the gauging station, on the ground station monitoring, but in many places with observations of the JSON. Be careful, not with observations of polar orbiting satellite. We can also find this increase in water level during the installation of the ice. Impact of so all this specific that I mentioned, how they impact on our measurements of the water level and retrievals of the discharge in the Arctic. First of all, I would like to highlight that in many places, me and also I've searched in other data bases, my colleagues retrieved the water level time series of very strange shape. When during the winter we have highest water level elevation, here I highlight, I showed the ice period by black line here, and you see that it's like very strange seasonality when during the winter, when all water is immobilized on the watershed as snow, we have highest water level here. So it was retrieved for many places, especially with the conventional altimetry, and now it exists even on the open databases. And you see, it was one of my retrievals, and for some of these places, we can, by applying specific Arctic filtering approach, to retrieve water level somewhere to find these real measurements. But for other places, I think like here, we are not able to retrieve the real measurements. So these actually, this forced seasonality should be taken into account. In the winter, you should have the lowest values, but not highest like here. But the things, it's not true for everywhere where you may find the ice and snow. So it is the situation in high Arctic, above the 66 degrees of north, because in subarctic areas and in boreal areas, you may find several cases when the winter water level can be comparable with the spring water level when the snow melts. It is possible in some Arctic areas if you have, for example, changes in water and ice regime due to the changes due to climate changes, when the melt episodes are alternated by freezing episodes, so it's rather in some Arctic areas, and also due to anthropogenic seasonal flow redistribution, like for example here in the basin of Nelson at Churchill Rivers in Canada. I downloaded the gauging station measurements here, records, and you see the winter. In the winter, the agencies empties the reservoirs, preparing to the flood, to the filling during the flood. Actually, and almost during all winters, the water level exceed the same or exceed flood values. So, and if you are interested to the climate change, you are welcome to see the poster of Krylenko, which I will present tomorrow. Massive water release that we expect in the high Arctic will provide us with the highest water level. Actually, when I started to work with the modelers, with hydrodynamic modelers, and we started to compare our water levels with the modeling results, we found very, very interesting places on the Middle Lena River, also 66 degrees north almost, when we, during 3 years, 2018-20, we had peak cut during 3 years in this specific location for around 300 or 400 kilometers. All tracks were cut, provided us with these strange measurements, and actually the situation was improved after 2020 or 2021. Now we have more or less good measurements, but our model unfortunately ran before, and we couldn't validate it correctly because we had only 1 year for calibration and validation. Yeah, but this is negative thing, but for positive that for other rivers, for example, with high seasonal magnitude, in the framework of hydrocoastal project, Karina, for example, could retrieve the water level measurements up to 70 meters of seasonal magnitude using the hydrocoastal processing scheme of Sentinel-3 from L1 up to L4 level of data. So the same on the north of the river, I think with 2D model, time-space model, using Cryosat and Sentinel-3 and Altica. Yep. Yes, and Altica as well. She could retrieve, not for all years, but for many years, the peaks of good seasonal magnitude. Large amount of wetlands on watershed regulates our shape of our hydrograph, but also wetlands are widely spread almost everywhere throughout the Arctic on the flooding plains, and they provide us with well-known so-called off-nadir effect and result in wrong retrievals of the water level elevations. Here, for example, you see very often we may see the line, the cluster of points which always track the floodplain elevation, actually. If you have 1-2 points, you can just classify using statistical or different approaches, them like outliers. But if you have 50% of points measured at the same cycle at this virtual station, like that catch the objects, water objects on the floodplain and on the rivers, your retrievals will be overestimated, like we had, for example, here, where our retrievals are overestimates by 1 meter, actually the points which are really located on the river. So I would say that sometimes automatic retrievals are not optimal, and almost every virtual station I verify manually for these ambiguous values. Sometimes among 5 points of measurements, only 1 corresponds to the channel, and other corresponds to the elevation of the floodplains. And for example, if you apply severe filtering to remove these points, it may result in some strange situations. For example, when you obtain when you underestimate the water level during the peaks, the situation that we had for Nadim River, for example, among 11 among 11 virtual stations, 8 provided us with very low estimates of the flood peaks. And I would say that I observed these really underestimations, overreaches with braiding morphology, and not only in the Arctic. So it was the same situation, it seems, over the Braiding River Murray, Braiding Ridge in Murray, which also, so in one case it was central line, Sword central line, which was designed not well for the Braiding River, but in another case it could be effect of the objects, wetlands and lakes situated on the flooding plains.
Sorry, Elena, can you go to the conclusion and recommendation?
Yes.
Please? Thank you.
Okay, sorry. So just one case, what I would highlight as well that to retrieve the discharge for the Arctic rivers, I usually, since 20 years already, I use the specific rating curve that I develop for ice conditions. But for this, we need actually the flag, to develop the flag of the ice period. And this was done several years ago, always based on the altimetry and Ob River, like test sites. And I applied it recently to the same Ob River, because I developed this data set of the ice phenology to calculate the discharge in the framework of ESA-CCI discharge project. So I will skip here. And actually, hydrocoastal, I provide here several results that we achieved during the hydrocoastal project. These are a global product based only on altimetry. Angelica developed also other product with other rivers based on merging altimetry and optical sensor. And you see 5 rivers here on the Arctic, and the accuracy that we obtained for the water level derived is from the Sentinel-3 for big and medium-sized rivers. And also in my portfolio, I present here the accuracy that we obtained for other Arctic rivers. And you see we are still far from the perfect, from the requirements. Probably because of some ambiguities, some outliers that we are still couldn't filter out using our filtering approach. So all what presented here,
Sorry,
like
Elena, we have to conclude.
Yeah.
Thank you.
Okay, so I would like that on Bodin Dam, I verified for several places. It is still not perfect everywhere. In some places it was corrected, in other places it was corrected in wrong way, comparing to previous data set. So I have several places at least where I detected these problems. Development of ice flagging or ice phenology product also is quite important for calculation of the discharge in the Arctic. So I would advise carefully verify the existing water level time series in the Arctic for this fourth seasonality, when the water level is in the winter is higher than water level during the spring flood. And I would like to see what full focus SAR treatment will provide us in this complex environment in the future. Yeah, sorry and thanks. Thank you.
Okay, so now Angelica has some seat questions, so we'll have maybe approximately 10 minutes before the coffee break for some discussions. And also, if you in the audience have any suggestions, feel free to come forward with them so we can add them to the list.
Yeah, actually, they are very generic for the team, and we expected some recommendation. Sorry, during the presentations, but was not the case. So we hope to open this discussion and continue also in the other session. So actually, we have to recommend what we need in terms of satellite data, in terms of also ground monitoring network. So if you have some suggestion to improve your methodology, your techniques, and your product, this is the room to do. And we can start reading this simple question. But if you have, if you want to interact and give us your opinion, is more than welcome. So, how much are you satisfied from the current satellite products? Of course, the spatial and temporal resolution are the main characteristics, but also in terms of quality of data, accessibility of data, do you have some suggestion that we can bring to the space agencies or the community? Yes, Cedric, thank you.
Angelica, I know you already got us started on your first point, but I wanted to make a comment related to the second point, which is also related to some of the conversation that we had earlier today.
Yes.
I think it's pretty clear from some of the presentations that we saw on the latest capabilities with Nader today that there is still a whole lot that can be done with it. And given that those instruments are more cost effective, they're not cheap, they're more cost effective than swath altimetry. And despite the incredible value of swath altimetry, I'm not saying that we don't need to do that, but I think we also need to consider the value of Nader for the future, particularly when thinking about smaller concepts and constellations. So if that's just to get the conversation started.
Okay, thank you very much. Yeah, Smash. Yes, Nick.
Someone's got to say something. I'm in danger of sounding like a scratch record this week, but my research has been entirely enabled by the capabilities that come from engaging with the commercial sector. So, you know, for me, very high resolution, very frequent revisits are what we need. And, you know, whether we need to build better relations with the commercial sector, because we all recognize, we all state that there's nothing more important than water. And yet, you know, we don't kind of have the means, the money to seem to leverage the best data that we might find application for. So whether it's, you know, whether it's something that we need to continue to rely on the commercial sector, or whether the agencies can match that capability, or if that's duplication, but.
Okay, thank you. Yeah, the problem is that we have to pay. So if the agency pay for us, it's good. Yes. Yes, yes, I agree. Thank you. Any other suggestion?
Just jump to the fourth point on the satellite data, whether there's a need for dedicated,
yes,
easy accessible inland water altimetry. And I think that's a really important point. We talk about a lot of data, massive amounts of data, and now we have to download basically all of it to just process very small parts. And so I think if, especially for altimetry and nadir missions, if they were easily queryable for different applications with meaningful attributes, that would really revolutionize how we get started with working on the data and how much we can actually accomplish. So I think, yeah, a database would be really an improvement. Thanks.
Thank you.
least I can give a partial answer to the last question. At Human Central Sentinel-3 and soon enough for Sentinel-6, we have the data store, the Human data store, which you can query on time, latitude, longitude, and very soon even cut the data to your right size. So you will get a product tailor-made to your little area or time of interest. Oh no, very soon. That would just mean a change in the software, in the user side software that is under development. Maybe it's even out already. But and soon when Sentinel-6 will also be on the data lake, should be still before the end of the year. In fact, if you would know what the collection numbers are, they're already there. You didn't hear that from me.
Very quick one. I always have to be a bit provocative, but I like the swimming pool one. I think the speaker thought he pulled a joke. But I think it's not a joke. I think what we forget, and this was exactly what was just said here, the data store. You get a tailored product to your needs. Now, who has the needs? Do we know? Because actually the swimming pool point is a very good one. Because there would be governments paying a lot of money to get an altimeter point of people when they shouldn't fill the swimming pool. So I think, I think we need to work towards getting the people in it that would pay for a service or product, that are not scientists, but people that are driven by the application need. And I think we very often forget that there may be a person out there right now wanting that data more desperately than actually we do, or maybe as desperately, but that would be willing to pay for that service or product. So just as a thought-provoking message, the swimming pool, I think, has the answer. Seriously.
Are there more points?
Hello. So in my team, we are currently analyzing very small surfaces of water, maybe smaller than 100 meters. And we are using Sentinel-6. And so this means using the OOLTC, but it doesn't have enough data about the surface or the elevation of the water. So we lose a lot of measurements. We cannot study small rivers because they are not inside the OLTC dataset. So it would be really great if this could be improved in the future.
Thank you.
Hello. Yes, I have a similar topic. I think it's about in situ data, but about center lines, either rivers, but also lakes. And the slope study showed if we had better center lines globally, we could do a lot of better and more accurate computations and results. And also for lakes, I've seen a lot of, for example, Arctic global study of Arctic lakes from ISAT or from some other sensors, but in the Arctic, the center lines of lakes are of very poor quality, and the results are not very good because in that specific location there is no lake. But the global database said there is a lake, and yeah, that's a huge problem. So I don't have the answer how to get the center lines, but if we had a good data set, it would help to improve.
Thank you.
Kind of related to that one, river cross sections. So, you know, we've been using drones to measure river flow, doing velocimetry for quite some time. To calculate discharge, you need the cross section. It's the same when we come to satellite, whether we're using velocimetry or some other technique. So, you know, building up a network of river cross sections around the world would hugely advance our cause.
Thank you. So are there any more points? Or should we break for coffee?
Yes, let's go.
Okay, so I think let's give a hand to all the speakers in the session, and then let's go have a coffee.
Thank you.
Ten minutes late already, and I would like to introduce our first speaker, Jean-Christophe Poisson from CLS, France. He will speak, and he will, sorry. He'll speak about fully focused SAR altimetry and innovative river level gauges for coastal monitoring, the full focus SAR coastal project. Yeah, welcome.
Thank you, Elena. So I'm Jean-Christophe Poisson from Vortex.io. We work into this project, but I will present on behalf of the project. Normally it was David Cotton, but he was not able to join, so I will try to present as well as him the project FFSAR Coastal. So the main objective of the project was to apply the SMAP processor, which is a fully focused SAR processor developed by CLS, on Sentinel-3 data, Sentinel-3A, 3B, to evaluate the potential of FFSAR on altimeter data in estuarine region to contribute to coastal and estuarine monitoring. So in the frame of the project, we select two different environments, two different targets, pilot site, I would say. So the Severn Estuary, which is a highly dynamic mixed tidal estuaries environment, and the lower Rhone Delta and Camargue, which is a low-lying flat river delta with a lot of wetland environment. So this project was funded through the EU for Society Open Call by ESA. So the DTU was in charge to apply the SMAP processor to Sentinel-3 data and to perform the analysis of Sentinel-3 data and FFSAR data to identify the optimum processing choices. And then we validated this processing with respect to in-situ data. And so Vortex was in charge of this, installing these in-situ gauges in order to validate the data, but we also perform drone campaign in the locations. And then the idea is to make a strong link with the users in evolving the users of this region, these both regions, in order to see with them if there is an interest in the FFSAR processing for their applications. So the two locations in the Severn Estuary and the Rhone Delta, you can see the Rhone Delta. So you can see the two estuarine regions here. So we installed 4 in-situ gauges just below the Sentinel-3A and 3B tracks. So you can see the data of the 2 gauges. In the up area, you can see the gauges on the Severn Estuary, and you can see the strong tidal signal, very strong. And in the bottom, you can see the data from the gauges in the Rhone Delta. So in the Rhone River, but also in small canal close to the bay. And you can see that the effect of the very, very small tidal effect of the Mediterranean Sea and the more dynamic, the less dynamic that they have in the Mediterranean Sea. We also performed 2 drone campaigns at the same day, at the same time, and the same location of Sentinel-3 track. Of course, we're trying to perform the flight at the same time, but it's difficult to follow a satellite that flies at 7 kilometers per second. But it was at the same day, at least. So we performed the first flight by connecting the 2 gauges of the Severn Estuary. So we fly over the whole estuarine region in the Severn Estuary following the Sentinel-3 track. And on the Rhone Delta, we performed the flight along the 2 different Sentinel-3 tracks. So one tracks following the Rhone River, and the other track following in the bay and inside the canal. So concerning the FFSAR activities, so DTU first applies the SMAP processor to Sentinel-3 and 3B data. With the first results, they identified the optimum processing choices in order to generate the final time series of all the data from the selected track. Then we perform the validation against in-situ data, against also tidal models. Evaluate how well the FFSR altimeter data can resolve the fine-scale structure and features of the different environments. And we have different conclusions on the two different environments, but I will go further into the following slides. So concerning the FFSR processing options, so the first action was to select the best retracker for FFSR processing. So DTU performed the analysis of 4 different retrackers: the retracker called PTR, the retracker called multi-PTR, the OCOG retracker, and the MWAP retracker. So the MWAP is a retracker from DTU, and if you want to have more information about this retracker, you can contact DTU directly. So the final choice for both locations was to account for an illumination time of 2.3 seconds and to have a posting rate of 1000 Hertz. And this was the MWAP retracker that provided the best results and that the retracker that has been selected in the following of the study. One thing what was very interesting to see during the analysis of the Severn Estuary was the fact that with the high tidal effect, there is all the coastal area dries out at low tides with very wet sands, and it's enabled and it's impact the FFSR signal by a snagging, a very strong snagging into the WSC signals. And so we can see here the hyperbola curve that we can see, and also the different water level due to the high tidal effect. We also process the entire track between the two micro gauge installed at the beginning, at the end of the estuarine region, following the Sentinel-3 track. And we make the comparison at the two different locations. So the location in the north in Newport, in the estuarine region, in the river falling into the estuarine region in the Severn Estuary. And also at the beginning, more in coastal data, there is a strong dries out effect. And you can see here that there is a flat line in the data, which related to the fact that the in-situ gauge was installed in the dries out area. And so sometimes it's totally flat. Maybe it's not very visible on the plot, but you have in very light gray all the measurements on the in-situ data. And we compared and we superimposed the FFSR data here with different processing. Generally, we have a very good agreement, but we have a higher MSE in this area because it was very difficult to have a perfect synchronization between FFSR data and in-situ data. Because with this high tidal effect, if you are small minutes of difference between the two measurements, you can have a strong impact on the WSC. And if we look at the OCOG retracker, we saw that there is a bigger RMSE, of course. So that's why they selected the MWAP retracker. Another thing, what's very interesting in exploring the signals in the estuarine region is that the FFSR is able to see the different slope due to the tidal effect. So DTU for that process the data at the highest rate, then perform some smoothing at 80 meters and then at 120 meters and remove the snagging effects. And they can see different sea level slopes for different passes, depending, of course, of the different tidal conditions. So we can see the slope of one tide and another tide at another difference. And it makes 1 meter difference in water level over 20 kilometers. So it's a strong slope, very strong slope. That was amazing to see it, thanks to FFSR data. DTU also investigate the FFSR signals, especially the tidal signals. As we can see that we are very impacted by these signals, and we can see very well these signals. So they compare the signals measured by the FFSR to the M2 tidal model. And they show that we have a very good consistency between the two, and even more because we can see small signals that we can see in the FFSR data that we cannot see in the model. So there is interesting high frequency resolution not seen in a phase 2014b at 8 kilometers of resolution. So we don't know what are this fluctuation, but we can see that it is a high frequency geophysical signal maybe. So I don't know, maybe its amplitude variations are related to flow around this island. We don't know, but we can see this these small features appearing in the tidal effect. On the Rhone Delta, on the other project, other pilot zone, the Rhone Delta is a very low-lying river delta with a lot of wetlands surrounding. So it's very calm water, and the tidal effect is very, very low here in this area. They use FFSR with a resolution increased up to 0.5 meter in this area. So the gauges were installed in the red point here, and when we compare the FFSR signals to the tide gauges in these two areas, we can see a very, very good agreement. And what was very interesting is that these two locations were selected because there is a small canal that is in the location, and I think we illustrated in this result the capability of FFSR to retrieve a good water surface elevation in very small targets, as François demonstrated just before the break. But we can see a very good agreement with the in-situ gauges. So this is a very interesting result from FFSR also. So to sum up, so a lot of work has been performed in the frame of this project. So an optimal FFSR processing option has been found on the Severn and the Rhone region. We have a very good agreement between in-situ data and FFSR data also with the MWA pre-tracker. FFSR demonstrates the capability to measure water level in very small targets, but it's something that it is confirmed here. The FFSR also is able to measure small-scale water level variations, and we can see a variation below 10 centimeters for the Rhone River, so it was very interesting and confirmed by in-situ station. Track screening in parallel to rivers offer detailed information on river slopes. It is similar that François showed on the Marmande River before, but we can see that if we have the good geometry, FFSR is very good to retrieve the slopes. And tracks across estuaries can be used to estimate along track slope, so in which it is very useful for tidal analysis. So when we come to recommendations, so the FFSR coastal processing recipe. So if you want to reproduce the results with the MWA pre-tracker, you have to account for a 2.3 seconds illumination time and 1000 Hertz posting rate. There is a guideline for use FFSR altimeter data. And one thing I forgot to mention is that all the data that we process and we produce in the frame of the project is freely available on the website that I will show later. In-situ data, including FFSR data. And further research for FFSR processing, so different coastal location and environments, multi-satellite study that can be very interesting for sea state impact. Of course, using FFSR on extreme events, we have to be lucky to catch an extreme event with FFSR, but it could be very interesting to look at extreme events with FFSR processing. Isolating Nadir reflection, intertidal bathymetry, that can be very interesting, also to compare with ISAT2 data. The interface between inland water and ocean, which are in eastern region. Small-scale variability in tides also that can be investigated thanks to FFSR data. We recommend also the use of micro gauge for satellite data validation because it works very well and show that very good agreement with FFSR data. The use of drone with LiDAR for research and satellite data validation. The users loved this drone solution, so that was very interesting. And concerning FFSR and FocusSAR altimeter product, so develop a proposal for this BOSS product in coastal product over priority areas. We saw that the users were very interested in this data and didn't know the existence of this processor. So they were very interested by using this data. But they have to be trained to this data, and they are not experts in radar altimetry. So we have to process the data and to learn them how to use it. And we recommend also to further develop FFSR processing for narrow rivers and to look for other inland water locations where other SAR altimeter processing fails. So FFSR can unlock the possibility to exploit data wherever standard SAR altimeter will fail. So this is the final output and my last slide. So you can see the data sets. You can download all the data sets, both in situ and satellite data through the site of the CCO. So you have the link here. So you have Sentinel-3A, Sentinel-3B, and in situ data from station and drones. You have also the product validation and evaluation report available on the website directly with the evaluation. And we also issued an application roadmap with all the recommendation of FFSR in coastal monitoring systems and also all the recommendation from the users. And I think that's all for me.
Thank you very much, Jean-Christophe. We have time for questions, please.
Try to do my best. I'm not David Cotton, but try to present as much as him.
Yeah.
Okay, thanks.
Thank you very much. And this next speaker, Angelica Tarpanelli, will present an integrated approach for estimating river discharge by leveraging near-infrared sensors.
So this presentation was done by Paolo Filippucci and with my contribution and also the contribution of Debbie Prasad-Sao. And actually, we introduced this concept of essential climate variables, so that actually they are the indicators that describe Earth changing climate. And for the first time, GCOS identify the river discharge like an ECV because it's very important for not only for water management and related services for flood processing, but also to adapt and identify the potential effects of climate change. So we know that from in situ station is difficult sometimes to derive long time series and to calculate the trends. So the satellites can be a strong support. And with this project, CCI River Discharge, we have this first precursor project to identify if it is possible to estimate river discharge for the climate change assessment. So the methodology is I want to precise that the project will be presented in the last presentation this session. And this is one part related to the estimation of river discharge by the using of optical sensor. So the methodology was originally published in 2012, and it is based on the fact that if we look at the close to the river in an area that can be flooded, this area has a reflectance that decreases with increasing of the water. When the water decrease, the reflectance increase. And this is not the same for a bare soil or urban area, because we use these differences between the bare soil and the water, clean or turbid. And so if this is mainly the concept, the originally concept. Of course, with all the noises of the satellites, we don't have this perfect signal. So we need to manage, to play with these two signals. And if we look at the ratio, we have exactly a proxy of variation of river discharge during flood. If we use this in the index, like a rating curve, the usual rating curve with the water level, we can use the same signal with the river discharge, and what we get is the river discharge even if we don't have in situ station. So we can calibrate the relationship, and then we can use it. During his PhD, Paolo developed this new let's say, the improvement to the methodology by including two other parameters. One is very important, and it is related to the sediments, because the water change color, and if change color, it is very close to the bare soil. So we need to calibrate and tune this M pixel, that is the measurement pixel, with respect to the water. And the other parameters is the vegetation, because sometimes the M pixel could be very vegetated, and so the signal could be affected by it. So actually what we have to do with a simple image is to identify every land use differently. So city, roads, bare soil, forest, fields, when we have water, and each of it has a specific symbol. And of course, all of them are not related to the M pixel that we have to calibrate, because it's the pixel related to the real measurement that we need. So actually what we have done is to identify some classes for wet areas, some classes for the C, that is the bare soil, the calibration pixel, very stable, some classes for the V, the vegetation pixels, and also the classes for the water. Finally, we have to identify the measurement M by calibration with the in situ stations. So for this project, we started with the use of Landsat 5 and all the other Landsat 7, 8, 9. We used also MODIS Terra and Aqua. We used Sentinel-2 and some harmonized product like the Sentinel-2 plus Landsat 7, 8. We use Sentinel-3 Olchi, and we are trying to use also Envisat with MERIS. All of these sensors have different spatial resolution and temporal resolution, and they are managed also with different platform. So you can imagine that for each site we have to manage a number of image very high. So we need some cloud performing tool. And so for most of them, we use Google Earth Engine. And in some cases, we use Sentinel Lab. And for Envisat MERIS, we are trying to using Earth Console. So one of the problems to manage all these data sets that are quite different is the spatial resolution. So when the river, in the figure, you can see the different spatial resolution from Sentinel-3, for example, the bigger, until Sentinel-2, that the smaller. And of course, when the river is big, we cannot use Sentinel-2 like this. But we have to aggregate the data. And so the methodology is further complex, make more complex, because we have to aggregate, and sometimes it is not obvious how many times we have to aggregate the data. And the same for temporal variation. Sometimes we have to manage rivers like this that are very dynamic. So if we look at a single pixel for a long time, for a long period, probably we don't have any more water in that pixel, but we could have land. So in this case, we have to try to calibrate and use these data sets 2 years by 2 years by making some period in common. So just a few numbers of the analysis that Paolo did. We have 2 ways of aggregation, what he called kernel. We have 3 approaches. One is the original one, C over M, and the other 2 is C over M with W1. That is a way to estimate the water pixel, and W2 is another way to estimate the water pixel. I don't do the detail. We have 2 kinds of vegetation, if we include vegetation or not, and we have 2 calibration approach, full or 2 years in 2 years. For 11 products, we have like, and for 45 sites, we have like 11,000 experiments. And if we look at the images, what the results is that we have to manage 26 million of image to analyze. And these numbers are not so easy also to get some conclusion from them. So about this experiment, today I want to show you just the analysis for some cases, and because we focus on the data in which we have the recent period of in situ station, and for which we have at least a long time series of data, because we have to calibrate each single missions. And so what we have done is first, this is not easy to understand as a result, but on the left, you can see the Spearman correlation between the simulated, let's say, to the reflectance indices with the river discharge. In the y-axis, there are the sites. In the x-axis. In the y-axis, you have all the algorithm for the 2 period of calibration, full calibration, the first, and the 2 years in 2 years, the bottom. And the color are meaning the value of Spearman correlation. These are the results just for Sentinel-2 and for Sentinel-2 analysis. And so already you can see that we are mostly satisfied about the correlation because it's quite high, even if there are some sites highlighted in blue in which we have still some problem. In the right, you can see the differences between the full calibration and the multi-year calibration. And so with this kind of differences, we are able to select which is the best for this site, for this algorithm, and so on. The next step is to use the same graph, but once we have identified the calibration period, we look at the aggregation. So it is better the kernel 1, kernel 2, and so on. And again, once identified the kernel, we move to the best algorithms, the original one and the modified one. And finally, we get with a conclusion if it is better to use the vegetation or not. So after this long process, we are able to identify the best algorithm with the best calibration period and the best and the best and the best until we have a reflectance product that look like this. So actually here you can see all the sensors in a long time series of the Mississippi River. It is not so easy to see the in situ station that is in gray below, but we are quite satisfied of these numbers. Of course, we miss some peak, but this is the limitation of the procedure because we are looking at the optical images. So during flood, we have clouds and we cannot see the river. These are all the products independently and separately. We are working on the integration procedure. Actually, when we submitted the abstract, we're too much optimistic. So we are still working on it. And this is a simple way to merge just by using an average and a moving average filter to remove the jump. And already we get, as you see in the last row, we get very good correlation that could be good in the middle of the single sensor. But Paolo is working also on some machine learning approach, and with random forest, we already have some good results. So there are space to improve the approach and the methodology. So next step, of course, to finalize the processing of satellite data, we have to finish to process Sentinel-3 and we have to start to process MERIS. We are still testing the artificial neural network, other machine learning techniques to obtain the multi-mission time series, a single multi-mission time series. And we have to apply this methodology also where we don't have this long time series of data. And in this respect, Paolo is working on a procedure for uncalibrated approach that is quite good. So maybe next time you will see the results. And some recommendation for you, maybe, is to continue to invest in the multispectral data because provide a clear and useful information to estimate variation of river discharge. Improve the platforms for big data analysis, especially for fostering the multi-temporal analysis. The problem of this big cloud platform is that they are very good in the spatial analysis, but not so good in the multi-temporal. So we have a lot of problem also by using this data in time. Of course, improve the quality of raw data. We had some problem of georeferencing the images and to try to make synergies with other communities for the use of auxiliary data. We need cloud masks. So, and we are not able to do a cloud mask. So probably some community of atmosphere and so on can help us. And finally, to invest in the use of possible applications of this kind of approach, not only for climate change initiative like this project, but also for other other applications like weather management, flood forecasting, and interaction between coastal and inland water. So thank you very much. If you have some question, you ask first Paolo Filippucci and then, of course, also me. Thank you.
Thank you very much, Angelica. We have time for questions, if you please.
Thank you for your presentation. If I understood correctly, you compute the discharge from the reflectance,
yes,
and you show that the reflectance is linked to the presence of water.
Yes.
So in fact, you link the discharge to the width, more or less.
No. This is, I presented this work in 2012, and always the same question, because actually I don't look at all the river. I look at a single pixel at the beginning. Now the mask take into account more pixels, but we are looking at the variation of reflectance. That is different of variation of width. So it is nothing geometrical. It's something related to the signal that we get from the satellite.
Other questions? I have one. When you start with a new site, do you do some classification of land covers or automatic or manual? What is the beginning? How you can enlarge the application of your method?
No, Paolo make everything automatic now. And so when he start looking at one site and start to look at different stuff. So with the NDVI, he is able to understand the wet area. And so he used this area to select after also the water pixel. For C, he go to the coefficient of variation. For V, he go again with NDVI and so on. So once he has the box, he continue to do some math between bands to obtain some classification. So we don't use the classification from anyone outside, but he process everything, and now the process is almost automatic. So if you put the the coordinates, you can have more or less everything, but in a long time.
Automatic,
So
yeah.
it's automatic, but it's long process.
Okay, thank you.
Thank you.
Other questions?
You mentioned that to apply the method, the coastal inland interaction is not very much different on the coast? For applying this method on the coast?
No, we don't apply, we want to apply.
Yeah.
In the sense that what we want to do is, because we are able to estimate river discharge from the inland water, we can use this information to understand how the river discharge can interact with the coastal. But
I was thinking that my question is, at the coast you have a lot of other things, waves and so on. This will not interfere on the...
No, but we have to study this kind of applications.
Okay. Thank you very much.
Thank you.
Yeah. So we switch to another speaker. Daniel Schrerer from TUM University, Technical University of Munich, will present estimating discharge of narrow rivers using satellite altimetry and optical imagery.
Yeah,
Please.
Thank you very much. Good afternoon. Nice to see so many faces still around. Yeah, we heard a lot of discharge already. So now I really want to focus on very narrow rivers that are maybe not so easy to detect with classical optical sensors. And also, I want to emphasize this is always designed for ungauged basins. So we really want to quantify the uncertainties in a very realistic way, physical based. Of course, we have now SWOT. So why do we actually continue in producing discharge algorithms? But we want to leverage the amount of remote sensing data that's already available before SWOT, and to derive 20 years of discharge data in this study, starting with JSON1, and then of course continuing with Sentinel-3 data. That's really the first data that's sufficient to obtain water level estimates at narrow rivers. And we already started with a discharge algorithm like 2-3 years ago, but I often get the request from the hydrologist side. They are really interested in the narrow rivers, in the ungauged rivers, not in the big streams. And so we really want to focus here on this narrow rivers. And as I said, we don't want to have the requirement for any calibration, but quantify a really realistic uncertainty in the end. So right now, our fundamental equation is the Manning equation. That's maybe not the most sophisticated, like there are new approaches like VDA or BAM or GeoBAM that are maybe more sophisticated, but in the end, they all somehow require information about the river slope, the geometry of the river, the cross-sectional geometry, or just effective width. And of course, also some quantification of the river roughness. We heard a lot about river slopes today already. So this quantity is quite good observed now. We use river slopes observed from ESA-2. Then the geometry, which is the biggest part of this presentation, we derive it from satellite altimetry and high-resolution imagery. And then in the end, we have to estimate the roughness that cannot be observed from space, of course. So we use the principle of mass conservation, like many other approaches already do, and just optimize these roughness coefficients at many stations to minimize the difference between those stations. But of course, this introduces a high uncertainty. The basic framework I just want to highlight this is, of course, based on the SORT database, a really great data set. And maybe already a recommendation now, it would be also nice if the similar data set or the SORT data set could also include rivers smaller than just 60 meters in width. I think that's right now the limitation. So let us take a look at our study site. It's the Ueme River. I'm not sure about the spelling, sorry. That we just got a request to process this river, and if you just take a look at the Landsat or Sentinel-2 resolution, you can still see the river, of course, but quantifying differences in width gets quite challenging from this coarse resolution. So we switched to 3-meter planet scope resolution data. That's of course great. It has a really high temporal and a really high spatial resolution. So we get for every day we can get an observation. We don't need to mask clouds. We just take a look what scenes are cloud free. But we have a really limited quota to download. It's not so nice to work with. So we cannot really scale this approach right now. And what is most important, we have less spectral resolution. So we only have like 4 or 5 bands and not the shortwave infrared bands we are used from Sentinel and Landsat. So we had to develop a new approach to classify water at first at high resolution. Here we use then the segment anything model, SAM, from Meta. It's a deep learning image masking model. And it provides 2 different applications. I will show you in just a second. And additionally, we also just developed a classical NDWI because for that we only need the near-infrared channel. So to the right, you can see the traditional NDWI band, so to say. And to the left, you see an RGB image, but we exchanged the channels for near-infrared, NDWI, and red because we experimented a bit with those combinations, and we saw the biggest contrast in this band combination. And now with to the left here, with the SAM deep learning model, you have 2 possibilities. You can either use this SAM predictor, but it needs like a number of labeled points that are in your area of interest and some that are outside of your area of interest or outside of your feature that you want to classify. And then on the other end, you also have this generator approach, which just generates a lot of masks, actually much more than you can see in this image because I got just out of colors and couldn't picture it better. But it only needs 1 labeled point inside the feature you're interested in. And then to the right, we also have this very classical NDWI thresholding approach just to classify water there. And in the end, we get 3 individual water masks and we can sum it up and then we get a final water mask. And the nice thing about this approach is it just takes 50 seconds of time if you're running with a GPU and CUDA. So that's a quite robust approach now to calculate water, and it doesn't require a big spectral resolution. That's very nice. What we also need to calculate discharge in the end is, of course, water level time series. Here we use water level time series from Tahiti. Nice thing is it's multi-mission cross-calibrated already. It's corrected for everything you need. And we can now also correct for the slope. As we heard, we have a lot of high-resolution slope data now. And then we can also combine multiple virtual stations within a reach by just adjusting for this slope. This, of course, introduces an error that we then in the end add to our uncertainty estimates. And when we have water level and surface area observations to the left, we can make an hypsometric relationship between the both of them. Here you can see nicely just that we don't need a lot of images to derive this. And what you can also nicely see on the left in the color coded, that the time lag is really, really low. And we did this before with Sentinel data and Landsat data. We often had like time lags between above 10 days. And now we nearly most of the time have a water surface image for exactly the date when we also have the water level observation. And then from this hypsometric curve, we can derive the bathymetry, as you can see in the middle. And here we took a look at two AOIs, but they are more or less really consecutive. So there's not much between, it's just some experimenting. And then to the right, you can see those 5 cross-sections that were extracted at all the sort nodes. So we have those sort nodes that just define for us the cross-section position and also the cross-section direction. So we can just derive the normal from the sort center line. And of course, we can only extract the bathymetry or the cross-sectional geometry up to the lowest point of or lowest water level that we observed, and below that we use this empirical width to depth ratio by Moody and Troutman, which is sadly not really transferring well to braided rivers. So right now we are more or less constrained to meandering rivers. Next on, as I said, slope. We heard a lot of this. So here we use this ARIS data set. You can see it's a nice global data set that we developed. And so we are not limited by slope observations. We can just apply this approach to anywhere we want. And the nice thing about it is it gives you also extreme slopes, so the maximum slopes that it detected and the minimum slope that was detected, and that we can also, again, use for the uncertainty in the end. If you want to see more about this, you can see our poster number 74. In the end, as I said, we now have to optimize this roughness coefficient, and here you can see we give it very loose bounds. So these are the boundary conditions. Of course, somehow we have to define them, but they are from 5 to 30, which is very loose, I would say. And you can see there are different local minima. So the optimization algorithm first found a local minima above. So this each line just represents, just connects the results for each cross-section for each run of the optimization algorithm. And here to the lower end, you can see what was in the end the optimal result. And all the dashed lines, they are rejected by a thresholding algorithm, so they are not used for the uncertainty estimation in the end, but all the solid lines, their variation is then used in the uncertainty estimation. Yeah, as I have written on the lower part, we also vary this roughness coefficient by the river depth. So the discharge is always calculated by section. So the cross section is again divided by vertical sections, and the deeper this section is, then we adjust this roughness coefficient. Let's take a look at the results. Here you can see it works quite nicely for this Orime River. This was more or less the first shot. We didn't, yeah, of course, we say we want to have it uncalibrated and without prior knowledge, but of course we have to validate it, and then always there's a high risk for observational bias that you just adjust the boundary conditions here. But this was really first shot, and that's quite nice. You can see it's only 8% NRMSE, and there's a good Nash-Sutcliffe efficiency, but you can see those very high uncertainties. And from the next slide, we see where these uncertainties come from. So the blue line is, as I said, the total uncertainty, and then the other colors are the individual constituents. So we adjust, so we have our standard run, and then we adjust all those constituents for our maximum and minimum values. So, for example, we just vary the water surface slope, then we vary these roughness coefficients from the optimization algorithms for the maximum and minimum roughness that was estimated. And the biggest contribution is most of the time actually the cross-sectional geometry and the unknown riverbed elevation. So that would be also maybe recommendation to look into river depths estimation from maybe from ESA-2 at very low water levels. Maybe it would be feasible in the end, or other approaches. Yeah, and also of course we somehow propagate those water level errors. So when we correct the water level for the water surface slope, we also use these slope variations that we used before here, also for the water level as an error. Here you can see how it transfers globally. So this is, we would like to take a look at more global stations, but this is mostly limited right now by this PlanetScope free scientists plan that we use. Of course, you could buy a license, but if you don't have a project right now and just want to take a look into it, it's quite hard to get then the funding for it. And I also know that there's an ESA sub-license or whatever, but it really didn't work for us, sadly. As you can see, it transfers quite nicely to 27 studied reaches with 12% NRMSE. Yeah, and especially what's for us most interesting are, of course, those rivers in Africa. I guess it could also then transfer to other stations there where we don't have validation data from GRDC, for example. Yeah. So just to conclude, we estimate river discharge based on 20 years of satellite altimetry data. Using PlanetScope satellite imagery, that's really, really nice to work with, and was no big problem to classify water, even that it has not the spectral characteristics as Landsat or Sentinel. With the segment anything model, we use the ISAT slopes, which are quite robust. Yeah, as I said, right now it's mostly focused to meandering rivers and also not Arctic rivers. So let's stay with the easy cases for the first, and then we can expand it. Yeah, and this approach would benefit from better and accessibility to PlanetScope data or similar high-resolution satellite imagery. Of course, from finer resolution centerline products, from higher resolution slope data, and also from temporal varying slope data that we hopefully get from SWOT, and maybe we can then create a relationship to transfer this temporal variations to earlier times. Yeah.
Okay, thank you very much. Questions, please. We have 4 minutes.
Did I understand correctly? Did you have to combine different, so to say, masks with each other?
I'm sorry, didn't understand.
Did you combine different masks, the water masks that you have generated from these 3 different methods?
Yeah, we combine them just to have a more robust approach. So we use all those 3 approaches. So we have 3 masks, and then we combine them and take every pixel, classify it, every pixel of water that is consistent in 2 or more masks.
Okay.
And then we get also an error from this that we can also apply to the bathymetry.
And then for the channel roughness, you said that you have benefited from mass conservation. Can you show this slide again?
I'm sorry, which slide?
The mass conservation slide where you get the channel roughness exactly.
This one or?
Yeah. Okay, so it's not, okay. Yeah, thanks.
I'm sorry.
Other questions? Yeah, one question about recommendations. You mentioned PlanetScope access and other missions. Do you have other missions in mind?
Oh, I mean, maybe ESA wants to create a new mission or whatever.
Okay, thank you.
Can I ask a quick one?
Yeah.
Hey, that was really inspiring. Very clever approach that you presented here. What's up with clouds?
I'm sorry?
You're using imagery. Now, the vast majority of the planet is covered in clouds. Is that a problem for you?
I still don't understand. Somehow I can't understand.
Clouds?
Clouds.
That stand in the way of visible imagery?
Yeah. So right now we do a manual selection and only select cloud-free days and cloud-free sections. Yeah.
And what percentage of your imagery is covered by clouds?
That's the imagery we use in the end is not covered by clouds.
I understand that.
Yeah.
All right. Thank you.
Okay, thank you. Okay, thank you very much. We continue with other presentation. Victor Pellet from Estelus will give us presentation about satellite-based mapping of river discharge at very high spatial temporal resolution, the Ebro and Po rivers basins. Yes, please.
Thank you. So this presentation was meant to be done by Victor Pellet, but he was not able to come, so I will be doing the presentation for him. So I will be talking about, again, river discharge estimations, but actually it will be a little bit more general than this topic here. We are going to talk about water cycle and budget, water cycle budget. And there is two case studies that we are looking at, the Ebro and the Po Basin. So the idea of this whole work is to use the satellite observations and to study the water cycle. So when we start to look at that, maybe 8 years ago, so we see that all these components, precipitation, evap, river discharge, and the groundwater storage can be monitored by satellite data. The difficulty is that when you are using these satellite data and you try to see if you close a water budget, you don't have closure. So this is a big difficulty. And actually, it's very difficult to say, for example, of group doing modelization, you should use our satellite data because you don't close the water cycle, which is a very important property. So, okay, we have this difficulty to close the water cycle because of the retrieval errors, incoherencies, and many other things. This error, this imbalance of the water cycle is actually not neglectable. Here there is 20% of the precipitation when it's integrated at the monthly scale, and actually it can be much bigger than that. It can be the order of magnitude of one of these components of the water cycle. So it's a big difficulty. But thinking about that, we decided to use this constraint. This is actually, the closure is actually a physical constraint that we can use to optimize the satellite data. So the whole idea of what I will be presenting is to use this closure in order to estimate the satellite observations. So the way we are going to do that is to use some of the inputs. So you see here for one water cycle component, for example, the precipitation, we might have different data sets giving us estimations of the precipitation at different resolutions. And you see already that there are quite a large differences between the different data sets. This is true for GRACE data with different algorithms giving different answers. And for evaporation, it's even worse. River discharge is given by in situ data. As I said, we are going to use the closure of the water budget. So this is a physical constraint that we are going to use in our optimization. And something that is new here, we are going to use the direction of the routing of the water at the surface. And this comes from the topography. So here in this case, it comes from the topography from Merit. So there is a big optimization, and from that, and from this optimization here, I will explain a little bit, we get optimized estimates of all these parameters, and we will see how to exploit these parameters later. So there is a mathematical framework. Actually, we can specify this optimization as an inverse problem. I will not go into the details, but just what is important to know is that it's not difficult, it's quite easy. There is a closed form solution, so there is no iterations. You can really define the solution of this optimization, and we can put a lot of information inside. So for example, this is a term that describes the closure of the water cycle, but we can put anything that we want. For example, if you want to constrain the river discharge to be positive, which is something reasonable, we can do that. If you want to specify the pumping and the irrigation, we can put that in the network of the horizontal transport. So it's a very flexible and easy to use framework. When we started doing this kind of studies, maybe 8 years ago, we started by looking into a basin. So this is a basin, and we have the outlet here, and we were doing the closure at the basin level. A few years after, we had a basin and sub-basins that were defined by some in-situ river discharges. So this gives us some sub-basins where the closure of the water budget should apply. And we have these constraints between the interconnections between the sub-basins that is specified. And currently, what we are doing is to do the closure of the water budget at the pixel level. So it means that we are taking into account all the water components in each one of the pixels and trying to close the water budget individually in each one of these pixels. So from that, we get a full description of the water cycle inside this basin. So you have an estimate for the precipitation, evap, etc. But what we are going to look more closely here is new estimates of the river discharge. So we're going to obtain an estimate of the river discharge in each one of these pixels. And this work, we are doing that at 1 kilometer resolution. So this work, this latest work, has been done under the 4D MED hydrology project that is funded by ESA, and there are a lot of partners. So the goal of this project is to monitor the water cycle at very high resolution, at 1 kilometer over the Mediterranean basin. So the Ebro and the Po are two basins among this domain. In this project, we have a partner, University of Ghent, that is estimating the evap at 1 kilometer resolution. We have also the precipitation by our colleagues in Italy for the estimation of the precipitation. And we did the work of downscaling the GRACE data. I will come back later to this application here. But we have the groundwater storage changes that have been downscaled at the 1 kilometer resolution. So these are the inputs that we are using. But we are also using, and this is very strategic, so this is something that we really require, is 200 stations where we have estimation of the river discharge. So this is a big constraint on what is happening in this basin. So from that, we have a two-stage optimization step. So here it's an illustration. We did this work over the Amazon basin, where we did this optimization. So there is a first step where we exploit the river discharge in situ data, and another one where we exploit the direction of the water, the routing, and we did this optimization. And this allowed us to estimate the river discharge in the river network of the Amazon, and there was evaluation on that, and it was working quite well. We were quite satisfied by these results. There is a paper that was published not long ago. So it's very interesting to see that this is a very huge optimization problem. We have 3 water components, for each one of the pixels. So the number of pixels for the Ebro case study is given here by 3 components. So we have 700,000 variables that we try to optimize at the same time. And again, I want to say that we do this optimization. There is a closed form solution to obtain this solution. The changes that we are doing into the water components are given here for January and for July. For precipitation, evap, and total water storage, we see that our optimization changes a lot over the mountainous regions. For precipitation, evap is, we have similar patterns. So one error in precipitation can be compensated by the evap. And for the groundwater storage, we have some kind of patchy changes that are related to the in-situ data that we have. But we try to take care of that in the method. So this shows you the changes that we are applying when we are doing the optimization in these water components. And now let's try to exploit this data. So once the data has been optimized, all the water components are more coherent with each other. So it means that river discharge, PE, and DS, they should close the water budget. And if you have access to these 3 components, as we do from the satellite, we should be able to estimate the river discharge. So this is one of the applications of this work. So precipitation, evap, and DS, if their signal-to-noise ratio is not too bad, you can exploit that in order to estimate the river discharge. So this is what we have done over the Ebro. The figure is really not that good. It's in a logarithmic scale, but the pattern seems to be quite well, and you will see some evaluation of that. So we did the comparison with a model. I believe it's ESA over Spain that was used here. And you see, for example, that is an interesting diagnostic that the score that we get in terms of correlation is much higher than a model that has been calibrated with a lot of physics inside. And we seem to have quite good scores about the estimation of that. We can also look along the river what we have. So this is a time series of the river discharge at the outlet. And again, you see that we fit perfectly. It's natural. It was part of our optimization, the river discharge. But we are fitting that very well. And in blue, you have the model that is quite good also, but there is some bias errors that are related most likely to the irrigation and the pumping of water. This is what explains these bigger errors. So the method is doing exactly what we are asking to it, and we are quite happy. This is along the river. So these are the pixels from upstream to downstream. And you see here in these points are the in-situ river discharge stations, and we go very well through that, and you have the answer of the model. So the river discharge seems to be quite satisfactory when we are using this method. We did also, we have done some kind of evaluation of the DS. As I said to you, we optimize each one of the water components, including the groundwater storage. So DS we obtain at 1 kilometer. So this is, I will go back to that, but we have this estimation of the DS, and we can compare that to the surface elevation change over some of the monitored basins. And we see that for most all the cases that we studied, we have a correlation with this water elevation that has been improved compared to the original DS estimate. So this was an evaluation. And another, okay, so we have done that over the Ebro. So I present the result over the Ebro basin with the evaluation, but we did that also over the Po. Over the Po, we have focused more on the downscaling of GRACE data. And I'm going to show you some of the plots very fast. Here, so we have done this downscaling. So this is what Grace can give you over the Po basin. You see that it's quite crude. And this is a kind of downscaling that we can obtain at the 1 kilometer resolution. Again, using this exact same framework, which is that can be used for many things. And the way we do that is that we have these indirect observations for, again, the other water components that are used. We need here a little bit more of the model because we need to have a reasonable first guess for the river discharge, and we are using a model in order to get that. But we are also using the river discharge in situ data measurements in order to do that. This allows us to do temporal downscaling. We go from a monthly Grace data to a daily estimate. And then we have a spatial downscaling that is given by here. We compare our product to two other downscaling of Grace, one that is called ETSG in Germany, and another one at a 10-day resolution by the CNES. We seem to be a little bit closer to the ETSG. But you see that we have daily data where some of these products, they start at 10 day. Again, we are not unhappy about these results for the downscaling of Grace. So in conclusion, I think the framework that we put together is working, is doing exactly what we are asking to it. Of course, the solution is not perfect because the observations that we have, they are not perfect. The method finds the best compromise describing the water cycle, considering all the uncertainties that we actually specify in the framework. We give an estimation of all the uncertainties for all the products, satellite products that we are using. We are able, the method is very flexible. We can hit the very diverse set of products at different spatial resolutions. So for example, precipitation and evap here, they were provided at 1 kilometer resolution, but actually we can use different products at different spatial resolutions, and we can handle that. So this is very, very good also. So what we obtain is a full description of the water cycle at 1 kilometer resolution. We have done that now over the Amazon, the Po, and the Ebro, but we could do that anywhere. And the things that I've illustrated here, the applications, is about the estimation of the river discharge and the downscaling of Grace. Some of the things that are very interesting, I think that the estimation of the river discharge estimates that we have, the assimilation of that into a model will be very interesting because basically inside this river discharge, we have information about the precipitation, the evap, and Grace data. So it's a good way to integrate a lot of data into the assimilation. The need for in situ data is capital. This is what constrains our optimization. And with SWOT, that could provide us with river discharge estimates at the global scale, then they could replace this in situ data. Of course, not for a long time period, but we could try to calibrate the satellite data over the grace period and then use that before we have the SWOT data. That will be very interesting. There is an application of downscaling of Grace. So we think at 5 kilometers, we could do that at the global scale, and it will be a nice product. And the water cycle CCI, for us, it makes a lot of sense that such a CCI is not, okay, we take different products and we put them together. If you really want to have a water cycle product, they need to be coherent with each other. And we believe that this framework is a good solution in order to obtain that. And I'm finished. Thank you.
Thank you very much. Very interesting presentation. Questions?
Okay, nice presentation. I have two questions, maybe if I ask quickly. So the first thing is, when you put these constraints, in the end you get some variables like ET, precipitation and stuff. Do you check if they are physically okay, or do you have it? So for example, you have mountainous area in some regions.
Yes.
And your output from, or revised version of precipitation shows something low precipitation over mountains, which doesn't make sense physically. Do you have any constraint on that? The second question is, for many of these fluxes, we have a huge amount of uncertainties.
Yeah.
And one of the biggest one is for grace. When you say uncertainty, you mean uncertainty for one product of precipitation, or you use many different products and somehow come up with the uncertainty, because the uncertainty would be much bigger if you consider all these products of precipitation, evapotranspiration.
Okay. So for the first question, so I mentioned the fact that, for example, we put a constraint for river discharge that are positive. Actually, when we don't put this constraint, we had some river discharge that were negative, and actually, this could be information. It might be the pumping that introduces incoherencies on the river discharge. So these are the kind of things that we could look at. Otherwise, we have done the evaluation using the in situ data. Anything could be done. For the products, we used normally we use as much products as we can. So we have shown that if you have several products for precipitation and you combine them, you always have something better, which is not completely natural for me, but it is a case. It looks like we are really benefiting from putting together different data sets. In this case, we try to have an estimate of the uncertainties for each one of the products. And this is a big challenge because we have no idea, not a very precise idea of the uncertainties of each one of the products, especially because they are state dependent. For high rates of precipitation and low rates, you don't have the same thing. So this is a difficult task to.
So you get the uncertainty from the products, or you calculate it yourself? That's the question.
We can calculate ourselves. Like the fashion way to do that is to use a triple location or these kind of things, for example. So you can use that. Or what I prefer is that we are very clear about some choices that we made. So for example, you say 20 millimeter for precipitation and you specify it and it's very clear. Sometimes I prefer to do like this.
You need in situ river discharge data.
Yes.
But you saw on the slide earlier presented by Omi Delmi that there's not very much in situ river discharge data available.
Yeah.
But why in situ? Can you not take it from space, like from the right side project?
Yeah, yes. As I mentioned, we are really waiting for the SWOT data. For us, it will be a game changer for this particular project. But we have used also altimetry to have these estimates. And we have a recent work where we had estimates using machine learning that were done at the global scale, and we can use that.
Okay, good. So maybe in situ should not be in bold.
Still, it's important.
Because if you want...
At the global scale, we don't have, yes.
If you want in situ data.
Yes.
And my other question would be, how fast can this be done in the sense that, are we talking about like near real time, or is it something that you need to wait for the GRACE data and so on? So when can you produce an output?
So
how fast?
For a basin like the Ebro and for a long time series, so we do other full record, it takes about one night in a small computer. So if we really optimize things, I think it could be done at.
But what's the latency before you gather all your input and then you can start computing during one night?
I think there is nothing
data.
that we could do that right when you get the data. It could be done daily if you have daily data. And then it will be much faster because we don't do the.
And you would like
full
to
week.
use SWOT as well?
Yeah, yeah.
So maybe you would like to have SWOT data immediately?
Yes.
Is that a recommendation? Et merci pour les recommandations. Hein, recommendation slide.
Okay, so I will add this one.
Okay. Thank you very much. Yeah,
Thank you.
Yeah. And our last presentation, the River Discharge Climate Change Initiative project will be given by two speakers. First part by Maxime Weirs from CLS and Angelica Tarpanelli from IRPI.
So, hi everyone, I'm Maxime from CLS. So, Angelica and I are going to present the River Discharge Climate Initiative project. So, on behalf of Alice, the project manager from CLS, and of course, all the participants involved. So, as you already know, the reverse discharge has been newly added as a new essential climate variable. So, it's now part of the 36 essential climate variable which benefit from space observation. This project is a precursor project of this new essential climate variable as part of the Climate Change Initiative project. So we try to highlight, to demonstrate the feasibility of a long-term time series of river discharge over different basins at different selected locations from both satellite nadir altimeter data and also multispectral images. So about the duration, here we speak about 1 year and a half since February 2023. Our science leader is Sylvain Biacamaria from the Lagos. Our project manager, as I said, is Alice Andral from CLS. Different partners are involved. CNRS, IRPI, EOLA, Magellium, Hydromatters, and CLS. Obviously, we thank all the different participants and try to represent them today with Angelica. So basically, it's where we stand now, computing the river discharge. And we are going to talk about all the different tasks, the user requirements, the basin selection, the generation of water surface elevation time series, and then the validation, round robin, and at the end, climate assessment and a large-scale model. Concerning the user requirement, one can mention the GCOS, GRDC, other CCI partners. About the main requirements, one can cite the need to provide long-term time series of river discharge with associated and consistent uncertainties over different river basins. And as a target for this precursor project, we must generate at least monthly average of a long-term time series and with an uncertainty target of about 15%. About our river basin selection, 18 basins have been selected with different climate and different latitude and data availability. So one can mention, for instance, the Congo, the Amazon, or the Garonne River. So over these kind of hydrological basins, 54 stations at specific locations, so virtual station, are selected with available altimetry data and also in situ discharge available, very useful for calibration and validation purposes. So basically here you can see, more or less, but it's a panel with all the different available data at all specific location. You can zoom in after. Concerning the main objective about the water surface elevation, so the main idea is to provide long-term time series with all the altimetry constellation. So hundreds of water surface elevation have been computed, and next merge ones have been and are generating from this monomission water surface elevation to provide 44 at the end consistent time series. So here you can see an example of such time series. It's an example of the Ubangi River on the Congo Basin. So it's generated from MVSAT, JSON 1, 2, 3, SARAL, and Sentinel-6 data. In this figure, you can also see two outliers due to surrounding water body nearby the main river watercourse. So it can be tricky dealing with altimetry data to remove this kind of point, especially with past mission. So it's kind of current issue that we are dealing with. Also, we can mention some data gaps, especially with past mission and due to the closed loop tracking mode. The mission like Topex, JSON, and MVSAT, for instance. Also, dealing with MVSAT and Saraltica, there is no overlap between these two missions, so bias correction can be tricky. The bias correction to build a consistent water surface time series. Also above 66 degrees and north latitude, rivers are only covered by polar orbiting satellites such as Sentinel-3, so or NVSAT. So it's also an issue. And concerning the uncertainties, obviously, Topex Poseidon and ERS-2 have less accuracy than the following mission. So here for the current issue. And I must mention that all time series will be soon available on the SIDA platform.
About the river discharge, we have three different approaches to provide long time series. The first one is with the use of altimetry, of course, with the traditional or more or less traditional rating curve approach. The second is the one that I explained before with the use of multispectral images. And the third one is the combination of the two, altimetry and multispectral images. So about the first approach, of course, from altimetry, the objective is always to estimate long time series of river discharge. And in this case, they used rating curve from altimetry and in situ river discharge when it is available. There is also the way to use the modeled discharge, or when we don't have consistent time series, so in the same period, we can use the approach of Turian et al. 2013. So this is an example of how to estimate river discharge, and this is another example for the Arctic rivers made by Elena, in which, of course, the conditions could change, and so we need more complex analysis for the rating curve. About the forthcoming tasks, so we need to improve the outlier removal, as Maxime said, also for river discharge, of course, to test the differences if single or merged time series of WSE, the water surface elevations, are used. We need to flag data when we have snow or ice on river. We still need to estimate the uncertainty, especially for the coming working package that are on the assimilation into large-scale models. And we need also to process river discharge for all the stations. About the river discharge from multispectral imagery, you have already seen this image. So actually we build the rating curve with the use of the reflectant index and the in situ discharge. And these are some results for preliminary results for Borgo Forte and Ponte Lago Scuro, in which you can see the long time series for river discharge and by using these images. So next steps and perspectives. Time series of river discharge over all the selected stations will be available in February, we hope. River discharge from multi-satellite data will be the next step, the next working package, and it will be done by combining the level 2 product, so directly the altimetry and the reflectance, or the level 3 product. So we try to combine the river discharge coming from the different approaches. And of course, we have several methodologies to do that. Right-sat algorithm is one of them, but also copula function, CDF function, and machine learning approach. Then we have still to investigate the round robin, actually which method is better than the other. So the round robin it will be done for different methodology. And the most important thing for this project is the evaluation of climate assessment. So with the analysis of trends and so on. And finally, we use also, will be also the large scale model. And so we try to assimilate the water surface elevation and the river discharge into the model and see if there are some improvements. Recommendations for this topic is to maintain a long-term archive of satellite altimetry data and optical images, to guarantee an easy and regular processing with products adapted to land surfaces. The second recommendation is to include other variables or other satellite missions like SWOT in the future evaluation of long time series of river discharge. So again, we have this project website with the documentation and project's goal, and you can visit it. And all these data will be available. The water surface elevation are already available, but also the river discharge dataset will be available on the SIDA platform as soon as they are available. And I want to let you know that there will be a river discharge workshop planned in May, June 2024. So if you are interested in, please contact Sylvian or Alice to be present at this workshop. So thank you for your attention.
Thank you very much for the presentation. And we don't have time for questions, but you can ask 1, 2 questions.
Hello, hello. Did you tell me earlier that there were 3 recommendations and you showed 2? There was not something else? No?
I don't remember.
Okay, I got it wrong. One thing very important to really be motivated to go to this workshop in 2024 is to know where is it going to be? I mean, what kind of food do they serve and so on?
Sorry?
Where?
Yes.
Perugia, in Toulouse?
In Toulouse, probably in Toulouse or maybe in France.
In Toulouse.
In France. Okay, because it's also in Paris.
Yeah.
Probably in
Okay.
Toulouse.
Just one comment. If you want to have a long retrieval, a long time series of river discharge, you cannot count on SWOT because that's going to be a little bit short, right? And so we have the same problem in sea level, CCI. We haven't added the new missions, which are the Sentinel-3 and Sentinel-6 and so on, because we've
we went along with the TOPEX until JSON 3. We're going to add Sentinel-6. That's going to be easy because it's the same virtual station, the virtual coastal stations. But same thing for river discharge. If you want to add SWOT, you're not going to go very far. But I'm eager to see how you can just put a little bit of SWOT at the end and make sure that you have an intermission calibration activity that guarantees that you're talking about a trend which is respected. I mean, the whole CCI story is to make sure the trend is accurate. It's not at all like doing near real-time monitoring.
Okay.
Yeah, sorry, it wasn't really a question, but an expression of interest.
Yes, but I agree with that, but also, yeah, clearly, but also for validation purposes, SWOT providing, I don't know, several and thousand instantaneous rating curves can be part of big validation processes of concerning past data, I think. But it just from my point of view, but it can be useful also for past mission to have data like SWOT to provide a consistent data set using that as a, I mean, as part of validation processes. But it's basically what I have in mind.
Yeah, I see what you mean, but I think that the CCI is really has to really work on the guarantee that the trend is a trend. It's accurate. It's not a intermission bias with steps and so on, and get the climate essential variable with a good accuracy. You're right. Adding SWOT will probably make you understand, you know, how to use properly rating curves and things like that. Okay, that.
Okay. Thank you. Thank you very much. Thank you, Angelica. We have 20 minutes for discussion.
So Elena and I came up with a list of few seed questions to, you know, start the discussion. So I will first present to you those questions. We decided to categorize them in relation with the different very good presentation that we have seen. So first is the question more dedicated to the fully focused SAR method. So it shows improvement in the water level retrievers on many water objects. So who can benefit, who in the hydrologist community may benefit from this processing, and how the user can access to this kind of data? Can we imagine processing on request or specific product, etc.? The other question is, does FFSAR allows to monitor some specific kind of rivers like braided and branching rivers with better accuracy than other SAR or Nadir altimeters? And what are the limitations of such process? The second category is about the combination of altimetry and optical near-infrared sensors. So which sensors can we also have in mind to complement this pair for ongoing and especially historical mission? And what is missing to employ them is data access, validating methodology, data treatment capacity, etc. How can we enlarge them? And what are the limitations of these processes? And is it working at every flow conditions? Do we have limitation on that? The third category is about the same topic, but how to improve that with more dedicated commercial optical or satellite missions. For instance, they have shown improvement in the sampling frequency in the past, for instance, both Pleiades or currently the Pleiades Neo. So could this historical mission or new mission be useful for the discharge community, and how can we access them? This is a question that we have a bit debated before, but can we envision a way for the scientists to get this pricey data using, I don't know, the EU or the ESA to negotiate a shared access for the scientists at lower price or for free? Fourth topic about historical climate change, a very important question. What are the challenges that we have when we combine the different missions and products to derive high quality hydrological variables? How can we share or automate the fusion of those products to continue those experiments? And to conclude, some more general questions. What are the benefits of the EO-derived hydrological variable with respect to in situ discharge? What are the needs for the future missions for monitoring hydrological variable? For instance, is time revisit more important than accuracy or spatial coverage? And finally, a very general question, how can we better advocate for the usage of EO-derived hydrological variable for the stakeholders or government agency, especially in the case where the in-situ gauge network is already available? So any comment on these different questions? Or any other discussion about the presentation?
Could you turn to the first slide, please?
Sorry?
To the first slide.
Yeah. For instance, experts for, yeah, go ahead.
Question. Well, what do you think about making 5 small groups and each group tackles the questions you've posed there? They might be more likely to speak up and come up with solutions and put it on a whiteboard or type it up or
Yeah, maybe.
share.
Maybe in this discussion, we can focus on the more general questions that maybe, see if you have a, I don't know, insight about that. I think, to me, how can we advocate to better advocate for the usage of EO-derived hydrological variables is a very important problem because, from what I know, the government agency or stakeholders are not very familiar with EO products, and they don't really want to tackle with them as they have the gauge station already available. So how can we better present our results, how to better, any comment on that? Or any wishes?
It's because someone's got to say something. But no, I think that to your last point, I think it's demonstrating benefit. It's demonstrating quality and benefit. And I'm presenting tomorrow on my project, but we wanted agencies to help us with validation data for my projects. We didn't have the budget to get out there and collect validation data ourselves. I had a conversation with Environment Canada. We talked about, to the last question on the previous slide, the cost of commercial EO data. The response from Environment Canada was, well, if you can get us good results, it's cheaper for us to pay the commercial provider than it is to send 2 or 3 people on a plane up the Yukon River. So, but we've got to demonstrate quality. We've got to demonstrate we can get results in a timely fashion. And also I think, as someone who worked for the Environment Agency, which covers England, and is the sort of statutory monitoring agency, engagement with science and research isn't always that strong. The links aren't that good. I don't know if there's anyone in the room representing a monitoring agency today, but you've got to have that interaction, I think, for people to gain confidence.
Okay.
Thank you very much.
Try a question.
You can use the microphone, which is.
Yeah, you can use this one.
Okay.
Oh,
Yeah, you can.
Thank you. It's actually on the second slide. Sorry, I jump slides here. It's about the first one with the gauges. I don't know where to start. So gauges are in decline globally. Actually, what we haven't talked about so much, but Jérôme talked about it a little bit outside there at coffee. One reason gauges are crucial is because they have an extremely high temporal frequency. So modern gauges tell you every minute you have a water level. And this is very important when we're talking about real flash flood events. It's very important also to, I don't know, I'm not a hydrologist. Maybe Nick, you could say a lot more about this, importance of gauges that measure at very high frequency. This is something I think it's not really possible to get there with satellites unless Elon Musk is helping to put 60 satellites a day up there that measure with altimeters, you know, every possible river at 5 minutes. Why not? He could do it. He launched Starship. So, but my question is, what do we do? What goals do we set with remote sensing for gauges? Because I don't think we can replace the gauges. But when I look globally, it seems like we should start replacing them because every year real gauges are just declining because of budget questions, of other questions. And we've seen in countries that have difficulties keeping the gauges alive, what great things remote sensing can do. So my question is more like, what are we trying to do with all these discharge studies? Are we trying to complement gauges or showing actually at some point that we can get towards something like flash flood monitoring with remote sensing? Because I think that would be a really cool goal to set. You know, if we can get to really this flash flood problem, because flash flooding is a problem for every sector, everybody. I think if we could demonstrate that capability, that would be great. So it's not a question, it's more like, you know, call for action or setting some goals would be really useful for everybody. Understand what is the goal we're trying to achieve with the discharges from space. Thank you.
Yeah, but just for discussion, for flash floods, actually we speak about small rivers, rarely about medium-sized rivers. Yeah, but our capability for small-sized rivers are still limited. So probably we are able to use precipitation data for forecasting, watch how they come to the specific place, to the specific watershed. But except for precipitation, what other types of satellite data could be useful from this question?
No, I think that's exactly part of that problem is also the size of rivers, because everybody, you know, these rivers can go into flood very, very often and very, very rapidly. And these are the rivers that now insurances and everybody else gets interested in because it's the one that are destructive. It's not the big Amazon River that is flooding so regularly. Actually, it's a problem when it doesn't flood, like we've seen now with the big drought in the Amazon. So, but in Europe, it was, for example, 2021 was the very small rivers in some countries that created huge problems. And there, remote sensing or satellite science cannot help. But everybody's getting that expectation that they should be helping. But there must be ways that we can help even in these rivers, and even if gauge is monitoring every 5 minutes, maybe there's a way we can get there. Maybe like you say, maybe through a combination of modeling, maybe looking at other variables, but then also looking at discharge from space. I have no idea. I'm just throwing that out there to, I don't know, get some thinking started.
Okay, thank you very much.
Yeah,
Thanks.
thank you. And I'm a flood person, by the way, so I'm always having that kind of question. And that's flooding.
Thank you.
Okay. So just for the last question, how can we better advocate for the users of you? Few years ago, when we were starting with SWOT, we were wondering, because we were telling to everybody that SWOT will be an excellent satellite mission for example, for transboundary river basin monitoring to help the stakeholders, to help the water management people, etc., etc. But we were not really sure of will it be so useful. So we did an exercise which was that we make big interview with many different people in two big basins, two different basins, the Amazon basin and the Rhine basin. And we were simply prepare a questionnaire these people, because these people, they are not the same community than us, and how they can, in fact, see if this kind of satellite can be helpful. And the result of this inquiry and this questionnaire was very surprising and very interesting, because in fact, first of all, it depends on the basin, it depends on the situation, of course. The Rhine Basin, you have a commission which is well organized with a lot of data, with a lot of protocols on how to make the measurements, et cetera, and they didn't, how to say, express a lot of interest. So we were surprised because they say, okay, your satellite, first, it will be only for 3 years. Second, the latency is not enough. And we don't need it, maybe for small reservoirs. So, and last point, and for the other basin, it was the same. They said, what we need, we have engineers, we are not researchers. And we don't want to have a new mission like this, where we have to commit, not to commit, but to involve ourselves in research development of new algorithms, etc. We need something which is ready on the table, and we need training. So I said that, so it was very interesting for us to understand that our idea of what the interest could be for this from this mission is not, in fact, what they were waiting for. And so I think that it's not so easy when we arrive as a scientific community, space agency, etc., and to say to these people, look, this data, you should use it because they are very useful. They would be. We need to go to them and to try to understand what is their need. And often their need, for example, is to have a very high temporal resolution. You know that, and all of our satellites don't have such high temporal resolution that they need. So that's why maybe we were trying to advocate for the SMASH mission, the constellation, when they repeat. So there is really a need, in order, if we want to answer to this question, to have, how to say, a strong discussion, long-term discussion with these people if we want to convince them to use our mission. So it's not an easy exercise, and I don't think we can answer only ourselves. And this need maybe over conference or over workshop or over discussion, because they are not so easily convinced that this can be helpful.
Yeah, I agree with that, because I'm working sometimes in the French agency for flash floods, for instance. And okay, for the flash flooding, it's not the time revisit is not good. It's an evidence, but we can tell them, and with discussion we can interact with them and say, okay, we have a fine spatial resolution with SWOT, for instance, and this is something that you could use. And we need to show what we are capable of and make them interested with that, and to convince. And well, I think this is a two-way problem. First, we need to, as you said, to gather their needs, their real needs, and then express for our scientific community, and then show them that the satellites and every method that we are developing can be useful for their needs. That's something we need to interact, as you said.
Just a comment. Actually, I made echoes to everything that you have said. What I think is important is that actually we shouldn't be, I don't know, river discharge community, precipitation community, soil master community. We should be all together first. And second, we should be honest. Flash flood, we will not, at least in the next 10 years, we will not do anything with satellite data. Latency is, we will never have the latency. The latency for this kind of problem is 10 minutes. Who is going to provide 10 minutes data? Only Metasat data. So we can't afford these activities, but for sure we can add, I don't know, for water resource management, we can do something. For long-term climate change assessment, we can do something. So basically, what is missing here, probably, I don't know, in the next days, we will have something more, is actually the link between the product that we have and the application that we would like to target. And we should be honest that we actually I don't know, don't claim that we are going to target flash flood forecasting, because it's, to me, it's really something out of the current capabilities of any kind of satellite dataset.
Thank you very much.
Hello? Hello. Okay. Yeah, so just to add to this question of the discharge, so we have time series of discharge, which is quite daily and even better resolution, but we don't have the spatial coverage. And probably the satellite community can provide spatial coverage, which is better than the gauging stations. And so we just have to look at what is there and what can everybody provide and put these things together. So this is quite important, I think. Okay. Thank you.
Great. Yeah, I think it's very important. The magic word, very in fashion now, is co-design. Of course, we need to do things that first we want to do for science, for the advancement of science. And when you talk about application, okay, it has to be co-design. Okay, flash flood. Let's just remove the word flash. And talking about floods, for instance, the United Mission in South Sudan, UNMISS, and Médecins Sans Frontières, Doctors Without Borders, they said, I want to know if the water level will be 10 centimeters higher or lower in 3 days. Because it takes 3 days to put one more brick over the levee to protect the Bentiu camp, where there's 100,000 refugees, a hospital of Médecins Sans Frontières. So can we predict the water level around Bentiu, which is, we saw the map from the keynote this morning, water everywhere. Can we predict that if the level will be 10 centimeters higher or 10 centimeters lower in 3 days? And I think this is an interesting requirement from the people who are asking. So, we had meetings on the subject and so on. So we're trying to supply this information to them. And of course, it's and the small rivers are very important. But for instance, we have in France a beautiful Vigicru network. And when you see the map of France, you see dots everywhere. And so, oh, wow, beautiful network. And then you start zooming, and then you start getting the complaints from the small mayor, for the important mayors of the small town. And they say, my river isn't covered, okay? And my river is small, and when it rains, then I have water all over the village. And then it comes to the first floor of the houses, and then one house goes down the river. And it's true, small rivers are probably more dangerous than the Amazon River. So Guy made the point. And that's why we like to see these high resolution technology and push towards higher and higher resolution. So fully focused SAR and two-dimensional altimetry, and also high resolution optical. And even if, we say the private sector is launching cell phones with a beautiful camera on board and selling the data at a very expensive price. But of course, they're trying to pay salaries and pay taxes and so on. But launching a satellite like SWOT is also very expensive. And so everything has a price, It's like when you talk about water should be free for everyone, but it's not free. Water has a cost. And so we can take this into account. Either it's coming from the public sector, meaning the taxes that are paid by the taxpayers, or it comes from a private sector, meaning the people who make profit, they give the profit to the shareholders and they pay tax on the income. And so this is the economy that we can boost if we develop applications that can be either seductive to the private sector so they can take it on board, or useful for the governments to protect their population, because it's what we say in French, régalien, so regalian, it's a king's duty to protect his subjects.
Thank you very much.
One last question.
Just to say that today we saw a lot of variables that relate to the availability of water, which can be good or bad, right? You have too much water, then you have a flood or you have a drought. But maybe on the feed box that we have there, I think it would be interesting to link all this water availability also to ecosystem services, and maybe to quantify the value of ecosystem services will move more the social society and politicians, the community, to get involved and be excited about these variables. But then what I'm thinking might be missing, or at least we didn't hear today, is data, the quality of the water. So there is a lot of water that is poisoned, so available, but not useful for the people and threatening the livelihoods. So I think something capturing the water quality would be very useful.
Thank you very much for the comment.
Last one, we were all discussing about user requirements and code design and stuff. I think what I'm really missing in most of what we do here are the actual user requirements. And one recommendation we can have to maybe not space agencies, but European Commission or GEO or another big institution is please provide user requirements for applications, not just the GCOS requirements, which have been designed for climate. And to be honest, most of them have been written by us. We need actual user requirements. And one important thing is we are here trying to have the very last centimeter of accuracy on water level, but we don't have even the threshold requirements. You said it. Sometimes you just need to know if it will be 10 centimeters higher, or maybe 50 is already an interesting information. And we don't publish the data because we are afraid that we will have bad reviews or something, but it's useful data. Maybe, I don't know. But we are really lacking the requirements for, not just for every variable, but for each application. What is the threshold? What is the target? When should we stop working? If 10 centimeters is enough, why should we try to have 8? I don't know. So yeah, that would be my recommendation, work on the requirements as a whole.
Okay. Do you mean for each application we should elaborate specific requirements? Or
for each application, which variable do we need? And for each variable, what is the accuracy, the spatial resolution, the time resolution, threshold, target, etc. Maybe it exists, but I never saw it.
Oh, it exists in general for instrumentation, at least for hydrological parameters. But I looked in this tables, and it was 0.001 meter by second for velocity, which is unrealistic.
Unrealistic from what we can do, or
for instrumentation?
Yeah, but it's a requirement. So
yeah,
we can't do it. We can do it, but at least it's a requirement.
Okay.
I don't know.
Thank you.
Any other comment? Question, discussion? I think we can close the session then. Thank you very much, all.
Thank you.
Yeah, so I have a comment. It's not an easy task, and I would really like to thank the co-chairs to think of building the future with the right question and launching discussion. And I count on the other co-chair. There are 42 co-chairs working to try to get something really some good juice out of this workshop and to help what the population, the agencies, to design the future. So big thanks to the co-chair. They're not just chairing a session, but they're contributing to building the future with your collaboration. So thank you. And now we continue the discussion and the feedback, and so, but outside, where you have an icebreaker cocktail. That's for the Arctic rivers. And Elena, the ice breaking will take place now.